up, everybody? This is Tech G, and I want to welcome you all to my CompTIA Network Plus N10-009 certification course. And the information that I will be presenting in this course is going to give you everything that you need to know to successfully pass this examination, assuming that you study properly. The CompTIA Network Plus certification, this is a globally recognized credential that validates foundational networking knowledge and skills required for IT professionals. And this certification covers essential networking concepts, including network architecture, infrastructure, security, troubleshooting, and operations. And the CompTIA Network Plus certification is vendor neutral, making it valuable for professionals in various IT roles, including network administrators, IT support specialists, and help desk technicians. And it serves as a foundational certification for advancing into specialized networking or cybersecurity certifications like the CCNA or the Security Plus. All right, so let's talk about some of the skills that you're going to learn during this course. So you're going to learn about networking concepts, and that's going to take up about 23% of the exam. And this domain will focus on basic networking concepts, including the OSI model, network appliances, applications, cloud concepts, connectivity options, and much more. Then there's network implementation, and this is going to make up 20% of the exam. And this is going to focus on routing technologies and important factors of physical installations, configuring switching technologies, and wireless devices. Then there's network operations. It's going to take up 19% of the exam. And this is going to focus on monitoring and optimizing networks to ensure business continuity. Then there's network security. That's going to take up 14% of the exam. And this is going to focus on understanding security concepts and network attacks to harden networks against threats. And then there's network troubleshooting, and that's going to make up 24% of the exam. And this is going to focus on the troubleshooting methodology and address common issues related to networking, including cable, connectivity, and software problems. All right, and finally, let's go over some of the exam details of the Network Plus certification. So the CompTIA Network Plus 009 certification, this is the latest and greatest exam version, and it was launched on June 20th, 2024. Now, at the time of this recording, CompTIA has not scheduled a retirement date for this exam, but normally 3 years after the launch of an exam is when you can expect for that exam to be officially retired so they can begin introducing the latest version. Also, this exam has a maximum of 90 questions, and the questions are presented as a multiple choice and performance based. There is a 90-minute time limit, and in order to pass this exam, you will need to score 720 out of a possible 900 points or get an 80% on the exam. Now, it is recommended by CompTIA that a candidate be CompTIA A+ certified and have at least 9 to 12 months of hands-on experience working in a junior network administrator or network support technician role. However, I have had plenty of students pass this certification without any IT experience whatsoever. So if you pay attention to these slides and take notes, there's a great chance that you will pass. Now, when it comes to the languages, the exam is available in English, Japanese, German, Spanish, and Portuguese. And the company that is responsible for administering the test is a company called Pearson View Testing Centers. And the cost of the CompTIA exam at the time of this recording is $369. Now, if you want to get a voucher at a much cheaper price, you can always visit my website, Technology G, where I sell discounted exam vouchers. So make sure you take advantage of that. Now, with all that being said, let's go ahead and get into the CompTIA Network Plus course. The Open Systems Interconnection, or the OSI model, this is a foundational framework for understanding and implementing network communication. It was developed by the International Organization of Standardization, and this 7-layer model breaks down the processes of network communication into manageable and distinct functions. Now, for those preparing for the CompTIA Network Plus certification, understanding the OSI model is not only essential, but also a cornerstone for mastering networking concepts. And in this video, we're going to go through the 7 layers of the OSI model. So we have the physical layer, the data link layer, network, transport, session, presentation, and application. We're going to explore the key functions, protocols, and devices that are associated with each layer, ensuring you have a clear and practical understanding. All right, so let's talk about layer one, which is known as the physical layer. So, the physical layer, this is the foundation of the OSI model, responsible for the transmission of raw binary data over a physical medium. And this layer includes the hardware elements of networking, such as cables, switches, and network interface cards. And its key functions are as follows. So, it defines the physical characteristics of the network, such as voltage levels, timing, and data rates. It converts binary data into signals, such as electrical, optical, or radio for transmission, and it handles the physical connection between devices. And some common devices and technologies that fall upon the physical layer are Ethernet cables such as Cat5e, Cat6, and fiber optics. You have hubs and repeaters, and you have physical ports and connectors. Now, for an exam tip, you want to be familiar with the types of cables such as twisted pair, coaxial, and fiber optic, and their respective use cases, including transmission speeds and distances. All right, so let's move on and talk about layer two, which is known as the data link layer. So the data link layer, this ensures reliable transmission of data over the physical layer by establishing error detection and correction mechanisms. And it is divided into two sublayers. You have what is called the logical link control and the media access control. And its key functions are as follows. So it organizes data into frames for transmission. It provides error detection and flow control, and it manages access to the physical medium using MAC addresses. And some of the common protocols and devices are as follows. So you have what is called Ethernet or IEEE 802.3. You have Wi-Fi. This is IEEE 802.11. And then you have switches and bridges. Now, as another exam tip, you want to understand how MAC addresses function and the role of switches in forwarding frames based on these addresses. Additionally, you want to grasp the concept of VLANs and how they segment networks at this layer. All right, next let's talk about layer three, which is known as the network layer. And the network layer is responsible for determining the best path for data to travel between devices on different networks. And it uses logical addressing such as IP addresses to route packets. And its key functions are as follows. So it provides logical addressing and routing, fragmentation and reassembly of packets, and path determination based on routing protocols. And some common protocols and devices are as follows. So you have the internet protocol, IP version 4 and IP version 6. They have various routing protocols such as OSPF, EIGRP, and BGP. And then you have routers that move the data from one network to another. And as an exam tip, you want to be able to distinguish between IP version 4 and IP version 6 addressing and understand how routing protocols function to direct traffic across networks. All right, next let's talk about layer 4, which is known as the transport layer. And the transport layer provides end-to-end communication control and ensures complete data transfer. It segments data into smaller units, manages connections, and facilitates error recovery. And some of its key functions are as follows. So there's segmentation and the reassembly of data. It offers flow control and congestion avoidance. And it also offers error detection and correction. And some common protocols associated with it are transmission control protocol and user datagram protocol. Now, as another exam tip, you want to understand the differences between TCP and UDP. So TCP is connection oriented and reliable, while UDP is connectionless and faster but less reliable. And recognizing scenarios where each protocol is used, such as streaming for UDP or email for TCP, this is also crucial. All right, so let's move on to layer 5, which is known as the session layer. And the session layer, this manages and controls the dialogue between two devices, and it establishes, maintains, and terminates communication sessions. And its key functions are as follows. So there's the session establishment, maintenance, and termination. There's synchronization and dialogue control, and then there's managing multiple sessions. And its common use cases are as follows. So you'll find it being used in remote procedure calls, network file systems, and session initiation protocol. Now, as an exam tip, while the session layer is less tangible than the other layers, it focuses on its role in maintaining session states and ensuring orderly communication between devices. All right, so let's move on and talk about layer 6, which is known as the presentation layer. And the presentation layer, this ensures that data is in a usable format for the application layer, and it handles data encoding, encryption, and compression. And its key functions are data transmission and formatting, encryption and decryption, and compression and decompression. And the common standards that are associated with it are secure sockets layer, the transport layer security, JPEG, MPEG, and ASCII. And as an exam tip, you want to recognize how the presentation layer facilitates compatibility between different systems by standardizing data formats. And also remember that encryption protocols like SSL and TLS, they also operate at this layer. And then let's talk about our last layer, which is layer 7, which is known as the application layer. And this is the layer that is the closest to the end user, providing network services and interfaces for applications. And it enables software to communicate over the network. And its key functions are as follows. So there's network service requests and responses, there's resource sharing and remote access, and then there's end user application interaction. And the common protocols and applications that are found at this layer are HTTP, or Hypertext Transfer Protocol, File Transfer Protocol, Simple Mail Transfer Protocol, and the domain name system. And as an exam tip, you want to understand the protocols and services that operate at this layer, particularly their role in facilitating user to network interactions. So for example, DNS, this resolves domain names to IP addresses, while HTTP facilitates web browsing. And here are some study tips to help you memorize the OSI model. So you want to use what are called mnemonics. So you want to remember the layers with phrases like, please do not throw sausage pizza away, which stands for physical data link network transport, session presentation, and application. You also want to understand relationships. So you want to grasp how data flows between layers and the interaction between protocols and devices at each layer. And then there are some practical scenarios. So if you get the chance, you want to apply your knowledge to real world networking issues to solidify your understanding. And you can do that by doing some labs. And if you want to go to my website, Technology G, I offer a whole bunch of virtual web browser based labs to help you really grasp these concepts. Now, mastering the OSI model, this will provide a strong foundation for networking. And with this knowledge, you're not just preparing for the Network Plus exam, but you're building expertise that will serve you throughout your IT career. So to wrap this lesson up, the OSI model layer, this works in unison to enable seamless communication across networks, from the raw transmission of binary data at the physical layer to end user interaction at the application layer. Each layer serves a distinct role while interacting with adjacent layers. Now, understanding the OSI model, this is critical for the CompTIA Network Plus exam. So focus on the functions, protocols, and devices associated with each layer. And by mastering this framework, you will not only be well prepared for the exam, but also equipped with a fundamental knowledge base for your networking career. Now let's get to the fun part, the check on learning. So the first question is, which layer of the OSI model is responsible for establishing, maintaining, and terminating connections between two devices? Would it be layer 3, layer 4, layer 5, or layer 7? And the correct answer is it will be layer 5, or the session layer. So the session layer is responsible for managing and controlling the dialogue between two devices. It establishes, maintains, and terminates communication sessions. And this layer ensures proper data exchange and controls interactions between devices during communication. Next question. At which OSI layer do switches primarily operate the forward frames based on MAC addresses? Would it be layer 1, layer 2, layer 3, or layer 4? And the correct answer is it will be layer 2, or the data link layer. So switches, they primarily operate at the data link layer of the OSI model. They forward frames based on MAC addresses and are essential for LAN communication. And this layer handles frame creation, addressing, and error detection for data transmission. And our final question, which OSI layer is responsible for the end-to-end delivery of data and ensures error recovery and flow control? Would it be layer 3, layer 4, layer 6, or layer 7? And the correct answer is it will be layer 4, which is known as the transport layer. So the transport layer is responsible for reliable delivery of data between devices. It provides end-to-end error recovery, flow control, and segmentation of data. And protocols like TCP, or the Transmission Control Protocol, they operate at this layer to ensure data integrity and proper sequencing. The CompTIA Network Plus certification. This is a critical credential for IT professionals seeking to build expertise in networking technologies. Among the exam objectives is understanding and differentiating between networking appliances, their applications, and their functions. And in this video, we're going to explore the foundational concepts outlined in the CompTIA Network Plus exam objective 1.2. All right, so let's talk about physical and virtual appliances. So networking appliances, they play a vital role in managing and securing data as it traverses a network. And these appliances can be physical hardware devices or virtualized solutions deployed in cloud or on-premises environments. And so we're going to go through an exploration of some of these key appliances. So let's talk about the router. So the function of a router is as follows. So routers, they connect multiple networks and direct data packets between them based on their IP addresses. They make decisions about the best path for forwarding packets. And routers, they are typically found in homes and enterprises, and physical routers, they provide connectivity and routing functions at the edge of a network. Then we have what is called a virtual router. So this is a software-based router that runs on virtualized environments and is often used in cloud networks or software-defined networking environments for scalability. Next, we have what is called a switch. And a switch, this operates at layer 2, or the data link layer of the OSI model, where it forwards data packets within a local area network based on MAC addresses. And within that, you have what is called a managed switch. And a managed switch, this allows admins to configure VLANs, QoS, and monitoring. And then you have what is called an unmanaged switch. And this is just a simple plug and play device with limited functionality. And then we have what is called a virtual switch. And these are deployed in virtualized environments to connect virtual machines together. Next appliance is that of a firewall. And firewalls, they act as barriers between trusted and untrusted networks, where they use predefined security rules to allow or block traffic. Physical firewalls, these are dedicated hardware that are designed to filter traffic at the network's edge. And then we have a virtual firewall, and they are often deployed in cloud environments to secure virtual networks. Moving on, we have what is called the intrusion detection system and intrusion prevention system. And IDS, what they do, they monitor network traffic for suspicious activity, while the IPS, it actively blocks identified threats. And IDS and IPS physical appliances, basically these are dedicated hardware that are designed for high performance traffic analysis. And then you have the virtual version, where these are cloud-based solutions that integrate with virtualized or hybrid environments. The next appliance is that of a load balancer. And a load balancer, this distributes traffic across multiple servers to ensure availability and prevent overload. A physical load balancer, they are often deployed in data centers to manage server workloads. And then virtual load balancers, these are software solutions offering similar functionality, where they are often integrated into cloud platforms. Then we have what is called a proxy server. So proxies, they act as intermediaries between clients and servers, providing content filtering, caching, and anonymity. And the physical proxy server, they are used for high performance web traffic management, whereas a virtual proxy server, they are integrated into enterprise networks for remote access or cloud-based filtering. Moving on, we have what is called network attached storage. And what this does is it provides file-based storage that is accessible over a network. And the physical NAS, it's a standalone device that connects to a local area network. And then you have the virtual NAS, and this is a software-based solution that integrates with cloud environments for scalable storage. And then we have what is called a storage area network. And this is a high-speed network providing block-level storage for enterprise applications. You got the physical SAN, and this requires specialized hardware like fiber channel switches and host bus adapters. And then you have the virtual SAN, where this uses software-defined storage solutions to provide block storage in virtualized environments. And then we have what is called a wireless access point and controller. So what this does is it extends wireless coverage by connecting wireless devices to a wired network. You have the controller aspect, and this is the centralized management for multiple access points, allowing administrators to configure and monitor wireless networks. And then we have virtual APs and controllers, and these are cloud-based solutions for managing wireless devices where they are commonly seen in modern enterprise environments. All right, so let's move on and talk about some applications. And the first one we're going to talk about is called the Content Delivery Network, or a CDN. So a CDN, this optimizes the delivery of web content by caching data at distributed edge servers closer to users. And this reduces latency and improves the end user experience. And its use cases are as follows. So it can be used for video streaming, e-commerce, and global web application deployment. And services like Cloudflare, Akami, and AWS CloudFront, they offer CDN solutions that are tailored for different business needs. All right, moving on, let's talk about some core networking functions. So networking appliances and applications, they often provide core functionalities that enhance performance, security, and connectivity. And we're going to quickly talk about three critical functions. So the first one is that of a VPN, or a virtual private network. So VPNs, what they do is they provide secure communication over public networks by encrypting data. And you got two types. You got a remote access VPN, where this enables users to securely access a private network remotely. And then you have what is called a site-to-site VPN, where this connects entire networks securely over the internet. And the common protocols that they use are IPsec, SSL, TLS, and OpenVPN. And the use cases for VPN are remote work, secure data storage, and bypassing geographic restrictions. Another function is that of QoS, or quality of service. And what this does is it prioritizes certain types of traffic where it ensures critical applications like voice over IP and video conferencing, they receive sufficient bandwidth. And some of the key concepts of QoS involve the following. So you have traffic shaping, and this is where it controls the rate of outbound traffic. You have what is called a differentiated service, and this uses packet marking to indicate priority levels. And then you have what is called an integrated service, where this ensures guaranteed bandwidth for specific applications. And the use case for QoS is as follows. So enterprises, they rely on QoS to support business critical applications without interruptions. And another core networking functionality is called time to live, or TTL. So TTL, this is a field in IP packets that limits the number of hops a packet can traverse before being discarded. And basically this prevents infinite looping in routing. So what happens is each router decreases the TTL value by 1. And when the TTL reaches 0, the packet is dropped and an error is sent back to the source. And the use case for this is it ensures efficient use of network resources, and it helps prevent routing loops. All right, so let's talk about some real world applications of these concepts. So understanding the integration of these appliances, applications, and functions is critical for designing robust and scalable networks. So we're going to talk about some real world scenarios that illustrate how these components work together. So when it comes to an enterprise deployment, an organization, they'll deploy physical routers and switches to establish a core network. Firewalls and IDS and IPS appliances, they protect against these threats, while the load balancers ensure web application availability. When it comes to cloud integration, virtual appliances, they are used for scalability, including virtual firewalls, load balancers, and proxies. When it comes to wireless solutions, employees, they can connect to a corporate Wi-Fi network that is managed by virtual APs, or access points, and controllers. Then when it comes to enhanced performance, quality of service, this prioritizes the voice over IP traffic for smooth communication, and CDNs, or content delivery network services, they accelerate the website performance. And then you have secure access. So VPNs, they will enable remote employees to connect securely to the enterprise network. All right, so in conclusion, networking appliances, applications, and functions, these are the building blocks of modern IT infrastructures. And mastering these capabilities, this is essential for IT professionals aiming to secure and optimize network operations. And by understanding the physical and virtual components, applications like CDNs, and functionalities like VPNs, QoS, and TTL, you will be well prepared to tackle real-world challenges and ace the CompTIA Network Plus examination. All right. So, with all of that being said, let's do some check on learning. So, the first question is, which of the following devices functions primarily to provide centralized authentication and encryption for wireless devices on a network? Would it be a router? Would it be an access point? Would it be a wireless controller? Or would it be a firewall? And this will be a wireless controller. So, a wireless controller, this manages multiple access points within a network and does some centralized tasks such as authentication, encryption, and configuration. It ensures seamless connectivity and security for wireless devices, while an access point, this provides access, but the controller, it coordinates the network. Next question. Which network appliance balances incoming traffic to multiple servers to ensure optimal performance and fault tolerance? Would this be a firewall, a load balancer, a proxy server, or network attached storage? And the correct answer is this will be a load balancer. So, a load balancer, this distributes traffic across multiple servers, ensuring no single server is overwhelmed. And this improves performance and reliability, often by redirecting traffic during server failures. Other appliances like firewalls and proxies, they do not perform traffic distribution. And our final question, which of the following is a function of a content delivery network? Is it encrypts data transmitted between devices? Is it reduces latency by caching content closer to users? Is it prevents unauthorized access to internal networks? Or does it monitor network traffic for malicious activity? And the correct answer is it reduces latency by caching content closer to users. So a content delivery network, it caches content like web pages and videos at multiple locations globally to reduce latency and improve user experience. It decreases the load on the original server and ensures faster delivery of content. The other options describe security and monitoring functions that are unrelated to CDNs. In the evolving landscape of IT infrastructure, cloud computing has become a cornerstone for organizations striving for scalability, cost efficiency, and agility. And CompTIA's Network Plus certification, this underscores the importance of understanding cloud concepts and connectivity options as part of network management and design. And in this video, I'm going to provide you an in-depth overview of these cloud topics to help you ace the objective 1.3 of the exam. All right, so let's begin by talking about network functions virtualization. So, network functions virtualization revolutionizes traditional network architectures by virtualizing hardware based network appliances. Instead of relying on proprietary hardware, NFVs they leverage software running on commodity servers to perform tasks such as firewalls, load balancing, and intrusion detection systems. And here are some of the key benefits of NFV. So, there's cost reduction. So, they minimize reliance on expensive proprietary hardware. You can easily deploy new virtualized network functions as demand increases, and it simplifies network updates and changes by enabling dynamic reconfiguration. Also, NFV is foundational for cloud native environments where they allow service providers to adapt quickly to changing requirements while reducing operational overhead. All right, next let's talk about a virtual private cloud. So this is a logically isolated section of a public cloud that provides users with a private environment to deploy and manage resources. And organizations, they can control their own subnets, route tables, and IP address ranges within a VPC. And some of the key features of a VPC include the following. So there's logical separation of resources from other users of the public cloud. You have control over network configuration, such as IP address ranges and subnets. And there's enhanced security measures, such as network security groups and access control lists. And also, VPCs, they are ideal for organizations that need the flexibility of public clouds while maintaining control over their network infrastructure. All right, next let's talk about network security groups and network security lists. So network security groups and network security lists, they are essential for controlling access to resources within a cloud environment. So a network security group, it acts as a virtual firewall at the instance level, and NSGs, they allow or deny inbound and outbound traffic based on rules that are defined by the user, and they typically operate at the virtual machine level. And then when it comes to a network security list, they operate similar to an NSG, but often at the subnet level, controlling traffic flow between subnets or external networks. Now, both tools, they are critical for enforcing least privilege and safeguarding cloud-based resources. All right, so moving on, let's talk about a cloud gateway. So gateways, they play a pivotal role in connecting cloud networks to external networks. And the key types include the following. So you have what is called an internet gateway, and this provides scalable and secure access to the internet for resources within a VPC. And then we have what is called network address translation gateway, or a NAT gateway. And this enables outbound internet connectivity for instances in private subnets while preventing inbound connections. And NAT gateways, they help maintain security by hiding private IP addresses from external networks. And also by strategically deploying these gateways, organizations, they can ensure seamless and secure cloud connectivity. All right, so moving on, let's talk about cloud connectivity options. So cloud connectivity options, they determine how organizations connect to their cloud resources. And the primary options are as follows. So we have what is called a VPN, or a virtual private network. And this securely connects on-premises networks to the cloud via encrypted tunnels over the internet. They are cost effective and straightforward to set up, and they are suitable for small to medium-sized businesses with limited budgets. And then we have what is called Direct Connect, and this provides a dedicated private connection between an on-premises network and the cloud. It offers lower latency and higher reliability compared to VPNs, and they are ideal for organizations requiring consistent, high-performance connectivity, such as in data-intensive applications. Now, both options serve different needs, and organizations, they often choose based on performance requirements and budget constraints. All right, so let's move on and talk about cloud deployment models. So cloud deployment models describes how cloud services are implemented and utilized. And the three primary models are as follows. So the first one is the public cloud. So this is where resources are owned and operated by a third-party provider and shared among multiple users. It offers cost efficiency, scalability, and reduced maintenance responsibilities. And some examples are Amazon Web Services, Microsoft Azure, and Google Cloud Platform. Then there's the public cloud, and this is dedicated to a single organization providing enhanced control and security, and it can be hosted on premises or by a third-party provider, and it's ideal for industries with strict regulatory requirements such as healthcare and finance. And then there's the hybrid cloud, and this combines public and private cloud environments, allowing data and applications to move between them. And it provides flexibility for workload distribution and cost optimization. And an example use case would be where you would run sensitive workloads on a private cloud while leveraging public cloud resources for less critical tasks. All right, so next, let's talk about cloud service models. So cloud service models, they define how services are delivered and consumed. And the first one is called software as a service. And this delivers software applications over the internet on a subscription basis. It provides infrastructure, application management, and updates. And examples of this could be Microsoft 365, Google Workspace, and Salesforce. Then there's infrastructure as a service. This offers virtualized computing resources such as servers, storage, and networking. And the users, they have control over the operating systems, applications, and middleware. And examples of this will be AWS EC2 and Microsoft Azure virtual machines. And then there's platform as a service, and this provides a platform for developers to build, test, and deploy applications without managing underlying infrastructure. And examples of this will be Google App Engine and AWS Elastic Beanstalk. Now, understanding these models is crucial for selecting the appropriate service type that are based on your organizational needs. And if you still don't understand the differences between software as a service, infrastructure as a service, and platform as a service, here is pizza as a service that can hopefully put this into context for you. All right, so let's move on and talk about scalability. So scalability, this refers to the ability of a cloud environment to grow or shrink resources to meet changing demands. And this includes what is called vertical scaling. This is where you add more resources like CPU and RAM to an existing instance. You have horizontal scaling. This is where you add more instances to distribute the workload. And cloud providers, they use automation and orchestration to ensure seamless scalability, which enables organizations to handle functioning workloads efficiently. The next concept is called elasticity, and this is a specific aspect of scalability that involves automatic provisioning and deprovisioning of resources in response to real-time demand. And this ensures organizations only pay for what they use. So, for example, an e-commerce site that's experiencing a surge in traffic during a sale, they can automatically scale up their resources. And once the traffic subsides, the resources scale down to minimize costs. So elasticity, this is a hallmark of cloud computing where it provides cost efficiency and dynamic resource management. The next concept is called multi-tenancy, and this allows multiple customers or tenants to share the same physical infrastructure while maintaining logical isolation. So each tenant's data and applications are securely segregated. And the benefits of multi-tenancy include the following. So there's cost efficiency. So the shared resources, they reduce the overall cost for each tenant. There's resource utilization, so they can maximize the efficiency of cloud resources. And then there's maintenance, where they have streamlined updates and maintenance across all tenants. And cloud providers, they employ multi-tenancy to deliver scalable and cost-effective solutions while ensuring security. All right, so to wrap this lesson up, mastering cloud concepts and connectivity options, this is critical for IT professionals aiming to achieve the CompTIA Network Plus certification. From understanding NFVs and VPCs to grasping the nuances of deployment and service models, each topic forms a fundamental building block of modern network design and management. Now, as organizations increasingly adopt cloud solutions, proficiency in these areas will not only help you pass the Network Plus exam, but also enhance your career prospects in the dynamic world of IT networking. And by leveraging this video, you're well on your way to understanding and implementing effective cloud strategies in real-world scenarios. All right, so with all of that being said, let's do some of this wonderful check on learning. So the first question is, what is the primary purpose of a network address translation gateway in a cloud environment? Is it to provide encryption for secure communication between cloud resources? Is it to enable private instances to access the internet without exposing them directly? Is it to restrict incoming traffic based on predefined rules? Or is it to connect on-premises networks directly to cloud resources? And the correct answer is, it is to enable private instances to access the internet without exposing them directly. So a NAT gateway, this enables private instances in a virtual private cloud to access the internet while keeping them hidden from incoming external traffic. This enhances security while providing necessary external connectivity. Next question. Which of the following best describes elasticity in cloud computing? Is it the ability to scale resources up or down automatically based on demand? Is it hosting multiple customer environments on shared hardware? Is it assigning static resources to meet projected workloads? Or is it connecting on-premises networks to cloud environments? And the correct answer is, it is the ability to scale resources up or down automatically based on demand. So elasticity, this refers to the capability of a cloud system to automatically adjust resources up or down to meet changes in workload demand, ensuring efficiency and cost savings. And our final question, what is the key difference between infrastructure as a service and platform as a service? Is it infrastructure as a service provides managed software solutions while platform offers unmanaged hardware? Is it infrastructure provides virtualized hardware resources while platform includes tools and frameworks for application development? Is it infrastructure includes email and collaboration software while platform offers storage solutions? Or is it infrastructure scales automatically while platform requires manual scaling? And the correct answer is, infrastructure as a service provides virtualized hardware resources while platform as a service includes tools and frameworks for application development. So infrastructure as a service, it offers virtualized computing resources such as servers, storage, and networking. In contrast, platform as a service provides a platform with tools and frameworks for application development and deployment, abstracting much of the underlying infrastructure. Networking. This is the backbone of today's connected world. And understanding common ports, protocols, and services is essential for anyone pursuing the CompTIA Network Plus certification or a career in IT. And in this video, we're going to dive into the intricacies of these topics that are aligned with the exam objective 1.4. All right, so let's talk about some common networking ports and protocols. So, ports and protocols, they facilitate communication between devices on the network. So, here's a breakdown of the most common ones that you need to know. The first is that of file transfer protocol, and this operates on ports 20 and 21. And FTP, this is used to transfer files between a client and a server. Port 20 is for data transfer, while port 21 handles control commands. And it's widely used, but it lacks encryption, making it less secure for sensitive data. Then we have what is called SFTP, or Secure File Transfer Protocol, and this operates on port 22. And this is a secure alternative to FTP, and it operates over the Secure Shell Protocol, encrypting both commands and data to ensure secure file transfers. And then we have Secure Shell, or SSH, and this operates on port 22. And SSH enables secure remote access to devices, and it encrypts all communications, making it ideal for managing servers and network devices securely. Then we have Telnet, and this operates on port 23. And this is an older protocol for remote access. Now, unlike SSH, it lacks encryption, exposing communication to potential interception. Then we have what is called TFTP, or Trivial File Transfer Protocol, and this operates on port 69. And this is a simplified file transfer protocol often used for transferring configuration files to network devices. It is lightweight, but however, it does lack security. The next protocol is SMTP, or Simple Mail Transfer Protocol, and this operates on port 25. And this is used for sending email. While it is widely implemented, it is often paired with secure alternatives like SMTPS, which operate on port 587 to protect email traffic. Then we have the Hypertext Transfer Protocol, HTTP, and this operates on port 80. And this facilitates communication between web servers and web browsers, and it is used for loading web pages, but it is not encrypted. Then we have HTTPS, and this operates on port 443. This is the secure version of HTTP, where it encrypts web traffic to protect sensitive information like login credentials and payment data. Next, we have the domain name system, or DNS, and this operates on port 53. And this translates human readable domain names into IP addresses, and it is a critical service for accessing websites and other online resources. Then we have DHCP, or the Dynamic Host Configuration Protocol. This operates on ports 67 and 68, and this dynamically assigns IP addresses to devices on the network, simplifying network configuration and management. And then we have LDAP, or the Lightweight Directory Access Protocol, and this operates on port 389. And this is used to access and manage directory services such as user accounts and network resources. And then we have the Lightweight Directory Access Protocol over SSL, or LDAP-S, and this uses port 636. And this is the secure version of LDAP, where it encrypts the traffic with SSL and TLS. All right, so moving on, we have the Network Time Protocol, and this operates on port 123, and this synchronizes clocks on network devices, ensuring accurate timestamps for logs and scheduled tasks. Then we have SNMP, or the Simple Network Management Protocol. This uses port 161 and 162, and this is used for monitoring and managing network devices. Port 161 is used for queries, while port 162, this is used for receiving alerts or traps. And then we have syslog, and this uses port 514. And this is used for logging system messages and events, and it is essential for monitoring and troubleshooting network issues. Next, we have SMB, or Server Message Block, and this uses port 445. And this facilitates file and printer sharing in Windows-based networks, and it is integral to many enterprise environments. Then we have the SQL Server, and this uses port 1433. And this port is used for communication between applications and Microsoft SQL Server databases. Then we have RDP, or Remote Desktop Protocol. This uses port 3389, and this allows remote control of Windows devices, and it is commonly used for remote work, but requires secure configurations to prevent unauthorized access. And then we have SIP, or the Session Initiation Protocol. This uses ports 5060 and 5061, and this establishes and manages voice and video communication sessions, which are commonly used in voice over IP solutions. All right, so next let's talk about some internet protocol types. So protocols like TCP and UDP, they rely on internet protocol to deliver data. So we're going to explore some common IP types and their functions. So the first one is the Internet Control Message Protocol, or ICMP, and this is used for error reporting and diagnostics, such as the ping command, and it helps identify network connectivity issues but doesn't carry data payloads. Next is the Transmission Control Protocol, or TCP, and this ensures reliable data delivery through error checking, acknowledgement, and retransmission. And it is used by protocols like HTTP, FTP, and SMTP. There's UDP, or the User Datagram Protocol, and this is a lightweight connectionless protocol. It's faster than TCP, but doesn't guarantee delivery, and its common use cases include DNS queries and streaming media. You have GRE, or the Generic Routing Encapsulation, and this is a tunneling protocol that encapsulates packets for transport across networks, and it is often used with VPNs. And then we have what is called IPsec, or Internet Protocol Security. And this secures IP communications by encrypting and authenticating packets. And it has two main components. The first part is called the authentication header, and this ensures data integrity and authentication. Then there's ESP, or Encapsulating Security Payload, and this encrypts packet payloads for confidentiality. Then there's another part which is called IKE, or the Internet Key Exchange, and this manages security associations and encryption keys. All right, so let's move on and talk about traffic types. So traffic types, this defines how data is delivered across a network. And the first type of traffic is called unicast. So unicast traffic is sent from one device to a single destination. And this is the most common type of traffic in networks. Then we have what is called multicast. So multicast traffic, this is sent from one device to multiple recipients in a specific group. And it's efficient for applications like video conferencing and streaming. Then we have what is called anycast. And anycast, this routes traffic to the nearest device in a group of potential recipients, and it is often used in content delivery networks to improve performance. And then we have what is called broadcast. So broadcast traffic, this is sent from one device to all devices on a network segment. Now, while this is useful for tasks like ARP requests, excessive broadcasting, this can cause network congestion. All right, so let's move on and talk about some practical applications of ports, protocols, and traffic types. So understanding how these components work together is essential for troubleshooting and optimizing networks. So here are a few scenarios that we can talk about. So there's troubleshooting DNS issues. So you would use tools like NSLookup or DIG to ensure DNS queries are resolving correctly. Because a misconfigured DNS, this can disrupt services that are dependent on domain names. Then there's optimizing DHCP. So you want to ensure that the DHCP scope is properly configured to avoid IP address conflicts, and you want to monitor lease times to balance efficiency and availability. Then there's securing file transfers. So you want to replace FTP with SFTP or FTPS to encrypt data and prevent interception. And then there's improving VoIP quality. So you want to optimize SIP configurations and prioritize UDP traffic for seamless voice communication. All right, so to wrap this lesson up, here are some key takeaways for those of y'all who plan on taking this exam. First thing you want to do, you want to memorize the key ports and protocols so you can pass this exam. Then you want to understand the differences between TCP and UDP. Next, you want to learn how traffic types impact network performance. Then you want to familiarize yourself with security protocols like IPsec, and then you want to practice using tools to diagnose and resolve network issues. Now, by mastering these concepts, you will be well prepared to tackle the CompTIA Network Plus exam and excel in real-world networking scenarios. All right, so let's move on and get to our favorite part of the segment, the check on learning. So the first question is, which port is used by HTTPS to secure communication over the internet? Is it port 80, port 443, 53, or 389? And the correct answer is port 443. So HTTPS, or Hypertext Transfer Protocol Secure, this uses port 443 to encrypt communication between the client and server, where it ensures confidentiality and security. Port 80, this is used for unencrypted HTTP traffic. Next question, which protocol and port combination is used for remote access using a secure connection? Would it be Telnet on port 23, SSH on port 22, RDP on port 3389, or FTP on port 21? And the correct answer is SSH on port 22. So secure shell, this is a protocol used for secure remote access and file transfers. It operates on port 22 and encrypts data to ensure confidentiality and integrity. Telnet, this is unsecure, and RDP on port 3389. This is specific to remote desktop connections only. And our final question, which of the following traffic types sends a message to all devices within a network segment? Is it unicast, multicast, broadcast, or anycast? And the correct answer is broadcast. So broadcast traffic, this is sent to all devices in a network segment. So for example, DHCP Discover messages are sent as broadcast. Unicast is traffic that is sent to a single recipient. Multicast is sent to a specific group. And anycast delivers traffic to the nearest node in a group. Transmission media and transceivers, they are essential components of network infrastructure where they ensure reliable communication across different environments. And in this video, we're going to talk about the key concepts that are outlined in Objective 1.5, where we are comparing and contrasting the various types of transmission media and transceivers. All right, so let's start off with our 802.11 standards. So the 802.11 standards, they govern wireless local area network communication, and they define the specifications for different Wi-Fi technologies. So we have 802.11a, and this operates in the 5 gigahertz band with the maximum theoretical throughput of 54 megabits per second, and it is less prone to interference but has a shorter range compared to 2.4 gigahertz standards. Then we have 802.11b. This operates in the 2.4 gigahertz band and supports up to 11 megabits per second. It has a better range, but is more susceptible to interference from other devices. You got 802.11g. This combines the benefits of 802.11a and b, operating in the 2.4 gigahertz band, and it has a maximum speed of 54 megabits per second. You have 802.11n. This supports both 2.4 and 5 gigahertz bands, and it introduces MIMO, which stands for multiple input, multiple output technology, where it achieves speeds up to 600 megabits per second. Then we have 802.11ac. This focuses on the 5 gigahertz band, providing gigabit speeds by utilizing wider channels and advanced MIMO technology. And then we have 802.11ax, which is also known as Wi-Fi 6. And this enhances performance in dense environments with OFDMA, which stands for orthogonal frequency division multiple access, and multi-user MIMO, where it achieves speeds over 8 gigabits per second. And on your screen right here, here is a handy dandy little chart that you can use to help you memorize all of these 802.11 standards. So take advantage of that. All right, so let's move on to our next wireless transmission media, and we're going to talk about cellular communication. So cellular communication, this enables mobile connectivity through various generations of technology. We have 3G, and this offers speeds up to 2 megabits per second, and it is suitable for basic internet usage and voice calls. You have 4G LTE, and this provides speeds up to 100 megabits per second with improved latency, supporting high-quality video streaming and mobile applications. Then we have 5G, and this is the latest generation where it offers speeds up to 10 gigabits per second with ultra-low latency and high device density, and it also enables IoT and smart city applications. And then we have satellite communication. So satellite communication provides internet connectivity in remote areas where wired or cellular networks are unavailable. Now, although it offers wide coverage, it suffers from high latency due to the long distance signals that must travel to and from satellites. All right, next let's talk about our wired transmission media. And we're going to start off with the 802.3 standards. So the 802.3 standards, they define Ethernet technologies, which are widely used in wired networks. So the first one we have is called 802.3AF, and this is the power over Ethernet standard that delivers up to 15.4 watts of power over Ethernet cables. We have the 802.3AT. This is also known as PoE+, and it supports up to 25.5 watts of power. And then we have the 802.3BT, and this extends PoE capabilities, providing up to 100 watts of power for devices like cameras and wireless access points. Next, we have single mode versus multi-mode fiber. So fiber optic cables, they transmit data using light where they offer high speeds over long distances. And there are two main types. The first one is single mode fiber, and this uses a small core in a single light path, which enables transmission over long distances of up to 40 kilometers or more. And this is ideal for wide area networks and telecommunications. And then we have multi-mode fiber, and this has a larger core and multiple light paths, which are suitable for shorter distances up to 2 kilometers. And this is commonly used in local area networks and data centers. Next, we have what is called the direct attached copper cable, and this uses copper conductors for short distance connections, and this is typically within racks and data centers, and these cables offer low latency and high availability. And then we have what is called a twin axial cable, and this is a type of direct attached copper cable to where they are often used for high-speed Ethernet and storage connections such as 10G base-CR and 40G base-CR4 standards. Another wired transmission media is that of your standard coaxial cable, and this features a central conductor that is surrounded by insulation, shielding, and an outer jacket. They are commonly used for cable TV, broadband internet connections, and legacy Ethernet networks. You have your various cable speeds. So wired transmission media, they offer varying speeds depending on the type of cable and technology. So you have Cat5e, and this supports speeds up to 1 gigabit per second. Cat6, this offers speeds up to 10 gigabits per second over short distances. Cat6a, this extends 10 gigabit per second support up to 100 meters. Then you have fiber optics, where this provides speeds up to 100 gigabits per second and beyond. Next, we have plenum versus non-plenum cable. So plenum cable, this is designed for use in air handling spaces. And plenum cables, they have fire-resistant jackets to reduce smoke and toxic fumes in case of a fire. And then you have non-plenum cable, where they lack the fire-resistant properties of plenum cables, and they are used in areas where fire safety regulations are less strict. All right, so let's move on and talk about transceivers. And first, we're going to talk about protocol support. So transceivers, they convert electrical signals to optical signals and vice versa, supporting various protocols such as Ethernet, which is widely used for local area networks. And the transceivers, they support speeds from 1 gigabit per second to 400 gigabits per second. And then you have what is called the fiber channel. And this is designed for high-speed storage area networks where they support speeds up to 128 gigabits per second. And yes, the spelling of fiber, F-I-B-R-E, that is spelled the correct way. All right, so let's quickly talk about some transceiver form factors. So transceivers, they come in different form factors, providing flexibility for network devices. You have what is called a SFP, or a small form factor pluggable. This is compact and hot swappable, and the SFP transceivers, they support speeds up to 10 gigabits per second. And then you have what is called the QSFP, or the quad SFP, and this is a larger variant of SFP. And the QSFP transceiver, this supports higher speeds, including 40 gigabit per second and 100 gigabits per second. All right, so let's move on to talk about some common connector types, and we have fiber optic connectors. So the first one is called the SC connector, or the subscriber connector, and this features a square-shaped design, and this is commonly used in data centers. Then you have what is called the LC, or the local connector, and this is a smaller connector with a latch mechanism that is ideal for high-density installations. Then you have the ST, or the straight tip, and this is a bayonet-style connector that is often used in legacy networks. And then we have what is called the MPO, or the multi-fiber push-on, and this supports multiple fiber strands in a single connector, and they are commonly used in high-speed data centers. The next connector types are your copper connectors, and the first one is your RJ11, or your registered jack 11, and this is a 4 to 6 pin connector that is used for telephone and DSL connections. Then we have your RJ45. This is an 8-pin connector that is used for Ethernet and network connections. You have your F-type connector, and this is a screw-on connector that is used for coaxial cables and cable TV and internet applications. And then you have your BNC, and this is a quick connect disconnect coaxial cable connector that is used in video and radio frequency applications. All right, so to wrap this lesson up, Understanding the differences among transmission media, transceivers, and connectors. This is crucial for designing and maintaining efficient networks. So whether you're dealing with wired or wireless technologies, the choice of components, this does impact performance, reliability, and scalability. And this knowledge not only aligns with the CompTIA Network Plus objectives, but also prepares IT professionals to make informed decisions in real-world scenarios. All right, so with that being said, let's do some check on learning. So the first question is, which of the following transmission media is best suited for long distance, high speed data communication with minimal signal loss? Would this be a coaxial cable, a multi-mode fiber, a single mode fiber, or a direct attach copper cable? And the correct answer is it is single mode fiber. So single mode fiber, this is designed for long distance communication and offers minimal signal loss compared to multi-mode fiber or copper-based cables. Its narrow core allows the transmission of a single light mode, reducing dispersion and enabling higher speeds over long distances. Next question. What type of connector is commonly used with coaxial cable for television and internet service? Would this be an SC connector, the F-type, the RJ45, or the ST connector? And the correct answer is the F-type connector. So the F-type connector, this is a threaded connector that is commonly used with coaxial cables in television and internet services, and it ensures a secure connection with minimal signal loss. And our final question, which of the following transceiver form factors supports higher data rates and is commonly used in data center applications? Would this be a small form factor pluggable? Would this be a registered Jack 45? Would this be a BNC connector? Or would this be a quad small form factor pluggable? And the correct answer is this will be a QSFP. So QSFP transceivers, they support higher data rates. They are typically used for high-speed networking in data centers. And QSFPs, they can handle multiple channels of data, making them ideal for applications requiring higher bandwidth, such as 40 gigabits per second or 100 gigabit per second networks. Network topologies, architectures, and types, they play a crucial role in designing efficient and scalable network infrastructures. And understanding these concepts, this is essential for IT professionals seeking the CompTIA Network Plus certification. So in this video, we're going to cover the various network topologies, architectural models, and traffic flow considerations to help you grasp the key concepts that are required for this exam. All right, so let's start off with our network topologies. And the first one we're going to talk about is a mesh topology. So a mesh topology, this is a highly resilient and fault tolerant network structure where devices are interconnected, where they create multiple paths for data to travel. And within that, you have what is called a full mesh. And this is where every node is connected to every other node, ensuring redundancy and failover capabilities. And then you have what is called a partial mesh. And this is where some nodes are interconnected while others have limited connections. And here are the pros and cons. So the pros are mesh topologies offer high redundancy and reliability, improve fault tolerance, and optimal performance with multiple data paths. Its cons, they're expensive to implement due to extensive cabling and configuration, and they can be complex to maintain and manage. And some of the use cases for a mesh topology are large enterprise networks and critical infrastructure like banking, government, and healthcare systems. Next, we have what is called a hybrid topology, and this combines two or more different network topologies to achieve better scalability, performance, and fault tolerance. Its pros, they are flexible and scalable. They allow organizations to mix different topologies based on their needs, and they offer redundant paths to improve network reliability. Its cons, they are complex in design and troubleshooting, and they come with higher costs due to mixed infrastructure requirements. And some of the use cases are large enterprises with diverse networking needs and data centers that are integrating multiple network designs. Next, we have what is called the star or the hub and spoke topology. So in the star topology, all devices connect to a central hub or switch, which manages traffic between nodes. A hub and spoke topology, this is a variation where a central hub connects multiple branch locations, which is often seen in wide area network environments. And the pros, they are simple to deploy and manage. It's easy troubleshooting and fault isolation, and they are scalable by adding more nodes to the hub. The cons, the central hub, this is is the single point of failure, and performance degradation comes along with high traffic loads. In some of the use cases, they are used in small to medium-sized business networks, and they're used in wide area networks using VPNs or MPLS connections. The next type of topology is called a spine and leaf topology, and this is a modern data center design where every leaf switch connects to multiple spine switches. In the pros, it's low latency and high bandwidth. It supports horizontal scaling, and it offers efficient traffic handling, especially with east and west traffic. Its cons, it requires more switches and it increases the cost, and it can be complex to set up. And the use cases, you'll find these in cloud data centers and other high performance computing environments. Then we have what is called a point-to-point topology, and this connects two devices directly, providing a dedicated communication channel. The pros, they are simple and efficient for direct communication, and they are secure and they have low latency connections. The cons, they offer limited scalability, and a failure in the link, this can disrupt the entire communication. In the use cases, you'll find this in wide area network connections between remote offices and also with direct links between routers or servers. All right, so let's move on and talk about network architectures, and we're going to start with the three-tier hierarchical model. So the three-tier hierarchical model, this is a structured approach for designing scalable and manageable networks, and it consists of three layers. The first layer is the core layer, and this is the backbone of the network, and it provides high-speed connectivity between distribution layers, and it is designed for fast packet switching and minimal processing. Then you have what is called the distribution layer. This interconnects the access layer to the core layer. It implements routing, quality of service, and access control policies, and it also aggregates traffic from multiple access switches. And then you have what is called the access layer, and this directly connects end devices like PCs and printers. It also provides security features like port security and VLAN segmentation, and it is also the first point of entry for network devices. And the pros of a three-tier hierarchical model are as follows. So they are an organized structure that allows for scalability. They simplify network management and troubleshooting, and they enable traffic segmentation for security and efficiency. Its cons, they can introduce latency due to multiple layers of processing, and they are more costly due to the requirement of multiple network devices. In the use cases, you can find this in large enterprises with high user density and also networks that require strong policy enforcement and segmentation. Our next architecture is called a collapsed core architecture, and this is a simplified version of the three-tier model where the core and distribution layers are combined into a single layer. And the pros, this reduces network complexity and cost. It's easier to manage in small to medium-sized businesses. The cons, they may not scale well for large environments, and they offer reduced redundancy compared to the full three-tier model. In the use cases, you'll find these in small to medium-sized businesses and also branch offices with moderate networking needs. All right, so let's move on and talk about traffic flows. So understanding traffic flows in the network, this is crucial for optimizing performance and security. And the first type of traffic flow is called the north-south traffic. So north-south traffic, this refers to data that moves in and out of the data center or the network, typically between end users and external services. And examples of this could be a user that's accessing a website that's hosted in a data center, or this could be traffic between on-premises clients and cloud services. Then we have what is called east-west traffic, and this refers to communication between devices within the same data center or network segment. And examples of this could be server-to-server communication within a data center or virtual machine interactions in cloud environments. Now, exactly why does all this matter? Well, security. So north and south traffic, this is monitored more aggressively with firewalls and intrusion detection systems, while east-west traffic, this often requires micro-segmentation. And then there's performance. So data centers, they prioritize low latency paths for east-west traffic since server-to-server communication needs high-speed data transfers. All right, so to wrap all this up, understanding different network topologies, architectures, and traffic flows, once again, this is essential for designing robust networks that meet the demands of modern businesses. So you have mesh, star, hybrid, and point-to-point topologies where they offer various benefits depending on scalability, fault tolerance, and performance needs. They have three-tier hierarchical and collapsed core architectures that help structure networks for efficiency and manageability. You have north-south and east-west traffic flows that impact network performance and security considerations. So by mastering these concepts, IT professionals, they will be better prepared for the CompTIA Network Plus exam and capable of designing, managing, and troubleshooting network infrastructures effectively. Now, with all that being said, let's do some check on learning. So the first question is, which of the following best describes the key feature of a mesh topology in networking? Would this be devices connect directly to a single central hub? Would this be devices form a linear chain with each device connecting to the next? Would this be traffic flows in a north-south pattern only? Or would this be all devices are connected to every other device for redundancy? And the correct answer is all devices are connected to every other device for redundancy. So a mesh topology connects all devices to each other, ensuring redundancy and fault tolerance. And this setup is common in environments where high availability is required, as failure of one link does not disrupt communication between devices. Next question. In a spine and leaf architecture, traffic flows between which two layers? Would this be access and distribution, spine and core, spine and leaf, or distribution and access? Well, of course, the answer is going to be spine and leaf. So in a spine and leaf architecture, the spine represents the core network switches, while the leaf connects endpoints like servers and devices. And traffic flows between spine and leaf switches, offering predictable performance and low latency, particularly useful in data centers. And then our final question is, which topology or architecture is most commonly associated with north-south traffic flows? Would this be a star topology, mesh topology, three-tier hierarchical model, or a spine and leaf topology? And the correct answer is this will be a three-tier hierarchical model. So the three-tier hierarchical model, which is the core, distribution, and access layers, this is typically associated with north-south traffic flows where data moves between clients and servers or from external networks to internal resources. This contrasts with east-west traffic, which is common in spine and leaf architectures where communication happens between devices within the same data center or network. All right, so in this video, we're going to be talking about IP version 4 addressing, its address structure, public versus private IP addressing, loopback and local host IPs, and a PIPA addressing. All right, so let's start off with talking about IP version 4 addressing. So although IP version 6 is increasingly being adopted in corporate networks, IP version 4 is by far the most popular layer 3 addressing scheme in today's networks. And for brevity in this video, the term IP version 4 address is going to be used interchangeably with the more generic term IP address. Now, devices on an IP version 4 network, they use unique IP addresses to communicate with each other. And metaphorically, you can relate this to sending a letter through the postal service. So you place a destination address on an envelope containing the letter, and in the upper left corner of the envelope, you place your return address. Similarly, when an IP version 4 network device sends data on a network, it places both a destination IP address and a source IP address in the packet's IP version 4 header. All right, so let's move on and talk about the IP version 4 address structure. So an IP version 4 address, this is a 32-bit address. However, rather than writing out each individual bit value, you would write the address in what is called dotted decimal notation. So consider the IP address 192.168.1.45. Notice that this IP address is divided into 4 separate numbers separated by periods. And each number represents 1/4 of the IP address. Specifically, each number represents an 8-bit portion of the 32 bits in the address. Because each of these 4 divisions of an IP address represents 8 bits, these divisions are called octets. So for example, as you can see in this picture right here, you have the binary representation of 192.168.145 down here at the bottom. All right, so let's move on and talk about public versus private IP addressing. So a public IP address, which is also known as an external IP address, this is assigned to every device that connects to the internet and each IP address is unique. This addressing scheme makes it possible for the devices to find each other online and exchange information. And the user, they have no control over the public IP address that is assigned to the device. The public IP address is assigned to the device by the ISP or the internet service provider as soon as the device is connected to the internet. And also a public IP address, this can be static, dynamic, or it can even be shared. In IP networking, a private network, this is a computer network that uses private IP address space. And these addresses are commonly used for local area networks and residential, office, and enterprise environments to allow for devices to communicate with each other on the same network. And private network addresses are not allocated to any specific organization, and anyone may use these addresses without approval from regional or local internet registries. Now, an IP address is considered private if the IP number falls within one of the IP address ranges that are reserved for private networks, such as a local area network. And the IANA, or the Internet Assigned Numbers Authority, they have reserved the following 3 blocks of the IP address space for private networks or local networks. So in order to communicate with the outside world, these IP addresses must be translated to a public IP address using what is called Network Address Translation, or NAT. And as you can see here on your screen, you have 10.0.0.0 all the way through 10.255.255.255. And within that IP address range, you can get upwards of 16.7 million IP addresses. Then the next one, starting with 172, you can get upwards of 1 million IP addresses. And then the one that's starting with 192, you can get a grand total of 65,536 IP addresses within that IP range. All right, so let's quickly talk about loopback and local hosts. So the loopback address, which is 127.0.0.1, this is a special IP version 4 address used for testing and troubleshooting network software. It allows a device to send traffic to itself without requiring a physical network connection. And this is commonly referred to as a local host. All right, so let's move on and talk about a PIPA, or automatic private IP addressing. So if a router does not have enough IP addresses for the devices that need to connect to it, a PIPA IP addresses are assigned. And a PIPA IP addresses range from 169.254.0.0 all the way through 169.254.255.255. But a PIPA IP addresses are assigned to devices arriving after the pool of addresses are used up. And once again, a PIPA, this stands for automatic private IP addressing, which is a feature in Windows-based operating systems that enables computers to automatically self-configure an IP address and subnet mask when their DHCP server isn't reachable. And the PIPA service checks regularly for the presence of the DHCP server every 3 minutes. If it detects a DHCP server on the network, the DHCP server will replace the PIPA networking address with dynamically assigned addresses. So exactly what is the purpose of a PIPA? So a PIPA, it was designed as a solution for quickly setting up a localized network without the need to configure a DHCP server or the need to statically assign IP address information. However, there remains a need for devices on this localized network to perform name resolution and discover network services. Now, fortunately, these needs are covered by what is called zero configuration. And zero configuration, this is a technology supported on most modern operating systems, and it performs 3 basic functions. The first is called assigning linked local IP addresses. So a linked local IP address, this is a non-routable IP address usable only on a local subnet. A PIPA, this is an example of a technology that assigns linked local IP addresses. The next function it does is resolving computer names to IP addresses. So multicast domain name systems, this is an example of a technology that can resolve computer names to their corresponding IP addresses on a local subnet without the aid of a DNS server or a WINS server. And then the third thing it does is locate network services. So examples of service discovery protocols include standards-based service location protocol, Microsoft's simple service discovery protocol, and Apple's DNS-based service discovery. Now, if devices supporting these 3 zero configuration features are interconnected on a local subnet, they can dynamically obtain linked local IP addresses, resolve one another's names to IP addresses, and discover services that are available on a network. All right, so that was a lot of information. So let's go ahead and do a check on learning exercise real quick. So the first question is, which of the following IP version 4 address ranges is reserved for private networks? Would it be 169.254.0.0? Would it be 192.0.2.0? Would it be 172.16.0.0? Or would it be 224.0.0.0? And the correct answer is it'll be 172.16.0.0 through 172.31.255.255. So private IP addresses, they are assigned for use within private networks such as local area networks, and the Internet Assigned Numbers Authority. They reserve 3 address ranges for private use. In choice A, that is an APIPA range that is used when a DHCP server is unavailable. Choice B, that is a reserved block for documentation and testing. And choice D, that is for multicast addressing. Next question. What is the primary function of the IP version for loopback address 127.0.0.1? Is it to assign an IP address when a DHCP server is unavailable? Is it to allow a device to send network traffic to itself for testing? Is it to provide access to a private network? Or is it to translate private IP addresses to public IP addresses? And the correct answer is it is to allow a device to send network traffic to itself for testing. So the loopback address is used for testing and troubleshooting network software. When a device sends data to this address, it effectively communicates with itself, making it useful for testing network stack functionality without requiring a network connection. And our final question. A computer on a network receives an IP address in the range of 169.254.0.0 through 169.254.255.255. What does this indicate? Is it the computer has successfully obtained an IP address from the DHCP server? Is it the computer is using a private IP address? Is it the computer has been assigned in a PIPA due to DHCP failure? Or is it the computer is using an IP address for multicast communication? And the correct answer is the computer has been assigned in a PIPA due to DHCP failure. So when a computer is configured to obtain an IP address automatically but cannot reach a DHCP server, it assigns itself an address in the range of 169.254.0.0 through 169.254.255.255. Now, this allows for local communication, but it prevents access to external networks such as the internet. In this video, I'm going to show you guys how to convert decimal numbers into binary, binary into hexadecimal, hex into binary, and binary back into decimal so that you can look like a superstar out on these streets with these conversions. So let's get into it. First thing we need to understand, ladies and gentlemen, is what is decimal, what is hexadecimal, and what is binary. So all of you out there, you all know what decimal is. This is the base 10 numbering system that you guys learn how to count your fingers and toes when you were in preschool. And that is numbers 0 through 9, 0 through 9 or 1 through 10, but we refer to it as 0 through 9 over here in the IT world. Next, we have hexadecimal. Hexadecimal represents base 16 values, base 16 numbers, right? And how this works is you have the same numbers 0 through 9 over here, but then when you get to the number 10, instead of it becoming the number 10, it is represented by the letter A all the way through the letter F, which stands for 15. So A through F, A, B, C, D, E, F, all of those letters represents numbers 10, 11, 12, 13, 14, and 15, okay? And then we have binary. This is powers of 2 or base 2 mathematics. And this represents zeros and ones, which stand for off and on. So in binary, what happens is we're going to take what is called an IP version 4 address. You guys have seen these before. It'll be some number here, dot some number here, dot some number there, dot some number there. That represents an IP address. And if you guys aren't familiar with IP addresses, go check out my IT Fundamentals course where I explain all of this to you. But a lot of you guys are familiar with IP addresses. You're just familiar with the names that are associated with them. Like if you type in youtube.com, or youtube.com is associated with an actual IP address. So think of the IP address as the house number to the house that you currently live in. Okay. Now, how binary relates to the IP version 4 that we're looking at here, we're only going to be focusing on what is called the fourth octet. This is octet 1, octet 2, octet 3, and octet 4. We're going to be focusing on the fourth octet so that we can try to figure out which bits to turn on and off, zeros and ones. And so first things first, we have to lay out the binary numbering system. So it goes like this. It goes from number 1, 2, 4, 8, 16, 32, 64, 128. This red decimal point represents the break in the fourth octet, and we're going on to the third octet. But as you can see, all of these values double themselves by a power of 2, and it just keeps going on and on and on. So we got to get this down packed first, because this is what is going to help us go through our conversion process, right? And how the actual conversion process works is, if you want to go from decimal to hexadecimal, you're going to have to use binary as the middleman. If you want to go from hex back to decimal, you're going to have to use binary as the middleman. So I'm going to show you guys how to do this. It's really simple. Don't sweat it. You'll be doing this like a boss by the time I'm done with this video. All right, so let's do our first example of how to convert decimal to binary. So in this example, we're going to convert the decimal number 175 into its binary equivalent. So the first thing that you're going to want to do is you're going to want to lay out all of your powers of 2s like I just showed you, from the fourth octet, numbers 1, 2, 4, 8, 16, 32, 64, and 128. And now we're going to turn on the values that actually add up to the number 175. Because if you recall, I just stated in binary, we work off of ones and zeros. Ones represents a value or a bit is turned on, and 0 represents a value or a bit is turned off. So in order for us to get 175, we have to turn on the number 128, the number 32, the number 8, 4, 2, and 1. You add all those numbers up together, you get 175. Real simple stuff, right? I know. All right, let's take this problem one step further. So we're going to go ahead and convert the decimal number 175 into its hexadecimal equivalent. Now, if you recall, I stated that in order to go from decimal to hexadecimal, or from hex back to decimal, you have to go through binary as the middle guy. All right, so now let me go ahead and explain what all this madness on your screen means, okay? So we have the decimal number 175, and we've already figured out how to solve for its binary equivalent, and that will come out to be 1010111. Now, remember, I stated that this was basically the fourth octet, right? The last octet of an IP address. I have this blue line right here going down the middle, because when we go through the process of converting it into hexadecimal, we're only going to be focusing on what is called a nibble, an N-I-B-B-L-E. This is basically half an octet that we're going to use for our conversions, okay? So we got our binary 1010111. We're going to move it down here. Now, we're going to break this down into two groups of 4s, or two groups of nibbles, right? We're just going to draw a line straight down the middle, just like I did. Being that we're only operating off of half of an octet, we're only going to basically apply half of the powers of 2 conversion. So we have 1111. So basically the values 1, 2, 4, and 8 have all been turned on. And then we're going to apply the same 1, 2, 4, and 8 over here. So as you can see, the value 8 and the value 2 have been turned on. And now we're going to go ahead and just start adding numbers up. 8 plus 2 is what? 10. 8 plus 4 plus 2 plus 1 equals what? 15. So now we have 10 and we have 15. That is what these nibbles break down into. So now we have to go ahead and figure out, what do these values mean as it relates to hexadecimal. So if you look over here, remember I told you hexadecimal numbers, they represent numbers 0 through 9 and letters A through F, where A through F represent numbers 10 through 15. So now that we have the number 10 over here, well, A equals 10. F equals 15. So the decimal number 175 equals the hexadecimal value AF. Now, if you want to go ahead and check your work real quick to verify that you know what you're doing, you can just go to Google and type in decimal to hexadecimal converter, and you just type in the number 175 and it will show you the conversions right here. Here's your hexadecimal value, and here is your binary value that I was showing you earlier on this screen. All right, so now let me give you an example of how to go from hexadecimal all the way back to decimal. So in this example, we have the hexadecimal value of B
2. We're trying to figure out what its decimal equivalent is. So what we're going to do with the B2, we're going to go ahead and convert it to binary, because remember, to go from hex to decimal, you got to go through binary. From decimal to hex, you got to go through binary. So we're going to go ahead and apply our middleman. So what we're going to do, we're going to take our B2 and we're going to divide it into its own little sections here of B and 2. And then we're going to come back over here and figure out what its equivalent is in its nibble notation. So remember, we're working with the number 2. So we got to come down here and do our 1, 2, 4s, and 8s that represent our nibbles so that we can figure out which value is actually turned on. So out of 8, 4, 2, and 1, the only value that is turned on is the value number 2. So that'll be 0, 0, 1, 0. Then we come over here to the letter B. If you look back up here, remember in hexadecimal notation is expressed in numbers 0 through 9 and A through F, where the letter A equals 10 and the letter F equals 15. So B would be the number 11. So 11 equals B. We go here and look at our nibble, 1, 2, 4, and 8. We add the values that are turned on. So it'll be 8, 2, and 1. 8 plus 2 plus 1 equals 11. And then we just put them all together. And this is what our binary equivalent for B2 is going to look like. It's going to be 1, 0, 1, 1, 0, 0, 1, 0. Now we're going to take this and we're going to figure out what our decimal equivalent is. So now we're going to come back to the fourth octet, the entire thing. 1, 2, 4, 8, 16, 32, 64, 128. We're going to take our binary equivalent and figure out which of these values are turned on. As you can see, values 128, 32, 64, and 2 are turned on. We're going to come up here and just add those numbers together. 128 plus 32 plus 16 plus 2, and that will get you 178. So the decimal equivalent of the hexadecimal value B2 is the number 178. And like always, if you're unsure, you can just run over to Google and do a check to verify that you added your numbers up correctly. So as you can see, I put B2 up into the converter. We got our decimal equivalent of 178, and then we have our binary equivalent of 10110010. And for my last trick, ladies and gentlemen, I'm going to show you how to convert a hexadecimal number that has 3 values back into its decimal equivalent. So if we look at our screen here, we have the hexadecimal values A, B, and C. Okay, so first thing we got to do, we got to convert A, B, and C back into its binary equivalent, because binary is the middleman. Also remember, hexadecimal values are the numbers 0 through 9 and the letters A through F, where A equals 10 and F equals 15. So we go through, we take ABC and we break it down into its individual groups. And then we figure out, what do these values represent? Well, A equals 10, B equals 11, and 12 equals C. We go ahead and apply our little nibbles that I was talking about here with 8421, 8421, 8421. We figure out which values are turned on that add up to this number right here. So 8 plus 4 equals 12, 8 plus 2 plus 1 equals 11, 8 plus 2 equals 10. So this is our binary equivalent of ABC, 101010111100. Now we're going to move on down to converting this into its decimal equivalent. So now we're going to apply the entire octet again. So remember, 1, 2, 4, 8, 16, 32, 64, 128. Now if you look right here, I have a little red dot right here that indicates the separation between the fourth octet and the third octet. So this value ABC is going to drag us out into the third octet. So what we're going to do, we're still going to apply the powers of 2. So 128 plus 128 is going to get us 256. 256 plus 256 is going to get us 512, then 1024, 2048, and so on and so forth. So now we're going to take our binary value and just figure out which of these numbers are turned on. As you can see, 2048's on, 512, 128, 32, 16, 8, and 4. Come up here, add up all these numbers together. 2048 plus 512 plus 128 plus 32 plus 16 plus 8 plus 4. That's going to get you the decimal equivalent of 2,748. So the hexadecimal value ABC equals 2748. And like always, you could just run over to Google and check your work if you want. So as you can see, hexadecimal number ABC, decimal value 2748, binary value down below.
In this video, I'm going to be explaining to you what class full IP addressing is. We're going to be talking about subnetting, what a subnet mask is, and then I'm going to explain to you what class list subnetting is. All right, let's talk about classful IP addresses. So classful IP addressing, this is a method that divides the IP address space for IP version 4 into 5 address classes based on the leading 4 address bits. So you got class A, B, and C. They provide unicast addresses for networks of 3 different network sizes. Then you got class D. This is for multicast networking. And the class E address range, this is for future or experimental purposes. And an IP address, this is divided into 2 fields. You got a network prefix, which is your network ID, and then you have your host ID. And what separates the network ID from the host ID depends on whether the address is a class A, B, or C address. And here's what class A, B, C, D, and E look like broken down. So class A, it ranges from 1 to 126, and it supports 16 million hosts on 127 networks. You got class B, it starts off with a number between 128 and 191, and it supports 65,000 hosts on each of 16,000 networks. Then you got class C, that starts off with the IP address of 192 all the way to 223, and this supports 254 hosts on each of 2 million networks. Then you got class D, 224 to 239, and that is reserved for multicast groups. And then you got class E, 240 to 255, and that is reserved for future use or research and development purposes. So let's talk about subnetting. So subnetting, this is the strategy used to partition a single physical network into more than one smaller logical subnetwork or a subnet. Subnetting allows for an organization to subdivide a large network into smaller, more efficient subnetworks to help minimize traffic and increase network speeds. An IP address includes a network segment and a host segment, and subnets are designed by accepting bits from the IP address's host part and using these bits to assign a number of small subnetworks inside the original network. And subnetting allows an organization to add subnetworks without the need to acquire a new network number from an internet service provider. And here are some of the benefits of subnetting. So it reduces the network traffic by reducing the volume of broadcasts. It helps to surpass the constraints in the local area network. So for example, the maximum number of permitted hosts, and it enables users to access a work network from their homes. So there is no need to open the complete network. All right, so let's talk about a subnet mask. So a subnet mask, this is a 32-bit number created by setting network bits to all ones and setting host bits to all zeros. The subnet mask splits the IP addresses into the network and host addresses, thereby defining which part of the IP address belongs to the network and which part belongs to the host. All right, so let's take a look at the subnet mask classes for A, B, C, D, and E. So as you can see here, you got class A, that's 255.0.0.0. The number 255 represents the 8 bits that identifies the network portion of an IP address. And the 3 zeros, which represents 24 bits, they represent the portion that will be assigned to identifying the host. When it comes to class B, the subnet mask will be 255.255.0.0. The first 16 bits are the 255.255. They identify the network portion of an IP address, and the 0.0 are the last 16 bits. They identify the host IPs that could be assigned to devices. And then you got class C, 255.255.255.0. And once again, the first 3 octets are 255.255.255 are those 24 bits. They identify the host, and the remaining octet, which is identified by the 0, those 8 bits identify the IP addresses that can be assigned to devices on that network. So now let's go ahead and put all of this wonderful knowledge together. So once again, class A, if you see an IP address that starts with the number 1 going all the way to the number 126, that is a class A IP address, and they support 16 million hosts, and each of them has 127 networks, and its subnet mask is going to be 255.0.0.0, where the first 8 bits identify the network portion of that IP address, and the last 24 bits, which are all those zeros, they identify the host IDs that can be assigned to devices on that network. Then you got class B. So if you see an IP address that starts with the number 128 all the way through the number 191. It can support 65,000 hosts on each of 16,000 networks. Its subnet mask is going to be 255.255.0.0. The first 16 bits represent the network portion, and the last 16 bits are the 0.0. They represent the host IDs. And then we got class C. So once again, if you see an IP address that starts with the number 192 all the way up to the number 223, that is a class C IP address, and it can support 254 hosts on each of 2 million networks. And it has a subnet mask of 255.255.255.0, with the first 24 bits identifying the network portion of that IP address, and the last octet or the last 8 bits, they identify the host ID for devices that could be assigned to that network. All right, next let's talk about classless subnetting. So earlier in the video, I talked about class-full subnetting, where I explained how to subdivide or subnet an IP version 4 address, which is the strategy that is used to subdivide a large network into smaller, more efficient subnetworks to help minimize traffic and increase network speeds. The problem with class-full subnetting is that you are restricted as to how far you can subdivide a network, because class-full subnetting focuses purely on the overall class an IP address falls up under, which causes an IP address to potentially have millions of available subdivided IP addresses to utilize, which is very inefficient for most networks. Now I'm going to show you how to apply a concept called classless subnetting, which allows for you to more narrowly subdivide a network into more manageable IP addresses that can be used for a sub-network. All right, so the first thing we have to talk about is this concept called CIDR notation. And CIDR, that stands for classless interdomain routing. In CIDR, this is also known as prefix notation or slash notation. And this is a method for allocating IP addresses and for IP routing. CIDR notation was introduced in 1993 to replace the previous classful network addressing architecture on the internet. And its goal was to slow the growth of routing tables on routers across the network and to help slow the rapid exhaustion of IP version 4 addresses. All right, so if you guys have been in my class for a while, you have probably seen this chart once upon a time for me teaching you how to convert from decimal to binary to hexadecimal. So this is our standard binary to decimal conversion chart, where we got binary represented on the left and its decimal equivalent represented on the right. And this is going to help us out when it comes to classless subnetting, which we're going to look at on the next slide. All right, so here's our first example of classless subnetting dealing with a class A IP address. So our IP address is 101.0.0.1. And just like I told you earlier, our subnet mask for this particular IP address will be 255.0.0.0. And as you can see, it's binary equivalent. All the ones in the first octet are turned on to represent 255. And then the last 24 bits are all turned off, which represent 0. In CIDR notation, we would just put a /8 to identify that the first 8 bits have been turned on. That's how simple this is, ladies and gentlemen. All right, here's example 2 of slash notation. We have a class B address, which is identified by 129.0.0.1. And like I told you earlier, our subnet mask for class B will be 255.255.0.0, where the first 16 bits are turned on to identify the network portion of the IP address, and the last 16 bits are turned off, which identify the host bits of that IP address. So when we write this out in CIDR notation, we could just simply write the IP address as 129.0.0.1/16. And the /16 tells us that this is a class B address, and the first 16 bits have been turned on to identify the network portion of this particular IP address. And obviously the last 16 bits are turned off, which identify the host. And next we have a class C address, 193.0.0.1, subnet mask 255.255.255.0. The first 24 bits are turned on, which identify the network portion of that IP address, and the last 8 bits are turned off, and its CIDR notation is going to be a /24. So you would simply write the IP address out as 193.0.0.1/24. And once again, that /24 lets you know that the first 24 bits of that particular IP address represents the network ID, and the last octet represents the host bits of devices that will be assigned to that network. All right, so now let's take a look at some examples that show you different numbers that don't have to deal with 8, 16, and 24. So we got this IP address of 198.0.0.1/14. So basically, when you look at this IP address with the /14, that tells you that the subnet mask is going to be 255.252.0.0. And basically what that means is the first 14 bits have been turned on to indicate that we're going to have 255 and .252 that identify the network portion of this IP address, and the last 18 bits are turned off, which identify the host bits that could be assigned to devices on this IP address. And remember, an IP version 4 address has a maximum of 32 bits. So you add 14 plus 18, that gets you a grand total of 32 bits. And this chart comes into play with helping you quickly figure out what the decimal equivalent is going to be. So you look at, we got 6 ones turned on right here and 2 zeros. You come down to your chart, 6 ones and 2 zeros, that gets you 252. That's how we ended up with a 252 right here, of the first 14 bits being turned on, which will give us 255.252 and obviously .0.0. Let's look at another example. We got IP address 201.1.0.0 with a /21. Its subnet mask is going to be 255.255.248.0, where the first 21 bits are turned on and the last 11 bits are turned off. All right, so let's look at an example where we lead off with the CIDR notation of /27. So we got /27 that tells us the first 27 bits are going to be turned on. So we got 8 bits here, 8 bits here, 8 bits here, and 3 bits here. Add that all up, that's 27 bits. That leaves us 5 bits that are turned off, which identify the host bits. And obviously all these bits turned on right here is 255, 255.255. And then we come down to our chart, find the first 3 ones that are turned on with 5 zeros following after it, and that lets us know that it is a 224. So our subnet mask for this particular / notation will be 255.255.255.224. So let's take a look at one more example with a CIDR notation of a /19. So we have a subnet mask of 255.255.224.0, where the first 19 bits are turned on and the last 13 bits are turned off, which identify the host bits. All right, next let's talk about IP version 6 CIDR notation. So an IP version 6 address is usually distributed by the Internet Assigned Numbers Authority, or the IANA. The IANA is responsible for providing address blocks to the regional internet registries, who then assign smaller blocks of IP version 6 addresses out to your ISPs or your internet service providers. From there, the ISP will then assign you, the end user, with an IP version 6 address that has a /48 subnet, which you can then further subnet down as needed. And as a side note, you want to remember that an IP version 6 address is 128 bits long, whereas consisting of 8 blocks of 16 bits. And remember that the values are hexadecimal numbers and not decimal numbers. All right, so let's look at an example of an IP version 6 address and how it is broken down. So we got IP version 6 address 2500:AAAA:3333:001: a whole bunch of zeros followed by a 1. The global routing prefixes identify the first 48 bits. So these are the first 48 bits right here. Just remember 16 times 3, they get you 48. So remember, the Internet Assigned Numbers Authority, they assign this first block right here, 2500. Your regional internet registries, they assign the second block, and your ISP, who you pay your internet bill to, they assign the third block right here. And like I say, all 3 of these, they make up the global routing prefixes, or the first 48 bits of an IP version 6 address. All right, so working with this same IP address, when we get down to the 4th block, this is locally assigned by the end user. And this is used for creating your network ID. So just like with IP version 4, we use subnet mask to identify which portion of the IP address represents the network ID. Well, in an IP version 6 address, this 4th block identifies the network ID of the network your IP addresses are going to reside on. And it could be a 1, 2, 3, 4, etc. And within this, you got 16 bits, and that'll give you a grand total of 65,536 total subnets you could theoretically create just off of this one block alone. All right, then finally we get down to our last 4 blocks, and these are the host IDs. So just like with the IP version 4 address, you had 255.255.255.0 or 255.0.0.0, whatever combination, right, for A, B, and C. So just like with a class A IP address where I said the subnet mask was 255.0.0.0, and I told you that the subnet mask represents the first octet or the first 8 bits that are turned on, and the remaining 3 octets represents the network IDs that can be assigned to potential devices on that network. Well, in an IP version 6 address, this is what this represents. These last 4 blocks represents the host IDs or IP addresses that can be assigned to various devices within a network. And under this system right here, this would get you approximately 18 million trillion hosts per subnet. So remember, we go back to the last slide when we were dealing with the actual network ID or identifying the subnet. We can get a grand total of 65,536 total subnets. Now, out of those 65,536 total subnets, each of those subnets could potentially host as many as 18 million trillion hosts per subnet. So in case you're wondering why this is, if you go back and check out my IT fundamentals class, I explained in that series that IP version 4 only has a maximum of like 4 billion IP addresses, and we've pretty much exhausted all of them. So in order for us to continue to enjoy the internet where we can surf our iPhones and watch YouTube videos like TechG and order random stuff off Amazon and slide into people's DMs and do all this crazy stuff we like to do, well, we need more IP addresses. And so working with an IP version 6 address where you can have 18 million trillion hosts per subnet, and then you can have a maximum of 65,000 subnets. Well, in theory, we should never, ever run out of IP addresses for at least a couple generations or so. And so continuing on with this slideshow here. So when we want to write this out in CIDR notation, we would just simply put this as a /64. So basically, when you're dealing with IP version 6 addresses, all of its CIDR notations are going to be expressed in a /64. And the /64, this represents the subnet mask options of this IP version 6 address. So we got 4 blocks of zeros right here, which make up 64 bits or 4 blocks times 16. But anyways, the whole point is IP version 6 CIDR notation. If you do the shorthand version, which I taught you guys in the A+ class of how to shorten out an IP version 6 address, but its CIDR notation is always going to be /64. And here is a graphical representation where in this picture we have 5 different networks being depicted in here, all expressed by IP version 6, and all of them have the /64 CIDR notation. All right, so that wraps up my lesson. So let's go ahead and get into some of this wonderful check on learning. So the first question is, which of the following IP address ranges belongs to a Class B network? Would it be 10.0.0.0 through 10.255.255.255? Would it be 128 through 129? Would it be 192.168.0.0 through 192.168.255.255? Or would it be 224.0.0.0 through 239.255.255.255? And the correct answer would be, this would be 128.0.0.0 through 191.255.255.255. So Class B IP addresses range from 128 to 191, and these addresses support 65,000 hosts on each network and are commonly used in medium-sized networks. Option A is for Class A, and option C is for Class C, and option D, this is reserved for multicast purposes. Next question. What subnet mask is used for a Class C network by default? Would it be 255.0.0.0, 255.255.0.0, 255.255.255.0, or 255.255.255.255? And of course, the correct answer would be C. So Class C networks that have a default subnet mask of 255.255.255.0. This means that the first 24 bits represent the network portion, while the last 8 bits are used for hosts. And this allows for 254 usable host addresses in each Class C subnet. And Class A uses 255.000. Class B is 255.255.000. And the last one, 255.255.255.255. This is a special mask used for single host subnets. And our final question, which IP class is reserved for multicast addresses? Would it be Class A, B, C, or D? And the correct answer is this will be a Class D address. So Class D addresses, they range from 224.000 to 239.255.255.255, and they are reserved for multicast networking. Unlike Class A, B, and C, Class D does not have a network and host ID structure because it is not used for traditional unicast addressing. Instead, it is designed for group communication where packets are sent to multiple recipients simultaneously. In this video, I'm going to be explaining to you what a variable length subnet mask is. Also, I'm going to be explaining the concept of a router on a stick. And then I'm going to be showing you how to put together what is called a VLSM chart, which allows for you to basically subnet IP addresses to assign IPs to various devices within a network that you control. So let's get into it.
All right, guys, so we have been learning subnetting for the past 2 or 3 videos in this Networking Plus certification class that I'm putting together. And some of you guys are probably lost and confused and wondering why we're doing this. Well, now I'm going to show you why we are doing this, to show you that these numbers actually mean something other than weird looking numbers written in a chart. So I'm going to show you guys a concept called a router on a stick. This is something that you will learn or apply if you go for your CCNA in the future or whatever the case may be. So the first thing you have is a router. It is represented by this circle with these lines going down the middle. It is connected to a switch, which is represented by this square with arrows going in opposite directions. And then hanging off this switch, you might have a computer over here, a computer over here, a computer over here, and a computer over here. Now, in this example, all these computers can be on the same VLAN, or we can separate them to where these guys will be representing VLAN 2, these guys will be representing VLAN 3, and the switch by default is going to represent VLAN 1. And if you don't know what a VLAN is, it stands for Virtual Local Area Network. Basically, VLANs allow for you to logically divide a switch into separate networks. So VLAN 1, 2, and 3, these would all be 3 separate networks. And in order for a computer over here in VLAN 2 to communicate with a computer over here in VLAN 3, they would have to pass their traffic through the router, come back down, and then they could receive the message. If they were all in the same VLAN, VLAN 1, if this computer wanted to communicate with this computer over here, they would only have to pass traffic through the switch to get to the other device. But being that they have been logically separated onto one physical switch, they have to use a router. Why? Because routers connect networks to networks. So if you're a little lost or confused about that, I advise you to go back and check out some of my earlier videos that explains this concept. So now what we're going to do, we're going to talk about actually subnetting an IP address. So just imagine that this router, this switch, and these computers are all in the Tech G Corporation right now. And within the Tech G Corporation, we have paid for some internet service from Comcast or whoever else is out there, and they said, hey, this right here is your IP address that you are going to use for your network. So basically this IP address is essentially the public IP address for this router that is communicating with the devices owned by Comcast so that I can go out there and live my wildest fantasies surfing the internet. Okay. Now, within this network, I want to go ahead and subdivide this IP address so that I can allocate IPs for this device, this device, this device, this device, and any other device that I want. Now, within this example of the TechG Corporation, I want to have sections. Now, currently TechG doesn't make a lot of money, so all I can afford is a router and a switch, right? But I do have enough money to have a couple different departments. So let's just say that this is my marketing department over here, and this is my HR department over here. And we're all connected to the same switch. And we'll call this switch SW. And this is our router in case you need to see it. Now, I want the people in HR to only be able to access whatever devices are within the HR department. And I want the marketing people to only be able to access devices in the marketing department. So that's why these guys are in VLAN 2. These guys are in VLAN 3. But I also want them both to be able to communicate with the switch VLAN 1 as well. Like I stated earlier, in order for that to happen, you need to go through the router so you can pass traffic back and forth. Now, this IP address right here, 192.16.1.1. This is a Class C address. And if you guys recall, a Class C address is basically a classful IP address, and it ranges from 192 to 223. All right. So basically any IP address between 192.0.1.1 all the way through 223.255.255.254. That is what a Class C IP address is. So now, that is what the ISP has given me. They said, hey, this is your quote unquote street address for your router over here. Now, we all know what routers, if you've been paying attention to my class, you got a public IP address and you got your private IP address. And within the router, they perform this thing called NAT, network address translation, so that basically you can quote unquote disguise all the IP addresses within your network. So when external networks are communicating with your network, the only IP address they see is this one right here. But now within this network, I want to go ahead and subdivide or subnet this network so I can allocate IP addresses to all these random devices over here in their particular VLANs. And the reason I want to do this is because it is going to make it much more easier and manageable to deal with a smaller collection of IP addresses. So we're going to go ahead and subdivide that. So before we get started, what we need to do is this. I need to first determine how many addresses do I actually need. So let's go to our marketing department over here. Let's just say our marketing department, I need 100 IP addresses for marketing. And then for my HR department, I need 50 IP addresses. And then for my switch, I need 6 addresses. And then for my router, I need 2 addresses. And this is my starting IP address right here, which once again is a /24 CIDR notation address or Class C address, right? So now we're going to go ahead and begin the construction of what is called a VLSM chart, or a variable length subnet mask chart. This is what's going to allow for us to get back over here and figure out what IP addresses we can assign to various devices within the network. So like I said earlier, we're going to need 100 IPs for the marketing department. We're going to need 50 IPs for the HR department. Our switch is going to need 6 IPs for whatever reason. And our router is going to need 2 addresses in order to make this thing work. And once again, our starting IP address is 192.16.1.1. That is our starting IP address over here. So let's go ahead and start constructing this chart. So first thing we're going to do, we're going to put what is the name column. Then we're going to have the number of hosts that we're going to need. We're going to need to know our incremental value, also known as our positional value. I'll explain all this as we go along. We're going to need to know our network ID. We're going to need to know our gateway address. We're going to need to know our IP range. And we're going to need to know our broadcast IP address. And we're also going to need to know our custom subnet mask. And in some cases, this is more particular to CCNA, you may need to know this thing called your wildcard mask. But we're not going to worry about the wildcard mask at this present moment. So this is the chart that we are about to build, ladies and gentlemen. Now, before we go ahead and start building this chart, let me go ahead and show you a quick little way on how to go about figuring out how many hosts you may need and what the subnet mask may be and all that wonderful stuff real quick. All right, so here's a little handy dandy chart that you can put together real quick when you're out there taking your Network Plus exam, which is going to help you figure out what the hosts are and the appropriate subnet mask that goes with the host. And all you're going to be doing is using your power of twos chart. So you're going to put 2 to the 0, 2 to the first, 2 squared, 2 cubed, 2 to the fourth, 2 to the fifth, 2 to the sixth, 2 to the 7th. You can drag this thing out, 2 to the 8th, 2 to the 9th, so on and so forth. But this right here represents your 4th octet. So from there, you can calculate how many hosts you're going to need. So 2 to the 0, well, that equals 1. 2 to the first, 2, 4, 8, 16, 32, 64, 128. And then from there, we can go ahead and figure out what our subnet mask is going to be using slash notation. So if you got one host right here, basically that means you're going to have a /32 for your subnet mask. Over here, you're going to have a /31, /30, /29, /28, 27, 26, and /25. That's what your subnet mask is going to be. Now, if you want to know what this actually looks like in binary notation, basically this will look like this. You would just have the first 32 bits turned on, if you recall from my last video. So you have 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8. So that's 24, 25, 26, 27, 28, 29, 30, 31, 32. What is that? 1, 2, 3, 4, 5, 6, 7, 8. All right, so all of them are turned on. I don't know why I didn't just put that together real quick. /31, same deal. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, and a 0. So in the /31, basically you have 31 bits turned on. 1 bit is reserved for the actual host. Over here, you're going to need at least 2 IP addresses that are going to be used for assigning IPs to devices. And I'll explain all that as we go along. But basically, instead of you sitting around here drawing out all of your binary, you can just go ahead and remember this slash notation in conjunction with the host, and that'll help you out and expedite this process a whole lot faster. So now let's get back to our chart over here. So like I stated, this is the IP address that has been assigned to us, 192.16.1.1/24. We need 100 devices that can have IP addresses for our marketing department. We need 50 devices for our HR department that can have IPs. Our switch needs 6 IPs for some weird reason, and our router is going to need 2 IP addresses. Now, when we begin this process, we need to start figuring out how to subdivide this network or subnet this network for the one that has the highest requirements, which will be 100. So we come over here, we put marketing, and we need 100 devices over here, or 100 IPs, I should say. Now we need to figure out how many hosts do we need. So what we're going to do with each of these numbers, 100, 50, and 6, we're going to add the number 3 to all of these numbers. So 100 plus 3 is going to give me 103. 50 plus 3 is going to give me 53, and 6 plus 3 is going to give me 9. And the reason why we're adding 3 is because the 100, that actually represents the actual devices that are going to be assigned IP addresses within this little network that I set up over here. Now we're adding 3 because we also have to take into account for the IP address for the network ID, the gateway IP address, and the broadcast IP address. The network ID, this is basically the identification for this network right here. It's essentially almost the same thing as the main IP address that was assigned to us from the ISP, but now we are acting like our own quote unquote ISP, and we need to first and foremost identify the network that these devices are going to reside on. So that's how we get to the network ID. Then we also have to identify the gateway IP address. And the reason we're doing that, so when we're out here sending messages around, we need to tell these messages what is the gateway IP address that they need to go find in order for them to get out onto the wild internet or communicate with somebody else in another network. And typically your gateway IP address, at least within this setup, is going to be the private IP address associated with this router for this overall network. But within this little tiny network, we're creating a separate gateway IP address, which will be programmed into this router, but we're not going to go too far into that for this video because that's more of a CCNA related topic. But basically, we need that gateway IP address. So when I start pressing ones and zeros and sending messages, these messages know, hey, I need to go find a certain gateway IP address so I can escape my network and go communicate with somebody over here or go talk to the router so I can get out to the greater internet. And then we also need to identify what is called the broadcast IP address. The broadcast IP address is essentially the last IP address before you begin the next network. And then everything in between the gateway and the broadcast is your IP range. This is where you will pull IP addresses from to assign to these 100 devices over here. And then the custom subnet mask, this basically identifies the portion of the network that all of this stuff is going to reside on. So we'll look at my previous videos where we're talking about this and I explain that in greater detail. And the wildcard mask, we're really not going to focus on this for this particular lesson. This is something that you'll need to know when you are going for your CCNA. And I'm just trying to keep this as simple as possible so that we can make sense of why we're doing this in the first place. So like I stated, we got 100 devices that need IP addresses for our marketing department, 50 devices for our HR department, 6 IPs need to be assigned to the switch for whatever reason, and then the router is going to need 2. And with the router, we're going to add another 2 to it, and I'll explain that when we get down to it. So 100 plus the 3. Remember the 3 came from, we need to set up an IP for the network ID, the gateway, and the broadcast. So we need a grand total of 103 IP addresses within this network. Now, what we're going to do next, we're going to figure out what is the positional value or the incremental value for this particular network that we are about to construct. And we come back over to this chart over here to figure that out. So when I was telling you about the hosts, I put 1, 2, 4, 8, 16, 32, 64. Then I drew a line to indicate the break between octet number 4 and octet number 3. And if you were to keep dragging this power twos thing out, you would start this positional spot all over again and just keep going down the line. But basically, these incremental values or these positional values are essentially going to tell me what spot in the octet is going to fulfill my actual host requirements so that I can have enough IP addresses to allocate to my devices. All right. So we come back over here. As I stated, I need 103 IP addresses in total for this particular network. We come back over here to our positional values, incremental values, whatever you want to call them. And we're going to figure out what number does 103 go into without going over. So does 103, does it go into 1? No. 2, no. What does it actually go into? 103 can comfortably fit inside the number 128 without going over. Now, being that we need 103 hosts, that means we're going to be just fitting comfortably inside of the 4th octet, dealing with our positional value of 128. So we're going to come down to our incremental block and we're going to put a 0.128 to indicate that we are operating out of the 4th octet because that is what 103 comfortably fits inside of, ladies and gentlemen. Now we need to figure out what is our network ID. So remember, this is our starting IP address, 192.16.1.1. With this particular network, we're operating out of the 4th octet. So that means we're just going to zero out the last octet. So our network ID for this network is going to be 192.16.1.0. That is the very first IP address for this network, which is part of the extra 3 numbers that I added here. Our gateway address is just going to be one IP address above this one. So that's going to be 192.116.1.1. And then our IP range is going to be one IP greater than the gateway. So it'll be 192.16.1.2. I'm just going to go ahead and put a .2, and we're going to stop right there. Now we're going to go ahead and start trying to figure out our requirements for the HR department that requires 50 hosts. So we come back down here, we identify HR. We said we needed 50, but we're going to add 3 to get 53, because remember, we got to create an IP address for the network ID, the gateway, and the broadcast. And then we're going to go ahead and figure out our incremental value for this particular network. So we come back over here. We said we need 53 IPs. What number does 53 go into without going over? We see it goes into the number 64. And being that we're working out of the 4th octet, our incremental value is going to be 0.64. And now we're going to go ahead and we're going to figure out the network ID. So this is what we're going to do to figure out the network ID for the HR department. We're going to take the network ID of the marketing department and add it to the incremental value. So we're going to take 192.16.1.0 and add it to 0.128. Essentially, we're just going to be adding the 4th octet number. So 128 plus 0 is going to give us our starting network ID for HR department. It's going to be 192.16.1.128. That is our network ID for the HR department. Basically, this is the starting point for this network right here. And then the same thing applies with the gateway. It's going to be 192.16.1.129. Just one IP address greater than the network ID. And then our IP range is going to start off with a .130. Now, we can use this number to go ahead and figure out what is the broadcast number for the marketing department, because like I told you guys, the broadcast IP address is the last IP address before you start the next network. So all we're going to do is just subtract one IP address from the network ID of the HR department, and the broadcast IP address for the marketing department is now going to be 192.16.1.127. And now we can figure out the last IP address of the IP range where we can pull IP addresses from. And in this example, it is going to be a .126. So everything between 192.16.1.2 through 192.16.1.126, this is where we can assign IP addresses to all of the devices within the marketing department. And as you can see, this is a grand total of 124 IP addresses, I believe. That is enough IP addresses to cover our requirements of 100 devices needing IP addresses. Now we can come over here and figure out our custom subnet mask, and that is real simple. All we got to do is just go back and look at our chart up here. We stated that we needed 103 hosts. 103 went into the number 128, and that gives us a /25 IP address. And if you want to write this out in this binary equivalent, it's going to look like this. It's going to be 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, then 7 zeros. 1, 2, 3, 4, 5, 6, 7, 8. Wait, 1, 2, 3, 4, 5, 6, 7, 8. All right, I put too many zeros on it. So that's what it's going to be. When written out in this binary equivalent, your subnet mask is going to be 255.255.255.128. So that is your actual subnet mask, 255.255.255.128. We just shortened it out and put /25. I mean, you can write it out if you want. It doesn't really matter. So there's another way you can figure this out for those of you who like math. So there's an actual formula for this. So basically the custom subnet mask, it equals the number 256 minus the network host. So 256 minus the network host equals the custom subnet mask. So basically you can just do 256 minus our network host, or our incremental value of 128 or 128. So 256 minus 128 is going to give you 128 over here. But since we're working out the 4th octet, it's going to be over here. So those of you who like math, that is a quick little easy formula. Custom subnet mask, 256 minus the network host, or the incremental value, I should say. And then that's going to tell you what your actual values are going to be for your custom subnet mask. Or you can do it the binary way, or you can just remember this easy little chart that I just showed you right here. Totally up to you. So now getting back to our chart over here, so we have pretty much solved all of our requirements for the marketing network. Now we're going to solve the IP address requirements for the HR department. So once again, we got 50 devices that need IP addresses. We add 3 because we got to account for the network ID, the gateway, and the broadcast. We figured out the network ID by taking the previous network ID and adding the incremental value to give us our current network ID, which then told us what our gateway IP address is going to be, which is just one IP greater than the network ID. Then it also told us our starting IP address, that we can start dishing IP addresses out to devices, and that's going to be a 130, which is just one IP greater than the gateway. So now we got that far. So now we need to go ahead and figure out the requirements for the switch. So we got our switch over here. I said we need 6 IP addresses for whatever reason. We're going to add 3. So that means we're going to have a host requirement of 9. We're going to go ahead and figure out our incremental value. So we come back over to this chart here. What number does 9 go into without going over? And we see it goes into the number 16 without going over. So that means we're working out of the 4th octet still. So now we got a 0.16. So now we can go ahead and figure out the network ID. So we're going to take HR's network ID, add this incremental value, and that's going to give us the network ID for the switch. So 128 plus 64 equals 192. So our network ID for the switch is going to be 192.16.1.192. That's going to be our network ID. Our gateway is going to be 1 greater than the network ID. So 192.16.1.193. That is our gateway IP address. And then our IP range is going to start with 1 IP greater than the gateway. So that's going to be .194. Now we can go ahead and use this information to solve for the broadcast for the HR department. So we go to our network ID and we just subtract 1 IP address to get us 192.16.1.191. And then from there, we're just going to subtract 1 IP address from the broadcast to get our last IP address of the IP range, which is going to be 190. So right here, we're looking at 60 IP addresses that we can assign to the HR department, even though the HR department only has a requirement of 50. Well, 60 is enough to cover all to meet this requirement right here. And then also we can go ahead and figure out our custom subnet mask based off of our incremental value of .64 or our positional value. And we come back over to our chart. 64 is going to yield us a /26 custom subnet mask. So now we solved all this for the switch. So now we need to go ahead and figure out the requirements for the router. Now with the router, we got a requirement of 2, but we're going to add an additional 2 IP addresses for the router to come up with 4 total hosts. And why are we doing that? Because we need to account for the network ID of the router and the broadcast. We do not need to account for the gateway IP address. Why? Because the router is the gateway. So we come back over to our little chart over here. We need to account for 2 IP addresses for this router, the private IP address and the public IP address. That is essentially what we are accounting for in this overall network that we are constructing over here. Remember, the router by default, at least in this scenario, this is the gateway device. Everything is trying to find this gateway device so they can go out there and communicate with the internet, or this network can communicate with this network and vice versa. So that's why we don't need to account for a gateway, and we only need to add an additional 2 hosts to this. So now we need to go to our chart and figure out what does the number 4 go into without going over. So 4, it goes into the number 4 without going over. So our incremental value, since we're in octet number 4, is going to be 0.4. Now to find the network ID for the router, we're just simply going to add 192 plus 16. So our network ID for this router is going to be 192.16.1.208. That is our network ID for the router, because we simply took the network ID for the switch and added it to the incremental value 192 plus 16. We're in the 4th octet, is going to yield us a 208. Now we can figure out our IP range. It's going to be 1 IP greater than the network ID. So this is going to start with a .209. And then also we can use this number to figure out the last IP address of the switch. So we're just going to subtract 1 IP, and that's going to give us a .208. So that'll be 192.16.1.206. .207. And then from there, we can just subtract one IP address, and that'll give us a .206. So all these IP addresses, that's a grand total of like 12 IP addresses. That'll meet all of our requirements over here for 6 IPs, or a grand total of 9 IPs. So we can, dish out IPs all over the place if we need to. And then we get back over here to our incremental value, .16. Come back over here, 16 yields a /28 subnet mask. And now we're going to drag this thing out one more step so we can figure out this same information for the router. So we're going to take our network ID for the router, .208, and add 4 to it. And that's going to give us 192.16.1.212. We're going to subtract 1 from this miscellaneous network so we can figure out our broadcast. That's going to give us 192.16.1.211. And then we're going to subtract 1 from the broadcast of the router to figure out the last IP that's ending for this particular device. And that's going to give us a .210. So essentially 2 IP addresses, .209 and .210, that are going to be assigned to this device if we want. And then from there, we can also take our .4 and figure out what our custom subnet mask is. So we come back up to our chart. We see our positional value of 4 is going to yield a /30. And basically a /30 is a .252. So this will be 255.255.255.252 once you crunch out the binary and work its way all the way out. So in a nutshell, ladies and gentlemen, this is what a VLSM chart looks like when you are trying to subnet a network so that you can have IPs that are way more manageable to deal with when you are going through trying to subnet the network beyond just the initial IP address that you were assigned from your ISP. So in this example here, we have our marketing department. They represent VLAN 1 or VLAN 3 or whatever. It doesn't even matter. They represent VLAN 3. And we said we needed 100 devices to assign to IP. So let's just imagine that in this network, there are 100 computers hanging off this switch in VLAN 3. Well, from here, when we go through and start programming our computers to bring them to life, if we're doing this manually, these are the IP addresses that we are going to assign to these devices. So this device right here might be .2, and this one might be .3, .4. We have options all the way up to .126. For HR, we said we needed 50 devices to have IP addresses. So this is our HR department. So imagine there are 50 computers hanging off this switch in VLAN 2. We come to our IP range. We have everything from .130 all the way to .190, a grand total of 60 IP addresses. So this one could be .130 and this one could be .131 all the way up to 190 if we want. And then from so on and so forth. And then once we actually get inside of the computer, if we were to manually do this, it's going to ask you for the IP address, the gateway IP address for the network, and the subnet mask. So you would just easily come back to your chart. So let's just say we're programming up this computer. We give it the IP address of 192.16.1.130 because this is the HR department. Well, from this chart, we already know what the IP address for the gateway is going to be. And we also know what the subnet mask is going to be for this particular device in this network. And you would do the same thing for this one over here. And then you come over to VLAN 3, marketing. Like I said, we gave this one an IP address of 192.16.1.2. And then this guy will be .3. So if we go in here and manually program up these 2 computers, we already know what our gateway IP address is going to be. And we know what our custom subnet mask is going to be for this device so that it can properly communicate on the network. And then we also know what the information for the switch and for the router is going to be. Anyways, I just wanted to show you guys this real quick, even though it's probably been like a 30-minute long video or something like that, as to what all this madness means when we were going through subnetting, learning about classful subnetting, classless subnetting. Well, this is what these numbers actually represent when people start talking about subnetting. This basically allows for you to create networks inside of a grander network so you can easily manage this thing better, because yes, even though I have them logically separated on the switch, I might have another switch hanging off this router over here to create another little network. I could throw some fire firewalls up in here. I can get real funky out in these streets if I really wanted to. But this VLSM chart, this is what allows for you to create a manageable pool of IP addresses to deal with. That's why we go ahead and subnet this thing down based off of our specific requirements that we need for our network needs. So that is why we do subnetting in a nutshell, ladies and gentlemen.
As network technologies evolve, organizations must adapt to new environments and methodologies to maintain efficient, secure, and scalable infrastructures. In the CompTIA Network Plus exam Objective 1.8, it focuses on summarizing evolving use cases for modern network environments, highlighting emerging technologies and concepts such as software-defined networking, virtual extensible local area networks, zero trust architecture, secure access, secure edge, infrastructure as a code, and IP version 6 addressing. So let's go ahead and dive into these use cases to better understand their significance in the networking landscape. All right, so let's talk about software-defined networking and software-defined wide area networks. And the first component we're going to focus on is application-aware networking. So SDN and SD-WAN, they enable application-aware networking, which allows the network to prioritize traffic based on application requirements. So for instance, critical business applications like video conferencing, they can receive higher bandwidth and lower latency compared to less critical tasks such as file downloads. And this capability, it optimizes resource allocation and improves end user experience. The next, we have what is called zero touch provisioning. And this is a feature of SDN and SD-WAN that simplifies the deployment of network devices to where administrators can configure devices remotely without manual intervention, which saves time and reduces configuration errors. And this is especially beneficial for organizations that manage large scale or geographically dispersed networks. Then we have what is called transport agnostic networks, and these allow SD-WANs to operate over any type of network transport, including MPLS, broadband, LTE, and satellite. And this flexibility ensures that organizations can utilize cost-effective and reliable transport options based on their specific needs while maintaining consistent performance. And then we have central policy management. So centralized policy management in SDN and SD-WAN, this enables administrators to define and enforce network policies from a single interface. And this reduces complexity, enhances security, and ensures uniform policy application across the network. So for example, an enterprise, they can create a global policy to restrict unauthorized access to sensitive applications, which is automatically applied to all branch locations. All right, so let's move on and talk about virtual extensible local area networks. So virtual extensible local area networks, this is a technology that extends traditional VLAN capabilities, providing scalable layer 2 segmentation over layer 3 networks. And it is widely used in modern data centers and cloud environments. And the first component of this is called the data center interconnect. So VXLANs, they facilitate data center interconnects, which enables organizations to link multiple data centers seamlessly. And this ensures that resources can be shared efficiently and provides redundancy for critical applications. So for example, a company with 2 geographically separate data centers, they can use VXLAN to create a unified environment, which enhances both performance and resilience. Then we have what is called layer 2 encapsulation. So VXLAN, it uses layer 2 encapsulation to encapsulate Ethernet frames within UDP packets. And this allows for better scalability, which supports up to 16 million unique network identifiers compared to the 4,096 identifiers, which are supported by traditional VLANs. And this scalability is essential for large enterprises and cloud service providers with extensive virtualized infrastructures. All right, so let's move on and talk about the zero trust architecture. So the zero trust architecture, this has become a cornerstone of modern network security, where it emphasizes the principle of never trust and always verify. So let's talk about the policy-based authentication. So zero trust architecture, this implements policy-based authentication where access decisions are made dynamically based on factors such as identity, device health, and location. So for instance, an employee accessing the network from an untrusted device may be required to undergo additional verification before gaining access. And then we have what is called granular authorization. So authorization within ZTA is granular, where it ensures that users and devices only access the resources they are explicitly permitted to use. And this minimizes the risk of lateral movement within the network in case of a breach. And then we have what is called least privilege access. So ZTA, this enforces the principle of least privilege, where it grants users and devices the minimum access necessary to perform their tasks. And this reduces the attack surface and limits the potential impact of a compromised account. All right, next let's talk about secure access, secure edge, and security service edge. So SASE and SSE, these are frameworks that combine networking and security services into a unified solution that is delivered by way of the cloud. And they address the challenges of securing and managing remote workforces and distributed networks. And here are some of the key benefits of SASE and SSE. So SASE, this integrates SD-WAN capabilities with security functions such as secure web gateways, firewall as a service, and zero trust network access. And SSE, which is a subset of SASE, this focuses specifically on security services without SD-WAN functionality. And by adopting SASE or SSE, organizations, they can simplify their network and security operations while ensuring consistent policy enforcement across users and devices, regardless of their location. All right, so let's move on and talk about infrastructure as code. So infrastructure as code, this is revolutionizing network management by enabling administrators to manage and provision infrastructure using code, similar to how software applications are developed. So within that, let's talk about automation. So IAC, this facilitates automation through reusable playbooks, templates, and tasks, and this reduces manual effort and ensures consistency in network configurations. So organizations, they can create standardized templates for common tasks, such as deploying virtual machines or configuring routers. Also, infrastructure as code tools, it helps detect and remediate configuration drift, ensuring that infrastructure remains compliant with organizational policies. Another thing it does is automating upgrades, which reduces downtime and minimizes the risk of human error. And also IAC, this enables dynamic inventories, which automatically update devices and resource lists based on changes in the environment. Another aspect is source control in infrastructure as code. So source control systems, they are integral to IAC, where they provide mechanisms for version control, central repositories, and collaboration amongst teams. What this does is it helps track changes to infrastructure code, making it easier to identify and revert problematic updates. It's also a single source of truth for infrastructure code, ensuring that teams work with the latest configurations. It identifies and resolves conflicts when multiple teams work on the same code base. And then teams, they can create separate branches for testing and development, which reduces the risk of introducing errors into production environments. All right, so let's quickly talk about IP version 6 addressing. So the adoption of IP version 6 addresses challenges IP version 4 address exhaustion and ensures compatibility with modern network requirements. So let's talk about mitigating address exhaustion. So IP version 6 provides an almost unlimited pool of IP addresses, eliminating the limitations of IP version 4. And this is crucial for accommodating the growth of IoT devices and other emerging technologies. And let's quickly talk about some of its compatibility requirements. So the first one is tunneling. So tunneling techniques such as 6to4 and Terado, they allow IP version 6 traffic to traverse IP version 4 networks, ensuring backwards compatibility during the transition to IP version 6. Then you have what is called dual stack and dual stack implementations. They enable devices to support both IP version 4 and IP version 6 simultaneously, which provides a seamless user experience during the migration process. And then you have what is called NAT64 and Network Address Translation 64. This facilitates communication between IP version 6 and IP version 4 devices by translating IP version 6 packets into IP version 4 packets and vice versa. All right, so to wrap all this up, the evolving use cases of modern network environments, this reflects the dynamic nature of technology and its role in addressing complex organizational challenges. And by understanding and leveraging technologies such as SDN, VXLAN, ZTA, SASE, infrastructure as code, and IP version 6, IT professionals can design networks that are more efficient, secure, and scalable. And these advancements not only enhance operational efficiency, but also position organizations to adapt adapt to future innovations, ensuring long-term success in an ever-changing digital landscape. All right, so with all of that being said, let's do some check on learning. So, which of the following best describes the primary benefit of software-defined wide area networks? Is it allows network devices to function without requiring a central controller? Is it enables centralized policy management and transparent agnostic routing? Is it eliminates the need for IP addressing and subnetting? Or is it solely relies on physical networking hardware for configuration? And the correct answer is it enables centralized policy management and transport agnostic routing. So SD-WAN, this allows organizations to centrally manage network policies while optimizing traffic routing across multiple transport types, including broadband, LTE, and MPLS. And this transport agnostic approach improves performance, enhances security, and reduces costs. Next question. Which of the following technologies is used to extend layer 2 networks across different data centers? Would this be VXLAN, SDN, SASE, or IP version 6? And the correct answer is VXLAN. So virtual extensible local area networks. This is a tunneling protocol that encapsulates layer 2 Ethernet frames within layer 3 UDP packets. And this allows data center interconnect functionality, which enables organizations to extend layer 2 networks over large scale environments without being restricted by VLAN limitations. And our final question, which of the following principles is a fundamental aspect of zero trust architecture? Is it implicit trust for internal network traffic? Is it least privileged access and policy-based authentication? Is it relying only on perimeter-based security controls? Or is it using static configurations without automation? And the correct answer is least privileged access and policy-based authentication. So zero trust architecture, this operates under the principle that no entity should be trusted by default, whether inside or outside the network. It enforces least privileged access and requires continuous authentication and authorization based on policies to ensure security. Routing technologies, they form the backbone of modern networking by enabling data to travel efficiently across complex networks. And the CompTIA Network Plus exam objective 2.1 focuses on the characteristics of various routing technologies, including static and dynamic routing, route selection methods, address translation, first hop redundancy protocols, virtual IPs, and sub interfaces. In this video, we're going to provide a comprehensive overview of these concepts, helping aspiring network professionals grasp the essentials of routing in preparation for the exam. All right, so let's talk about static routing. So static routing, this is a manual method of routing where administrators configure fixed paths for traffic to reach specific destinations. Now, unlike dynamic routing, static routing does not change unless manually updated by a network administrator. And here are some of the characteristics of static routing. So you have simplicity, so that means it's easy to configure on small networks. It's predictable because the routes do not change unless manually modified. They're efficient, so there are no extra bandwidth usage for routing updates. And here are some of the limitations associated with it. So it does not scale well for large networks. It requires manual intervention for updates, and they cannot adapt to network topology changes automatically. All right, so let's move on and talk about dynamic routing. So dynamic routing protocols, they enable routers to exchange information and update routing tables automatically. And these protocols improve efficiency and adaptability by selecting the best paths based on network conditions. And the first routing protocol we're going to talk about is the Border Gateway Protocol. So BGP, this is the primary exterior gateway protocol used to route traffic between autonomous systems on the internet. And some of its characteristics are as follows. So it uses what is called path vector routing. It determines the best path using attributes like autonomous systems path, next hop, and local preference. It provides scalability for large networks, and it supports both internal BGP and external BGP. Next, we have what is called Enhanced Interior Gateway Routing Protocol, or EIGRP. And this is an advanced distance vector routing protocol developed by Cisco, and it is commonly used in enterprise networks. And some of its characteristics are as follows. So it uses a hybrid approach combining distance vector and link state properties. It supports multiple network layer protocols. It uses diffusion update algorithms for efficient route calculation, and it offers fast convergence and reduced bandwidth usage. And the next protocol we have is called OSPF, or Open Shortest Path First. And this is a widely used link state routing protocol designed for large and complex networks. And its characteristics are as follows. So it utilizes the shortest path first algorithm. It supports hierarchical design through areas to optimize performance. It has fast convergence and minimal routing overhead, and it uses cost as a metric based on bandwidth. All right, so let's move on and talk about route selection. So route selection, this is the process of determining the best path for data packets. And routers use various criteria to make these routing decisions. The first criteria is called AD, or administrative distance. So administrative distance, this is a value assigned to routes to indicate their reliability. And lower values, they represent more trusted routes. And some of the common AD values are as follows. So you have directly connected, you'll see the value 0. Static route, it'll say 1. External BGP, it'll say 20. EIGRP 90. OSPF 110. And internal BGP, it'll say 200. And then next we have the prefix length. So when multiple routes exist for a destination, the router prioritizes the one with the longest matching prefix length, which is the most specific match. Then we have metrics, or best path selections for routing protocols. So each routing protocol uses different metrics to determine the best path. So OSPF, it goes with the cost, which is based on bandwidth. EIGRP uses a composite metric, which is bandwidth, delay, reliability, and load. RIP, it uses a hop count. In BGP, it uses path attributes such as autonomous system path, local preferences, and next hop. All right, so let's move on and talk about address translation. So address translation, this allows devices within private networks to communicate with external networks by modifying IP addresses. So the first part is network address translation. So NAT, this is used to map private IP addresses to a public IP address, allowing multiple devices to share a single public IP. And we have different types of NAT. So the first one is called static NAT. And this is a one-to-one mapping between private and public IP addresses. You have what is called dynamic NAT, and this maps private IP addresses to public ones dynamically. And then you have what is called overloaded NAT, or PAT, which stands for port address translation. And this is when multiple private IP addresses share a single public IP using different ports. And speaking of port address translation, so PAT, once again, this is also known as NAT overload. This assigns multiple private IP addresses to a single public IP using different ports. And this method conserves public IP addresses and is widely used in home and enterprise networks. All right, so let's move on and talk about FHRPs, our first hop redundancy protocols. So a first hop redundancy protocol, this is a group of protocols that are designed to provide gateway redundancy to ensure high availability. And some of the common FHRPs include the following. You have what is called a hot standby router protocol. And this is a Cisco proprietary protocol that elects an active and standby router. Then you have what is called a virtual router redundancy protocol. This is an open standard protocol that is similar to HSRP. And then you have what is called a gateway load balancing protocol. And this is a Cisco proprietary protocol that allows multiple active routers. All right, so let's move on and talk about virtual IPs. So a virtual IP address, this is an IP address assigned to multiple devices within the network to ensure redundancy and load balancing. And VIPs, they are used in conjunction with FHRPs to provide uninterrupted network services. And some of the use cases are as follows. So it has load balancing in server farms. It provides high availability in network gateways. And it also has failover mechanisms in enterprise networks. All right, and finally, let's talk about sub interfaces real quick. So sub interfaces, they allow a single physical interface to be divided into multiple logical interfaces, with each assigned to different VLANs or IP subnets. And its benefits are as follows. So it reduces hardware requirements by using a single physical interface. It supports VLAN tagging using IEEE 802.1q, and it enhances network segmentation and traffic management. All right, so in conclusion, understanding routing technologies, this is essential for networking professionals preparing for the CompTIA Network Plus exam. In this video, we talked about static and dynamic routing, route selection factors, address translation, FHRP, VIPs, and sub interfaces, which are all key concepts that play a critical role in efficient network communication. Now, by mastering these topics, candidates, they can enhance their knowledge and excel in their networking careers. All right, so with all of that being said, let's do some check on learning. So the first question is, which of the following statements about static routing is true? Is it static routing requires less administrative effort than dynamic routing? Is it static routing is best suited for large complex networks with frequently changing routes? Is it static routes do not consume bandwidth for route updates? Or is it static routes automatically adjust to network topology changes? And the correct answer is static routes do not consume bandwidth for route updates. So static routing, this involves manually configuring routes in a router's routing table. Since it does not use a routing protocol, it does not generate periodic updates, reducing bandwidth usage. However, static routing requires manual maintenance and does not dynamically adapt to network changes, making it unsuitable for large, complex networks. Next question. What is the primary purpose of administrative distance and route selection? Is it determines the fastest route to a destination based on link speed? It specifies the best path by calculating the number of hops to a destination. It ranks the trustworthiness of different routing sources in a router's routing table? Or is it determines the shortest path by using cost metrics like bandwidth and delay? And the correct answer is it ranks the trustworthiness of different routing sources in a router's routing table. So administrative distance is used by routers to prioritize competing routes from different sources like static routes, OSPF, or BGP. And the lower the AD value, the more preferred the route. It does not determine speed or hop count directly, but influences which route is chosen when multiple routes to the same destination exist. And our final question, which of the following statements accurately describes port address translation? Is it PAT allows multiple private IP addresses to share a single public IP address? Is it PAT assigns a unique public IP address to each internal device? Is it PAT eliminates the need for a default gateway on internal networks? Or is it PAT is only used for IP version 6 networks? And the correct answer is PAT allows multiple private IP addresses to share a single public IP address. So PAT, which is a type of network address translation, this enables multiple devices on a private network to access the internet using a single public IP address. It differentiates traffic by assigning unique port numbers to each session, allowing efficient use of IP addresses. And PAT is widely used in IP version 4 networks to conserve public IP space. Switches. These are critical components of modern networks. They are responsible for efficient data forwarding and segmentation. And the CompTIA Network Plus exam emphasizes understanding and configuring essential switching technologies and features. And in this video, we're going to explore VLANs, interface configurations, 802.1q tagging, link aggregation, spanning tree protocols, and much more. All right, so let's begin with talking about virtual local area networks, or VLANs. So a VLAN, this is a logical segmentation of a physical switch into multiple broadcast domains. The VLANs, they enhance security, improve network efficiency, and they reduce congestion by grouping devices logically rather than physically. All right, so let's talk about a VLAN database. So the VLAN database, this is where VLAN configurations are stored on a switch. And in some switch operating systems, VLANs are managed using the VLAN.dat file, which is stored in its flash memory. On Cisco devices, VLANs are created and stored in the VLAN database using commands like the ones you see on your screen right here. However, modern Cisco iOS switches, they allow VLAN creation in global configuration mode, as you can see on your screen right down here. All right, so let's move on and talk about a switch virtual interface. So an SVI, this is a logical layer 3 interface on a switch that allows inter-VLAN communication. And SVIs, they are essential for routing between VLANs and layer 3 switches. Now, to configure an SVI on a Cisco switch, you would simply type in some commands on your screen that look like this right here. All right, so let's move on and talk about interface configurations. And we're going to start with the native VLAN. So the native VLAN, this is an untagged VLAN that is assigned to a trunk port. And by default, VLAN 1 is the native VLAN on Cisco switches. But best practice is to assign a different VLAN to prevent VLAN hopping attacks. And if you want to change the native VLAN, you would type in some commands that look like this right here. And then we have what is called a voice VLAN. And this is a separate VLAN that is dedicated to voice over IP traffic to ensure quality of service. And if you want to configure a voice VLAN, you would type in commands that look like this right here. Next, we have what is called 802.1q tagging, and this is an IEEE standard for VLAN tagging, which allows multiple VLANs to traverse a single trunk link by adding a VLAN identifier in the Ethernet frame. And to configure an interface as a trunk and enable 802.1q tagging, you would type in some commands that look like this right here. And then we have what is called link aggregation. So link aggregation, this groups multiple physical links into a single logical link to increase bandwidth and redundancy. And the IEEE standard for link aggregation is 802.3AD or LACP, which stands for Link Aggregation Control Protocol. And if you want to configure the LACP, you would type in commands that look like this right here. And moving on, let's talk about speed and duplex settings. So interface speed and duplex settings, they must match to avoid network issues such as collisions and slow performance. And some common speeds are 10 megabits per second, 100 megabits, 1 gigabit per second, and 10 gigabit per second. Then within duplex modes, we have two types. You have what is called half duplex, and this is used in legacy systems and shared media networks. And then you have what is called a full duplex mode, and this is used in modern switch networks. And to configure them manually, you would type in commands that look like this right here. All right, so let's move on and talk about the spanning tree protocol. So spanning tree protocol, this prevents layer 2 loops by disabling redundant paths in a switch network. And some variants include the following. So you have what is called RSTP or rapid STP, and this is for faster convergence. You have what is called MSTP or multiple STP, and this is for multiple VLANs. And you have what is called PVST plus or per VLAN spanning tree plus, and this is for VLAN specific STP. And once again, if you want to enable STP on a switch, you would type in a command that looks like this right here. All right, so let's move on and talk about maximum transmission units or MTUs. So MTU, this defines the maximum size of an Ethernet frame, and the default MTU is 1500 bytes, but it can be increased for performance gains. And if you do so, they're going to be called jumbo frames. So jumbo frames, they allow for Ethernet frames that are larger than 1500 bytes, usually up to 9000 bytes, to enhance network performance in high bandwidth environments. And if you want to enable jumbo frames on a switch, you would type in a command that looks like this right here. All right, so that was a quick class. So in conclusion, understanding and configuring switching technologies, this is vital for optimizing network performance and security. VLANs, they segment traffic. SVIs, they enable inter-VLAN routing. 802.1q, this provides VLAN tagging. And link aggregation, this boosts bandwidth. Additionally, spanning tree protocol, this ensures loop-free topologies. And MTU settings, they optimize data transmission. So mastering these concepts is crucial for passing the CompTIA Network Plus exam and excelling in real-world networking scenarios. Now, to make the most out of all this knowledge, you're going to want to do some hands-on type of activities, whether you got access to a physical switch that you can configure, or you can download a program like Packet Tracer, or you can buy some type of virtual lab program that will allow for you to get in there and start manually configuring these things. That is the best way that you are going to learn and comprehend what all this information means that I just went over in this slideshow. Now, with that being said, let's do some check on learning. So, the first question is, which of the following is a primary function of 802.1q in VLAN configuration? Is it assigns a specific IP address to each VLAN? Is it enables multiple VLANs to share a single physical switch port? Is it restricts VLAN traffic to specific interfaces? Or is it automatically assigns devices to VLANs based on MAC addresses? And the correct answer is it enables multiple VLANs to share a single physical switch port. So 802.1q, this is a VLAN tagging protocol that allows multiple VLANs to share a single physical port by adding a tag to Ethernet frames. And this tag identifies the VLAN to which the frame belongs, ensuring proper network segmentation across trunk links. Next question, which feature is used to prevent loops in a switched network by disabling redundant paths until needed? Would this be spanning tree protocol, link aggregation control protocol, native VLAN, or switch virtual interface? And the correct answer is this would be spanning tree protocol. So STP, this is designed to prevent switching loops in a network by identifying and disabling redundant paths. If a primary link fails, STP dynamically reactivates a redundant link to maintain network connectivity. And our final question, a network administrator wants to optimize traffic for voice over IP devices on a switch. Which VLAN configuration should be used? Would it be assign VoIP devices to the native VLAN? Would it be increase the MTU size for VoIP packets? Would it be disable 802.1q tagging for VoIP devices? Or would it be use a voice VLAN to prioritize VoIP traffic? And the correct answer is you would use a voice VLAN to prioritize VoIP traffic. So a voice VLAN, this is a dedicated VLAN designed to carry voice over IP traffic separately from data traffic. And this configuration prioritizes voice packets, ensuring lower latency and improved call quality by applying quality of service policies. Wireless networking. This plays a crucial role in modern IT infrastructure, requiring professionals to understand and configure wireless devices and technologies effectively. And the CompTIA Network Plus exam objective 2.3 covers selecting and configuring wireless devices and technologies in various scenarios. And in this video, we're going to explore key aspects such as frequency options, network types, authentication, encryption, and other critical configurations for setting up wireless networks. All right, so let's begin with talking about channels and wireless networking. So wireless channels, they determine how much data can be transmitted over a network, and channel width, this defines the bandwidth available for communication, which is commonly set at 20 megahertz, 40 megahertz, 80 megahertz, or even 160 megahertz. And wider channels, they offer higher throughput, but can lead to interference, especially in congested environments. Then we have what are called non-overlapping channels. So to reduce interference, non-overlapping channels, they must be used strategically. In the 2.4 gigahertz band, there are 3 non-overlapping channels, which are channels 1, 6, and 11. And in the 5 gigahertz and 6 gigahertz bands, there are more channels available, which reduces congestion and improves performance. All right, so let's talk about the regulatory impacts such as 802.11h. So the IEEE 802.11h standard, this addresses regulatory requirements, particularly for dynamic frequency selection and transmit power control. In DFS, this allows devices to detect radar signals and switch channels automatically, preventing interference. And TPC, this regulates power output, ensuring compliance and regional restrictions. All right, so let's move on and talk about frequency options. So we have the 2.4 gigahertz band, and this is widely used due to its range and compatibility. However, it is prone to interference from devices like microwaves and Bluetooth equipment, and it does support lower data rates, but provides better coverage. And then we have the 5 gigahertz band, and this offers higher speeds and more available channels, reducing interference. And it does support wider channels like 40 megahertz, 80, and 160 megahertz, making it ideal for high performance applications. And then we have the 6 gigahertz band. And the 6 gigahertz band, this is a part of Wi-Fi 6E, and it offers even more channels with less interference. And this band improves throughput and reduces congestion in enterprise environments. And then we have a concept called band steering, and this encourages devices to connect to the best available frequency band, improving performance. And it automatically directs dual band and tri-band clients to the 5 gigahertz or 6 gigahertz band instead of the overcrowded 2.4 gigahertz band. All right, so let's move on and talk about the SSID, or the service set identifier. And the first one we're going to talk about is called the basic service set identifier. And this is the MAC address of a wireless access point in a network. And each access point has a unique BSSID, allowing devices to identify and connect to a specific access point. Then we have what is called the extended service set identifier. And the ESSID, this is a group of multiple access points configured under the same SSID, allowing seamless roaming between access points in larger networks. And it provides network continuity and enhanced coverage. All right, moving on, we're going to talk about network types. And the first one we're going to talk about is a mesh network. So mesh networks, they use multiple access points to provide wide coverage, and nodes that communicate dynamically, ensuring continuous connectivity even if one access point fails. Then we have what is called an ad hoc network. And these are peer-to-peer wireless networks where devices communicate directly without an access point. And these networks are temporary, and they are commonly used for quick file transfers or emergency communication. Then we have what is called a point-to-point network. And a point-to-point network, they connect two devices using a dedicated wireless link. They are commonly used for long-distance communication between buildings or remote locations. And then we have what are called infrastructure networks, and they rely on a central access point to facilitate communication between devices. And this is the most common network type in business and home environments. All right, so let's move on and talk about encryption methods. And the first one we're going to talk about is WPA2, or Wi-Fi Protected Access 2. And this is a widely used encryption standard providing strong security through AES, or Advanced Encryption Standard. And it offers robust protection, but it is vulnerable to brute force attacks and key reinstallation attacks, also known as crack. And then we have what is called WPA3, and this enhances security by using simultaneous authentication of equals to prevent offline dictionary attacks, and it improves encryption for public Wi-Fi and strengthens protection for weak passwords. All right, next we have what are called guest networks, and we're going to talk about a captive portal. So a captive portal, this authenticates users before granting access to a guest network. And these portals typically require users to enter login credentials, accept terms of service, or complete a verification process before using the network. Next, we have authentication methods, and we're going to talk about a pre-shared key versus enterprise. So PSK authentication, this is commonly used in home and small business networks where a user enters a shared password to connect. And when it comes to enterprise authentication, this uses 802.1x authentication with a radius server, offering better security and individual user authentication. Next up are wireless antennas, and the first one is called an omnidirectional antenna. So an omnidirectional antenna, this broadcasts signals in all directions, making them suitable for general coverage areas such as offices and homes. And then we have what is called a directional antenna, and this focuses signals in a specific direction, increasing range and performance. And these are commonly used for point-to-point wireless links and extending coverage in targeted areas. All right, and next we have access points. So we're going to talk about autonomous access points and lightweight access points. So an autonomous access point, this operates independently, requiring manual configuration and management. They are ideal for small networks, but can become difficult to manage in larger departments. Then we have what is called a lightweight access point, and this relies on a centralized wireless controller for configuration and management. And these access points are used in enterprise environments for scalability and improve network administration. All right, so in conclusion, understanding how to select and configure wireless devices and technologies is essential for network professionals. And by considering factors like frequency options, network types, encryption, and authentication, IT professionals can design efficient and secure wireless networks. And mastering these concepts will not only help in passing the CompTIA Network Plus exam, but also in real-world networking scenarios. All right, now with all of that being said, let's do some check on learning. So the first question is, which of the following best describes the primary advantage of using 5 gigahertz and 6 gigahertz frequency bands over 2.4 gigahertz in a wireless network? Would it be greater range and better penetration through walls? Would it be higher data transfer speeds and less interference? Would it be compatibility with older devices and greater congestion? Or would it be ability to operate with lower power consumption? And the correct answer is higher data transfer speeds and less interference. So the 5 gigahertz and 6 gigahertz frequency bands, they provide higher data transfer speeds and experience less interference compared to 2.4 gigahertz, which is commonly congested due to shared use with other wireless technologies like Bluetooths and microwaves. However, 5 gigahertz and 6 gigahertz, they have shorter ranges and lower penetration through walls compared to that of the 2.4 gigahertz band. Next question. Which of the following is the primary benefit of enabling band steering on a dual band or tri-band wireless access point? Is it improves security by blocking unauthorized devices from connecting? Is it prioritizes voice and video traffic for a smoother experience? Is it directs capable clients to use the 5 gigahertz or 6 gigahertz bands instead of the 2.4 gigahertz? Or is it increases signal strength for all wireless clients by amplifying transmissions? And the correct answer is it directs capable clients to use the 5 gigahertz or 6 gigahertz bands instead of 2.4. So band steering, this is a feature in modern dual band or tri-band access points that encourages clients capable of connecting to 5 or 6 gigahertz to use those bands instead of 2.4. And this reduces congestion in the 2.4 gigahertz band, leading to improved overall network performance. And our final question, which of the following best describes the difference between an omnidirectional antenna and a directional antenna in a wireless network? Is it omnidirectional antennas send signals in all directions, while directional antennas focus signals in a specific direction? Is it omnidirectional antennas require line of sight connections, while directional antennas do not? Is it omnidirectional antennas are only used indoors, while directional antennas are used outdoors? Or is it omnidirectional antennas support only 2.4 gigahertz networks, while directional antennas support only 5 gigahertz networks? And the correct answer is omnidirectional antennas. They send signals in all directions, while directional antennas focus signals in a specific direction. So omnidirectional antennas broadcast wireless signals equally in all directions, making them suitable for general coverage in homes, offices, and public spaces. Directional antennas, on the other hand, they focus the signal in a specific direction, which is useful for long distance point-to-point connections or targeted coverage areas. Physical network installations are fundamental to establishing reliable and scalable infrastructure. So, whether setting up a small or large enterprise network, key considerations such as equipment locations, rack sizes, power management, cabling, and environmental controls play a crucial role in performance and longevity. And in this video, we're going to go over the CompTIA Network Plus exam objective 2.4, focusing on essential factors that impact physical installations. All right, so let's begin by talking about some important installation implications. And we're going to talk about IDFs and MDFs, or intermediate distribution frames, and main distribution frames. Networking infrastructure is typically organized into two main physical locations: the intermediate distribution frame and the main distribution frame. And understanding their roles, this ensures efficient data transmission and structured cable management. So let's talk about the MDF. So this is the primary hub of network connectivity within a building or facility. It connects external circuits such as internet service providers to the internal network, and all network traffic is routed through this centralized point, making it critical for stability and performance. And the MDF is also located in a secure area with proper ventilation. It houses core network components like routers, switches, and patch panels, and it must be easily accessible to IT professionals for maintenance and upgrades. Then we have the IDF, and the IDF serves as a secondary distribution point within larger buildings or campuses, typically located on different floors or wings. And the IDF is connected to the MDF via backbone cabling, which is often fiber optics for high-speed data transmission. It also facilitates shorter cable runs to workstations, reducing latency and clutter, and it requires environmental controls that are similar to the MDF. All right, next let's talk about rack size considerations. So rack mounted equipment, this is standard in structured networking environments, and the size and configuration of a rack, this directly impacts space utilization, cooling, and accessibility. So we have what are called rack units. So equipment racks, they are measured in standard units represented by the letter U, where 1 U equals 1.75 inches of vertical space, and the common sizes are 42 U and 48 U for data centers, and 24 U and 12 U for smaller installations. And this ensures compatibility with standard networking gear such as switches, servers, and patch panels. Then we have depth and width. The standard rack depth is 19 inches, and this is common for networking and server equipment. And deep racks, which could be 29 to 42 inches, they accommodate cable management and airflow optimization. And then you have width considerations, and these are 23-inch racks, and they are less common, but they exist for telecom equipment. All right, next we have what is called port side exhaust or intake for proper airflow. So proper airflow management, this is critical to prevent overheating and ensure network reliability. So front to back cooling, this is preferred in most data centers. Side to side airflow, this may be necessary for certain switches and network appliances. And this ensures adequate spacing between equipment and uses blanking panels to direct airflow efficiently. And then there's also the implementation of hot aisle and cold aisle arrangements in large scale installations. All right, next we have cabling considerations. So structured cabling is essential for an organized and efficient network. This minimizes interference, simplifies troubleshooting, and improves scalability. So we have patch panels, and these allow for easy cable management and organization, reducing stress on network ports. So you want to make sure you're labeling the ports to enhance troubleshooting, and this helps in future expansion and maintenance. They have fiber distribution panels, and these are essential for fiber optic connections, and they protect delicate fiber optic strands, and they also provide an organized way to connect backbone infrastructure. Then you have lockable enclosures, and these are network cabinets and patch panels that should be lockable to enhance security to prevent unauthorized access. And ultimately what they do is restrict physical tampering with critical connections, and they also ensure compliance with security policies and regulated industries. All right, so let's move on and talk about some power considerations. So reliable power solutions are essential for network availability, and proper planning prevents downtime and protects equipment from electrical issues. So let's talk about the UPS, or the uninterruptible power supply. So in UPS, this provides temporary backup power in case of electrical outages, allowing for graceful shutdowns or continued operation. And the first type of UPS you have is called an online UPS, and this provides continuous power with zero transfer time, which is ideal for mission critical environments. Next, you have what is called a line interactive UPS, and this adjusts voltage fluctuations without using battery power, and this is common in offices and small server rooms. And then you have what is called a standby UPS, and this switches to battery power during an outage, and this is suitable for non-critical devices. All right, next we have what is called a power distribution unit, or a PDU. And a PDU, they distribute electrical power to networking equipment and racks. And you have what is called the basic PDU, and this is your standard power strip for distributing AC power. And you have what is called a metered PDU, and this displays power consumption for monitoring. And then you have what is called a switched PDU, and this allows remote power management and rebooting of devices. Next, we have power load and voltage considerations. So understanding power loads and voltage requirements, this ensures equipment runs efficiently without risk of overload or failure. So you want to calculate power consumption, and this is the total wattage of connected devices that must not exceed the PDU or circuit capacity. Then you have various voltage options. So you have 120 volts, and this is standard in North America for most office equipment. Then you have 208 volts all the way to 240 volts, and this is common in data centers for increased efficiency. Do you have redundant power supplies that can mitigate single points of failure? All right, so let's move on and talk about some environmental factors. So proper environmental management, this extends the life of networking equipment and ensures stable operations. So let's first talk about humidity control. So humidity levels, they should be controlled to prevent corrosion and static electricity buildup. And the ideal humidity range should be about 40 to 60%. Now, if it's too high, this can cause condensation, which can lead to short circuits. If it's too low, this can increase static electricity, which can damage components. And so you also want to use humidifiers and dehumidifiers that are based on climate conditions. Next, we have fire suppression systems. So networking equipment, this is vulnerable to fire hazards due to high power consumption and heat generation. So gas-based suppression systems like FM200, CO2, or Novec 1230, this can prevent damage to sensitive electronics. You have water-based systems that should only be used as a last resort. Then fire suppression, this should be integrated with smoke detection and alarm systems. Next, there's temperature control. So maintaining optimal temperatures, this prevents equipment failure and ensures network stability. And the ideal range is 64 to 80 degrees Fahrenheit or 18 to 27 degrees Celsius. You have some cooling methods like HVAC systems, and these are your standard air conditioning units for server rooms. You also have what is called a CRAC unit, or a computer room air conditioning, and this is specialized cooling for data centers. And then you also have liquid cooling, and this is used in high performance computing environments. All right, so in conclusion, successful physical network installations, this requires careful planning and adherence to industry best practices. And key considerations include strategic equipment placement of the MDF and IDF, proper rack configuration, structured cabling, reliable power sources, and environmental control. And by implementing these principles, network professionals, they can create efficient, secure, and scalable infrastructures that align with the CompTIA Network Plus standards. Now, with all of that being said, let's do some check on learning. So which of the following is the primary purpose of an intermediate distribution frame in a structured cabling system? Is it acts as the central point for all network connections in a facility? Is it provides backup power to networking equipment? Is it is used for fire suppression and environmental monitoring? Or is it connects end user devices to the main distribution frame? And the correct answer is it connects end user devices to the MDF. So the IDF, this is a secondary distribution point that connects to the MDF, allowing network connections to be extended to various floors or areas in a building. And the MDF, this is the primary hub where external network connections enter the facility. Next question, which power-related factors should be considered to prevent damage to network equipment due to power fluctuations? Would this be port side exhaust configuration? Would this be an uninterruptible power supply? Would this be a fiber distribution panel? Or would this be the rack size? And the correct answer is this will be an uninterruptible power supply. So an UPS is critical in preventing sudden power losses or fluctuations from damaging network infrastructure. It provides backup power in case of an outage, allowing devices to safely shut down or continue operating until power is restored. And our final question, which of the following environmental factors is crucial to monitor in a network equipment room to prevent overheating and equipment failure? Would this be proper humidity levels, lockable racks, patch panels, or power distribution units? And of course, the answer is going to be proper humidity levels. So maintaining appropriate humidity levels, this is essential in data centers and network rooms. Low humidity, this can lead to electrostatic discharge, also known as static electricity, while high humidity, this can cause moisture buildup, leading to short circuits and corrosion. So temperature control, this is also important to prevent overheating of network devices.
All right, so in your home, you more than likely have a smartphone, some type of tablet, or maybe even a laptop that you use for wireless internet connectivity so you can get out there and live your best life surfing these internet streets. Also in your house, you may have a laptop or a desktop computer that may be hardwired to your wireless router in your house. So this is typically what you will find in the average household. You'll find mobile devices and you'll find desktop computers, right? So these devices, they are connected to a device called a switch. And this is a switch right here that is being represented by a little square with two arrows going in opposite directions. Also, if you're using mobile, you may have another device called an access point or a wireless access point. Also, there is another device called a router, which is represented by this circle right here that has arrows going up and down and left and right. And then there is another device called a modem, which is going to be represented by this device. We'll just put MD for modem. And then you have the internet, which is represented by this cloud looking thing over here. All right, so these are the basic components for how the internet works, which allows for you to press the enter key on your keyboard and go way over here to watch a YouTube video like Tech G. So how does all this work? So like I said, we got a mobile device, which is your wireless device. And what this does, your wireless device, it connects to this access point right here. This access point is then physically connected by way of a Cat5 cable to the switch. If you have a desktop computer with a wire hanging out of it, that's called a Cat5 cable, it is hardwired to the switch as well. And then you have your switch that is hardwired to the router. And then you have your router that is hardwired to your modem. And then you have your modem, we're just going to use this little squiggly line here to represent that it's going out there to the great internet so it can retrieve whatever content you're looking for. Okay. Now, how this directly relates to your house is you guys more than likely don't have a separate switch, you don't have a separate access point, and you don't have a separate router. These three devices right here are typically combined into what is called a SOHO router, small office, home office router, or your wireless router as you guys all know it. So you guys go look at your wireless router. You might see some antennas hanging off of it. You'll see a couple ports on there. And then you see another port that has some type of Cat5 cable or something hanging out of it. That is your wireless router. Basically in a SOHO environment, it combines all of those elements into one device to save you money and save you space. All right, so how this works is like this, ladies and gentlemen. So you're on your mobile phone, you're over here pressing buttons, you're on your laptop, you're over here pressing buttons, because you want to see Amazon.com over here, or you want to watch a YouTube video over here, right? That's what you're out here doing, trying to live your best life, right? So as you're pressing buttons, you're actually sending a bunch of ones and zeros across the ether or across the wire. Ones and zeros. They're physically moving across these mediums right here. If you're on mobile, your ones and zeros travel through the air and they hit this access point, which then converts the ones and zeros to put them on a physical wire and send them down into the switch. If you're on a hardwired connection like a PC and you're pressing buttons to get access to YouTube or Amazon or Google, it sends those ones and zeros directly into the switch. And what the switch actually does, the switch says, hey, I recognize both of these devices. They're allowed to be in this network. I'm going to let you communicate to try to get on out here to the wild, wild internet, right? Now, everything from the switch back to your mobile devices, this is called your LAN, your local area network. Your switch manages all the devices within your network that are trying to reach out and communicate with the internet. And how it recognizes this stuff is by it keeps essentially a record of the MAC addresses that are associated with these devices. Now, after it collects all the ones and zeros saying, hey, I want to go out there and reach the internet, it then passes it off to the router. The router then takes those ones and zeros and says, hey, you want to go to Amazon, you want to go to YouTube. Okay, let me slap a quote unquote destination label on top of these ones and zeros. So I guess the best way you could think of this like a package that you are dropping off at the post office that you're trying to mail to a friend. You box the package up. Inside the box are all your ones and zeros. At the post office, they go ahead and print a label out, slap a label on the box and throw it in the back to prepare for it to be shipped. This is what the router essentially does. It takes your ones and zeros that have been handed off from the switch and prepares it to get a destination label slapped on it so your ones and zeros can go to their appropriate destination so that you can interact with the internet. So after the router does that, the router then sends that information to the modem, and modem stands for modulate, demodulate. So what the modem actually does, depending upon the type of internet connection that you are paying for that's coming into your house, it's going to take those ones and zeros that have been packaged up by the router and put them in the digital equivalent of an Amazon Blue Truck. So you're like, wait a second, what do you mean? So when the Amazon guy goes to pick up your packages from the warehouse, they put the packages into the Amazon Blue Truck, and next thing you know, you see the Amazon Blue Trucks driving all around the city to deliver the packages. This is what the modem essentially does. Now, how this works is like this. So you may have a fiber connection, you may have cable internet, you may have DSL, you may have satellite, or you may have RF. line of sight, or radio frequency internet. Depending upon what type of internet connection that you have that you are paying for to go to your house is going to determine the speeds that your ones and zeros are going to travel back and forth across the internet. So you could think of it like this. Here we are at the Amazon warehouse or the post office, and we're getting ready to ship these packages out, our ones and zeros that are in the box with their shipping label on it, right? If we have satellite internet, just imagine that I'm taking my package of ones and zeros and I'm putting them inside of a garbage truck that can only travel 45 miles per hour. Well, the garbage truck signifies my internet connection, and the 45 miles per hour signifies as to how fast my connection can actually push the ones and zeros across the wire for me to establish connection with whatever website that I'm trying to interact with. And we all know garbage trucks are pretty slow, and the slowest internet connection up on here would be satellite. So think of satellite as your garbage truck. Now, let's just say you have a fiber connection. Well, just imagine you're going into the modem or you're going into your garage and you see a Ferrari sitting in the garage. Well, Ferraris are pretty fast vehicles. So just imagine that your fiber connection is the Ferrari, and you throw your packages into the Ferrari and you want to get your packages across town. Let's just imagine that there are no speed limits on the highway. Well, that Ferrari is going to be able to get up and get it at really fast speeds in comparison to that of a garbage truck, aka your satellite connection. So essentially, the modem is basically the means for how fast it's going to allow your ones and zeros to travel across the wire so that you can interact with whatever website that you're trying to interact with by the time you hit the enter button on your computer and you request to watch a YouTube video, and by the time that thing comes back to you so you can watch that video. Your modem and your internet connection are going to dictate how fast those speeds are actually moving, okay? And then finally, everything that's within this blue line right here, this represents your actual network right here. This is your actual network that you are trying to get to communicate with another network out here somewhere, whatever website that you're trying to visit and do whatever it is that you're trying to do on the internet. All right. So this is just a very simple explanation as to how the internet works. I'm not trying to go into super detail about how to program all this stuff up. I just want those of you who are new to IT just to understand what these components actually do. So we have our mobile device. We have our desktop computer. Our desktop computer has a hardwired connection to the switch. Our mobile device is connected to an access point. The access point is hardwired to a switch. The switch is then hardwired to a router, and the router is connected to the modem. The switch pretty much controls all the devices that are trying to connect to the internet. The router essentially takes the ones and zeros that these devices are transmitting and slaps destination labels on the ones and zeros so that your ones and zeros can reach their appropriate destination to whatever website that they're trying to go to. The modem is basically the means of transportation for how fast your ones and zeros are going to be traveling across the wire, depending upon what type of internet connection you have coming to your house. If you have fiber, you have the fastest internet connection possible. If you have satellite, you have probably the slowest internet connection possible. So that is essentially what the modem does. But like I said earlier, most of you guys don't have a separate access point. You don't have a separate switch. You don't have a separate router. Most of y'all probably just have a wireless router and a modem in your house, and the access point, the switch, and the router. These things are typically combined to form what is called a SOHO router, or a small office home office router. So in a nutshell, ladies and gentlemen, this is essentially how the internet works in a very super simplified explanation. So hopefully you learned something from this. In the future, I'll probably be making more videos explaining how each of these actual components work in a little bit more detail. But this is really just for those of you who are just learning about IT, and you've been watching my videos in my IT fundamentals course or my A+ course, and you've been hearing me throw these terms around: access points, switches, routers, modems. Well, this is how all of these components actually come together, which allow for you to communicate with the internet through your phone or through your laptop or through your desktop computer.
In the realm of IT networking, well-defined organizational processes and procedures are crucial to maintaining stability, security, and efficiency. And the CompTIA Network Plus exam emphasizes the importance of various documentation methods, lifecycle management strategies, change management, and configuration management in enterprise networking. And in this video, we're going to provide an in-depth look at these essential organizational procedures. All right, so let's begin by talking about documentation. So, proper documentation, this is the backbone of an efficient IT infrastructure. It ensures seamless troubleshooting, smooth onboarding for new IT staff, and compliance with industry regulations. And there are several key documentation types that exist in a structured networking environment. So, first, let's talk about physical and logical diagrams. So, physical diagrams, they represent the physical layout of network devices, including routers, switches, firewalls, and cabling, and these are useful for hardware installation, maintenance, and troubleshooting. Then we have what are called logical diagrams, where they depict the logical flow of data through a network, showing VLANs, IP addressing schemes, and network segmentation. And these are essential for understanding how traffic moves across the network. Next, we have what is called a rack diagram. And a rack diagram, this shows the physical arrangement of networking equipment within a rack. And these diagrams help IT staff efficiently organize, install, and troubleshoot hardware while ensuring proper airflow and cable management. Then we have cable maps and diagrams, and these illustrate the interconnectivity between devices, including fiber optic runs, patch panels, and structured cable layouts. And these documents prevent misconfigurations and they speed up repairs when connectivity issues arise. And then we have what are called network diagrams, and they provide a structured view of network components and their interconnections. And they are classified into 3 layers. So you have layer 1, the physical layer. This displays the physical connections of network devices such as Ethernet cables and fiber optic links. You have layer 2, or the data link layer. This illustrates MAC addresses, VLANs, and layer 2 switches, aiding in troubleshooting broadcast domains and segmentation issues. And then you have layer 3, or the network layer, and this represents IP address assignments, subnetting, and layer 3 routing paths that are essential for understanding network traffic flow. Next, we have what is called an asset inventory. So tracking network assets, this helps organizations manage resources effectively. And an asset inventory includes hardware, which is used for cataloging network devices, such as routers, switches, servers, and endpoints. You got software that's used for maintaining records of installed applications and operating systems. You got licensing. This is where you keep track of software licenses to ensure compliance and avoid legal repercussions. And then you have warranty support. This is for monitoring warranty and support agreements to schedule timely hardware replacements. And then we have what is called IP address management. So this tool assists in managing and allocating IP addresses, tracking subnets, and avoiding conflicts. And they streamline IP address assignment and aid in DHCP and DNS administration. Next, you have what is called an SLA, or a service level agreement. And this is a formal contract between service providers and clients defining expected performance levels. And key SLA components include the following, such as uptime guarantees, you got response and resolution times for incidents, and then you got performance metrics and penalties for non-compliance. You also have what is called a wireless survey, or a heat map, and this assesses the strength and coverage of a Wi-Fi network. And the heat map, this visualizes signal strength across different areas, helping admins optimize access point placement and eliminate dead zones. All right, so let's move on and talk about the life cycle management. So life cycle management, this ensures that network components are adequately maintained, upgraded, and retired at appropriate times. And the first aspect of the lifecycle management is the end of life and end of support. So end of life, this marks when a product is no longer manufactured or sold. And then end of support, this indicates when a vendor stops providing updates, patches, and security fixes for a product. So IT teams, they must plan for EOL and EOS transitions to prevent security vulnerabilities and compatibility issues. Next, there's software management. So keeping software up to date is crucial for security and performance. And this includes regularly applying security patches to mitigate vulnerabilities, also ensuring that servers and endpoints run on supported operating system versions, and keeping network devices firmware current to enhance performance and security. Then you have what is called decommissioning, and this is the structured process of safely removing outdated hardware and software. And this includes data backup and secure data wiping, hardware disposal or recycling, and revoking device access from network resources. All right, next let's talk about change management. So change management, this ensures that all modifications to the network follow a structured approval and implementation process. And part of that is the request process tracking or service requests. So a structured request tracking system allows IT teams to document, approve, and review network changes. And this prevents unauthorized modifications and reduces downtime risks. And then there is configuration management, and this involves maintaining consistency in network settings and documentation. And within that, you have production configuration, and this is the current active configuration of network devices that should be carefully documented and managed. You have backup configurations, so regular backups of network configurations. This helps in disaster recovery and quick restoration in case of failures. Then you have what is called the baseline or the golden configuration. In the golden configuration, this serves as a standard reference configuration for devices, ensuring consistency and simplifying recovery processes. All right, so in conclusion, understanding and implementing organizational processes and procedures and network management, this is vital for maintaining efficiency, security, and compliance. And the CompTIA Network Plus exam emphasizes these best practices to help IT professionals streamline network operations. So proper documentation, lifecycle management, change management, and configuration management. This ensures that networks remain resilient and scalable in the long run. All right, now with all of that being said, let's do some check on learning. So the first question is, which of the following documentation types provides a visual representation of how devices are physically connected within a network? Is this a logical network diagram, a rack diagram, a layer 3 network diagram, or an asset inventory? And the correct answer is this is a rack diagram. So a rack diagram, this is a physical representation of how network and server equipment are arranged in a data center or networking closet. It details the placement of hardware components such as switches, routers, and servers within network racks. In contrast, a logical diagram, this focuses on network relationships and traffic flow. And a layer 3 network diagram illustrates IP routing and subnet segmentation. Asset inventory, this tracks hardware and software, but does not provide a visual layout. Next question, what is the primary purpose of change management in an organization's IT infrastructure? Is it to track software updates and bug fixes? Is it to ensure that all network documentation is properly stored? Is it to standardize the process of requesting, reviewing, and implementing changes? Or is it to enforce network security policies? And the correct answer is it is to standardize the process of requesting, reviewing, and implementing changes. So change management ensures that modifications to an IT environment follow a structured and well-documented process to minimize disruptions. This includes tracking service requests, obtaining approvals, and testing before deployment. While software updates and bug fixes are part of software management and documentation is essential, neither directly encompasses change management's role. Enforcing network security policies, this is a security function rather than a change management process. And our final question, a company wants to monitor and allocate IP addresses dynamically while keeping a record of all assigned addresses. Which of the following tools should they implement? Would this be a network diagram, a service level agreement, an IP address management, or a wireless heat map? And of course, the obvious answer is IP address management or IPAM. So IP address management, this is used to track, manage, and allocate IP addresses dynamically, ensuring efficient utilization of network resources. A network diagram, this provides a layout of network components, but does not manage IP addresses. A service level agreement, this defines service expectations, but does not handle IP address allocation. And a wireless heat map, this is used for analyzing Wi-Fi coverage and signal strength, not IP address management. In modern IT environments, maintaining optimal network performance, security, and reliability, this requires effective network monitoring. And as networks grow more complex, organizations must deploy advanced monitoring technologies to ensure smooth operations, identify anomalies, and preemptively address potential threats. And in this video, we're going to discuss the methods and solutions used in network monitoring. By understanding these concepts, IT professionals, they can effectively manage networks and enhance organizational security. All right, so let's begin by talking about Simple Network Management Protocol, or SNMP. So, SNMP, this is a widely used protocol for monitoring network devices, collecting status information, and managing network performance. It operates via an agent-based architecture where network devices communicate with an SNMP manager. And the key components of SNMP are as follows. So, you have what are called traps, and these are notifications that are sent by an SNMP agent to alert network administrators of significant events like device failures or high CPU usage. You have what is called the management information base, and this is a structured database that stores device information, including performance metrics and configurations. You have two different versions of SNMP. You got SNMP version 2C, and this adds support for bulk data retrieval but lacks strong security. Then you have version 3, where this enhances security with authentication and encryption. Another component is called community strings, and these are password-like tokens that grant permission to access SNMP data. And then you have authentication, and this is used in SNMP version 3 to prevent unauthorized access and data manipulation. All right, next we have what is called flow data analysis. So flow data, this provides insights into traffic patterns and device communication within the network. It includes information on source and destination IPs, port numbers, and protocol usage. And some popular flow monitoring technologies are as follows. So you have NetFlow from Cisco, SFlow, which stands for sample flow, and IPFix, or IP flow information export. And flow data, this basically helps network administrators analyze bandwidth utilization, detect anomalies, and optimize network traffic. Next, we have what is called packet capture. So packet capture tools, they collect raw network traffic for in-depth analysis. And this method is crucial for troubleshooting network issues like latency and packet loss, investigating security breaches like detecting unauthorized communications and deep packet inspection, and also for optimizing network performance. And tools like Wireshark, TCP dump, and Zeek, they help analyze captured packets, providing insights into network behavior. All right, next we have baseline metrics and anomaly detection. So establishing baseline performance metrics. This allows IT teams to detect deviations that indicate potential issues. So you have your baseline metrics, and these are normal traffic patterns, latency, bandwidth utilization, and device response times. Then you have anomaly alerting or notifications. So automated alerts, they trigger when performance deviates from the baseline. And examples could include high CPU usage, excessive bandwidth consumption, and unusual traffic patterns. Next, we have what is called log aggregation, and this centralizes logs from various network devices, simplifying analysis and improving security monitoring. So you have what is called a syslog collector, and this is a central repository that collects and processes log data from firewalls, routers, and switches. Then you have what is called a security information and event management, or a SIEM, and this is an advanced platform that aggregates, correlates, and analyzes log data for security monitoring. And some examples of a SIEM product are Splunk, Elk Stack, IBM QRadar, and Microsoft Sentinel. All right, next we have what are called APIs, or application programming interface integration. So modern network monitoring solutions, they leverage APIs to automate data collection and reporting, integrate with SIEM and other security tools, and improve scalability and customizability of monitoring solutions. And APIs, they facilitate seamless interaction between monitoring platforms and third party, enhancing overall network visibility. Then we have what is called port mirroring, and this is also known as span switch port analyzer. And this duplicates network traffic from one port to another for monitoring purposes, and is used for troubleshooting, intrusion detection, and performance analysis. And it is often implemented in switches to analyze live network traffic without affecting production performance. All right, so let's move on and talk about some network monitoring solutions. And the first one we're going to talk about is called network discovery. So network discovery tools, they help admins identify active devices and monitor their status. You have what is called ad hoc discovery. And this is when you manually scan a network using tools like Nmap or Angry IP Scanner. And then you have what is called a schedule discovery. And these are automated network scans using enterprise monitoring tools like SolarWinds and PRTG. Next, we have what is called traffic analysis, and these are tools that examine data flows to identify performance bottlenecks and security threats. And deep packet inspection, this can reveal detailed information about application usage and protocol behaviors. And some popular traffic analysis tools are tools like Wireshark that are used for detailed packet analysis, NTO-PNG, which provides real-time visualization, and Cisco NetFlow Analyzer, which provides flow data analysis. Next, we have performance monitoring, and this focuses on evaluating network speed, latency, and resource utilization. Its key metrics are bandwidth usage, network latency, packet loss, and jitter. And some popular tools are SolarWinds NPM for enterprise-grade monitoring, and Zabbix, which is a free and scalable solution. Then we have availability monitoring, so ensuring network devices and services are always accessible. This is crucial for business continuity. So you have what is called ICMP ping, and this is your basic uptime check. You have SNMP polling, and this is for regular device health checks. And you have synthetic monitoring, and this is used for simulating user interactions to detect application availability issues. And some availability monitoring tools include PRTG Network Monitor, Datadog, and Site 24/7. All right, next we have configuration monitoring. So configuration monitoring tools track changes in network device configurations to maintain compliance and security. They detect unauthorized changes to firewall rules, router settings, and switch configurations. They prevent misconfigurations that can lead to downtime or vulnerabilities. And they automate backups of network configurations for disaster recovery. And some example tools include the following, such as Cisco Prime Infrastructure, SolarWinds Network Configuration Manager, and Manage Engine Network Configuration Manager. All right, so in conclusion, effective network monitoring, this is essential for maintaining a secure and high-performance IT environment. And by leveraging SNMP, flow data analysis, packet capture, log aggregation, and API integration, IT professionals, they can gain deep insights into network health. Additionally, employing solutions like traffic analysis, performance monitoring, and configuration management, this ensures robust network visibility and security. And mastering these technologies will not only help you pass the CompTIA Network Plus exam, but also empower you to become a proficient network administrator. And implementing these best practices, this will significantly improve your ability to manage and secure modern network infrastructures. All right, now with all of that being said, let's do some check on learning. So the first question is, a network administrator wants to monitor traffic and identify unusual patterns that may indicate a potential security threat. Which network monitoring method would best provide real-time anomaly detection? Would this be packet capture, baseline metrics, port mirroring, or flow data? And the correct answer is this will be baseline metrics. So baseline metrics, they help establish normal network behavior and are used to detect anomalies through alerting and notification mechanisms. And by continuously monitoring traffic patterns, any deviation from the baseline can trigger alerts, helping admins identify potential threats in real time. Next question. Which of the following simple network management protocol versions provides authentication and encryption for secure network monitoring? Is it SNMP version 1, SNMP version 2C, SNMP version 3, or SNMP community strings? And the correct answer is SNMP version 3. So SNMP version 3, this is the most secure version of SNMP, offering authentication and encryption features to protect network management data. In contrast, version 1 and version 2C, they lack security mechanisms, making them vulnerable to interception and unauthorized access. And our final question, a network engineer needs to aggregate logs from multiple devices and analyze them for security incidents. Which solution is best suited for this task? Would this be a syslog collector, port mirroring, SNMP traps, or network discovery? And the correct answer is this will be a syslog collector. So a syslog collector, this is used to centralize and aggregate logs from various network devices, enabling admins to analyze logs efficiently. When integrated with a security information and event management system, it enhances security monitoring by correlating logs and identifying potential threats. Disaster recovery. This is an essential component of any organization's IT strategy. It involves preparing for, responding to, and recovering from incidents that can cause data loss, service disruptions, or hardware failures. And the goal of disaster recovery is to minimize downtime and data loss while ensuring business continuity. And the CompTIA Network Plus exam covers several key disaster recovery concepts, including disaster recovery metrics, sites, high availability approaches, and testing methods. And in this video, we're going to provide an in-depth explanation of these topics to help IT professionals understand how to implement and manage disaster recovery strategies effectively. All right, so let's begin by talking about disaster recovery metrics. So disaster recovery metrics are crucial for measuring the efficiency and effectiveness of recovery plans. And these metrics help organizations define their expectations for recovery in terms of time and data loss. And the first aspect we're going to talk about is called RPO, or Recovery Point Objective. So RPO, this defines the maximum amount of data loss an organization can tolerate. It determines the frequency of backups needed to minimize data loss in case of a disaster. So an example, if an organization has an RPO of 4 hours, it means that backups must occur at least every 4 hours to ensure minimal data loss. And the use case for this would be businesses with critical data, such as financial institutions. They typically require lower RPOs to prevent significant data loss. The next aspect is RTO, or the Recovery Time Objective, and this specifies the maximum acceptable downtime after a disaster before services must be restored. So for example, if an e-commerce website has an RTO of 1 hour, it must be back online within 1 hour after a disaster. And the use case for this would be organizations with high uptime requirements like online banking, where they need low RTOs to minimize service disruption. Next, we have what is called the mean time to repair. And this measures the average time required to repair and restore a failed system. So for example, if a server crashes and takes an average of 3 hours to fix, the MTTR is 3 hours. And the use case for this will be the MTTR. This is essential for evaluating the efficiency of IT support teams in resolving system failures. Then we have the MTBF, or the mean time between failures. And this is the predicted time between one failure and the next in a system. So as an example, if a hard drive is expected to fail every 2 years, its MTBF is 2 years. And a use case for this will be organizations that use MTBF to estimate when hardware replacements or preventative maintenance should occur. All right, next let's talk about disaster recovery sites. So organizations that use disaster recovery sites to ensure business continuity in case of a disaster. And these sites vary in terms of cost and recovery speed. So the first type of site is that of a cold site. And this is a backup facility that has infrastructure in place but lacks active computing resources such as servers and storage. And its pros are it's cost effective and is suitable for businesses with high RTOs. The cons, it can take a long time to become operational, and it requires hardware and software installation after a disaster. So as an example, this would be a company that rents an empty data center with power and cooling, but it needs to install servers and restore data before it can be in full operational use. Next is that of a warm site, and this is partially equipped with some hardware, software, and network infrastructure, but requires additional setup to become fully operational. The pros, it offers faster recovery than a cold site, and it balances cost and recovery speed. The cons, it is more expensive than a cold site, and it may still require data restoration and system configuration. An example would be a secondary data center with pre-installed servers, but requires data synchronization and application setup after a disaster. And then we have what is called a hot site. And this is a fully operational backup site that mirrors the primary site and can take over operations almost immediately. The pros, it has very minimal downtime. It's ideal for mission critical operations. Its cons, it's expensive to maintain and requires continuous synchronization. An example of this would be a bank that maintains a hot site that automatically replicates transactions from the primary site, allowing instant failover. All right, so let's move on to talk about high availability approaches. So high availability, this ensures that IT systems remain operational with minimal downtime. In organizations, they use active-active and active-passive approaches to achieve this. So let's talk about the active-active configuration. So in an active-active setup, Multiple systems run simultaneously, sharing the workload. If one system fails, the remaining systems continue to operate without service disruption. The pros are this maximizes resource utilization and provides seamless failover. The cons, it is more complex to manage and it requires higher infrastructure costs. An example of this would be a load balanced web application that's running across multiple data centers where traffic is evenly distributed. And then we have the active passive configuration. So in an active passive setup, one system is active that handles operations while the other is passive and remains on standby. And the passive system takes over only if the active system fails. The pros, this is easier to configure and maintain, and it reduces the risk of data conflicts. The cons, its passive system remains idle until needed, and failover may cause a brief service interruption. An example of this would be a database server with a backup instance that activates only when the primary server fails. All right, so let's move on and talk about disaster recovery testing. So regular testing, this is essential to ensure that disaster recovery plans work as intended. In organizations, they use different testing models to validate their disaster recovery strategies. And the first type of test is called a tabletop exercise. And this is a discussion-based test where team members review and simulate disaster scenarios. The pros, this identifies gaps in the disaster recovery plan, and it is cost-effective and easy to conduct. The cons, it does not validate technical implementation and it relies on assumptions rather than real-world execution. An example of this would be the IT team that discusses a simulated cyber attack scenario and then evaluates response procedures. And then we have what is called a validation test. And this involves executing parts of the disaster recovery plan to ensure systems function correctly after a failover. The pros, this confirms that recovery processes work as expected, and it also provides real-time assessment of failover capabilities. The cons, this may disrupt normal business operations, and it requires resources and planning. So an example of this would be an organization that tests its backup site by redirecting network traffic to verify system functionality. All right, so in conclusion, disaster recovery. This is a fundamental aspect of IT management, ensuring that businesses can quickly recover from system failures, cyber attacks, and natural disasters. Understanding key disaster recovery metrics, selecting the appropriate disaster recovery site, implementing high availability strategies, and conducting regular testing, all of this is crucial for a successful disaster recovery plan. So for CompTIA Network Plus candidates, mastering these concepts will enhance your ability to design and implement effective disaster recovery solutions. And by applying these best practices, IT professionals, you all can minimize your downtime, protect critical data, and maintain business continuity, even in the face of unexpected disruptions. All right, so with all that being said, let's do some check on learning. So the first question, which disaster recovery metric defines the maximum acceptable amount of data loss measured in time? Is it the recovery time objective, the mean time between failures, the recovery point objective, or the mean time to repair? And the correct answer is this will be the recovery point objective. So the RPO, this determines the maximum acceptable amount of data loss in terms of time. It defines how far back in time data must be recoverable after an outage. So for example, if an organization has an RPO of 4 hours, data backups should occur at least every 4 hours to ensure minimal loss in case of a disaster. Next question. A company requires a disaster recovery site that is fully operational with up-to-date data and can immediately take over in the event of a failure. Which type of disaster recovery site best meets this requirement? Would this be a cold site, a warm site, a hot site, or backup tape storage? And the correct answer is this will be a hot site. So a hot site, this is a fully functional, continuously updated disaster recovery site that can immediately assume operations if the primary site goes down. It minimizes downtime and data loss, but it is the most expensive option. In contrast, a cold site, this requires extensive setup before use, and a warm site is partially operational but needs some updates before going live. And our final question, which high availability approach involves multiple systems running simultaneously, sharing the workload to ensure continuous availability? Would this be active-passive, active-active, mean time to repair, or a tabletop exercise? And the correct answer is active-active. So in active-active configuration, this ensures that multiple systems operate concurrently, distributing workloads to enhance performance and availability. If one system fails, the other continues to handle traffic seamlessly. In contrast, an active-passive setup, this has a secondary system on standby, only activating when the primary system fails. Networking. This relies on fundamental services that facilitate communication, security, and efficient management of devices in an IP version 4 and IP version 6 environment. In the CompTIA Network Plus exam, it emphasizes the need to understand and implement these network services. And in this video, we're going to explore dynamic addressing, name resolution, and time protocols, providing a thorough guide to their implementation. All right, so let's go ahead and talk about dynamic addressing. So dynamic addressing, this allows network devices to obtain an IP address automatically, reducing manual configuration errors and improving scalability. And the two primary methods are DHCP for both IP version 4A and IP version 6, and stateless address auto configuration for IP version 6. So let's go ahead and talk about DHCP. So DHCP, this dynamically assigns IP addresses, subnet masks, gateway addresses, and DNS settings to devices. And it operates using a lease-based system, ensuring addresses are reclaimed when no longer in use. And here are some of the key concepts of DHCP. So you have reservation. So a DHCP reservation, this assigns a specific IP address to a device on its MAC address. And this is useful for devices requiring static IPs such as servers and printers. Then you have a scope. So a scope, this defines the range of IP addresses available for distribution. And each subnet typically has a unique DHCP scope. Next, you have what is called the lease time. So the lease time, this determines how long a device retains its assigned IP before requesting renewal. And shorter leases, they work well for high turnover environments like public Wi-Fi, while longer leases are better for stable networks. Then you have DHCP options that provide additional configuration parameters such as the default gateway, DNS servers, NTP servers, and Pixie boot, which is used for network booting. Then you have the relay or IP helper. So in larger networks, DHCP relay agents, which are also called IP helpers, they forward DHCP requests between subnets, allowing a centralized DHCP server to serve multiple networks. And then you have exclusions. So DHCP exclusions, they define addresses within the scope that should not be assigned dynamically. And these are typically reserved for static assignments. All right, next let's quickly talk about the stateless address auto configuration, or SLAC. So SLAC, this is an IP version 6 exclusive method allowing devices to configure themselves automatically, and it relies on router advertisements from a router to assign a unique global unicast address without requiring a DHCP server. And SLAC, this operates by combining the network prefix with a host interface identifier or some randomly generated ID. All right, so let's move on and talk about name resolution. So this maps human readable domains to an IP address, and the two primary methods are DNS and host files. So let's talk about DNS, which is the domain name system. And this translates domain names to IP addresses using a hierarchical structure. And DNS records, they store essential information about domains. And here are some of the record types. So you have what is called an A record, and this maps a domain to an IP version 4 address. You have what is called a quad A record, and this maps a domain to an IP version 6 address. You got the CNAME record. This creates an alias for a domain. You got the mail exchange record, and this defines mail servers for email routing. You have what is called a text record. This stores arbitrary text, which is commonly used in SPF or sender policy framework, and DKIM, which stands for domain keys identified mail. You have what is called the NS record, or the name server record, and this identifies authoritative DNS servers for a domain. And then you have the pointer record, and this performs reverse lookups, mapping an IP address to a host name. Then we have various DNS zone types. So the first one is called a forward lookup zone, and this resolves domain names to IP addresses. You have what is called a reverse lookup zone, and this resolves IP addresses to domain names. Then you have what is called an authoritative versus non-authoritative DNS, and the authoritative DNS servers store original domain information, while the non-authoritative DNS server caches query requests. Then you have the primary versus secondary DNS, and the primary DNS server holds the original records, and the secondary DNS server provides redundancy through replication. And then we have what is called a recursive DNS query, and this is when DNS resolvers fetch records from authoritative servers if they don't already have cached data. And then you have what is called the secure DNS implementation. And the first one is the domain name system security extension. So this adds cryptographic signatures to DNS records, preventing spoofing. And then we have what is called DNS over HTTPS and DNS over TLS. And this encrypts DNS queries to prevent eavesdropping and tampering. And then we have what is called a host file. So the host file, this is a local text file that maps IP addresses to domain names. Although largely replaced by DNS, it is useful for testing and overriding domain resolutions locally. All right, next let's talk about time protocols. So accurate time synchronization, this is crucial for authentication, logging, and network operations. And the main time synchronization protocols include NTP, PTP, and NTS. So let's go ahead and talk about them. So the first one is NTP, or Network Time Protocol, and this synchronizes clocks across devices using a hierarchy of time sources, and it ensures accurate timestamps for network logs, authentication, and scheduling. Then you have what is called PTP, or Precision Time Protocol, and this provides higher accuracy than NTP, making it ideal for financial transactions, industrial automation, and telecommunications, and it synchronizes devices within nanoseconds by accounting for network latency. And finally, you have what is called NTS, or Network Time Security. And this is a security extension for NTP that protects against spoofing and man-in-the-middle attacks. And it uses transport layer security to ensure time synchronization integrity. All right, so in conclusion, proper implementation of IP version 4 and IP version 6 network services. This ensures efficient device communication, security, and network management. DHCP, this automates IP assignment, while Slack provides a lightweight alternative for IP version 6. DNS ensures seamless name resolution with secure implementations like DNS security and DOH/DOT enhancing security. And finally, time protocols like NTP, PTP, and NTS, they maintain network synchronization, which is crucial for security and logging. So mastering these concepts is essential for networking professionals preparing for the CompTIA Network Plus exam and real-world network administration. All right, now with all of that being said, let's do some check on learning. So the first question is, a network admin wants to ensure that specific devices always receive the same IP address from the DHCP server. Which DHCP feature should be used? Would this be the DHCP lease time, scope, reservation, or relay? And the correct answer is the DHCP reservation. So a DHCP reservation, this ensures that a specific MAC address always receives the same IP address from the DHCP server. And this is commonly used for network devices like printers and servers that require a constant IP address. Other DHCP features like lease time, they determine how long a device can hold an IP address before renewal. Scope defines the range of available IPs. And relay, this helps forward DHCP requests between different subnets. Next question. Which of the following DNS record types is used to map an IP version 6 address to a domain name? Would this be A, MX, CNAME, or Quad A? And the correct answer is this will be a Quad A record. So this is used to map a domain name to an IP version 6 address. And this is similar to an A record, which maps a domain name to an IP version 4 address. Other DNS record types include the mail exchange for email servers, the canonical name or the CNAME for aliasing one domain to another, and the name server for identifying authoritative DNS servers. And our final question, which protocol is used to synchronize time across network devices with high accuracy? Would this be DNS security, NTP, DOH, or Slack? And the correct answer would be NTP, or Network Time Protocol. So this is used to synchronize time across network devices with high accuracy, ensuring that all systems on the network have the correct time. Precision Time Protocol, this offers even greater precision for time-sensitive applications. DNS security, this secures DNS transactions. DOH, which is DNS over HTTPS, this encrypts DNS queries. And SLAC, which stands for Stateless Address Auto Configuration, this is used for automatic IP version 6 addressing. As businesses grow and networks expand, IT professionals need to implement robust network access and management strategies to maintain security, efficiency, and control. Various methods such as VPNs, remote access technologies, and management approaches, all of this helps organizations manage their networks effectively. And in this video, we're going to explore the different network access and management methods that are covered in CompTIA Network Plus Exam Objective 3.5, including VPN types, connection methods, jump hosts, and in-band versus out-of-band management. All right, so let's begin by talking about VPNs. So VPNs, these are essential tools that enable secure remote access to networks by encrypting data transmissions over public or private networks. There are two primary types of VPNs. You have site-to-site and client-to-site. So let's talk about a site-to-site VPN. So a site-to-site VPN, this is used to connect entire networks at different physical locations securely over the internet. And this type of VPN is commonly used by organizations with multiple offices to ensure secure communication between branch offices and headquarters. And the primary characteristics of a site-to-site VPN include the following. So there's persistent connections. So there's always on connectivity between locations. There's encryption, where it uses security protocols such as IPsec or SSL TLS. There's network-based access, and this is when devices within the network do not require additional configuration. Then there's efficiency, where it reduces the need for individual VPN client configurations. And the common use cases for a site-to-site VPN are businesses that are connecting the branch offices to a central corporate network, secure communication between data centers, and government agencies linking regional offices to headquarters. All right, next we have what is called a client-to-site VPN, and this is also known as a remote access VPN. This enables individual users to connect securely to a network from remote locations. Now, unlike site-to-site VPNs, client-to-site VPNs require users to authenticate before gaining access. And within that, we have what is called a clientless VPN. And this allows remote users to access network resources through a web browser without needing a pre-installed VPN client. And this method is often used for quick and temporary access to internal web applications or cloud services. And it also typically employs SSL TLS encryption. And its advantages are you don't have to install any VPN software. It provides secure access through a web interface, and it is ideal for temporary or third-party access. Its disadvantage is it has limited access to network resources, and it may not support advanced applications requiring full network connectivity. And then you have what is called split tunnel and full tunnel. So VPN configurations, they can use split tunneling or full tunneling depending on security and performance requirements. And the split tunnel, this allows users to access the corporate network while directing non-corporate traffic directly to the internet. And the pros, this reduces bandwidth usage, improves speed, and allows local internet access. The cons, this can create security risks if non-corporate traffic is not secured. And then you have what is called a full tunnel, and this routes all traffic through the corporate network, providing increased security but potentially reducing speed. And the pros, this ensures all traffic is encrypted and monitored. And the cons, this increases bandwidth usage and can slow down internet access. All right, next let's talk about connection methods. So to access and manage networks effectively, IT professionals that use different connection methods, including secure shell, graphical user interfaces, APIs, and console access. So let's talk about secure shell. So secure shell, this is a secure protocol used to access and manage network devices remotely via an encrypted command line interface. And it is commonly used for secure remote administration of routers, switches, and servers. It's also used for file transferring using secure copy protocol or secure FTP. And it's also used for encrypted authentication and data exchange. And its advantage advantages is it offers secure and encrypted access, it's lightweight and efficient, and it supports automation via scripting. Its disadvantages, it requires knowledge of the command line interface, and it can be complex for beginners. Then you have what is called the graphical user interface, or the GUI, and this provides a visual interface for managing network devices and configurations. And many network management tools such as Cisco ASDM or the Adaptive Security Device Manager or web-based interfaces, they use GUIs. And the advantages are they're user-friendly and easy to navigate, they reduce the need for complex command line knowledge, and they provide visual data representation such as charts and logs. The disadvantages, they require more system resources, they may have security vulnerabilities if not updated regularly, and they have limited flexibility for automation. Next, we have the API, or the Application Programming Interface, and this allows automation and integration of network management tasks by enabling software applications to interact with network devices. The advantages, it facilitates automation of repetitive tasks, it enables integration with third-party tools, and it allows for scalable and efficient network management. The disadvantages, it requires programming knowledge, and it can introduce security risks if not properly secured. And then you have what is called the console access. So console access, this is the direct physical or remote connection to a network device via a serial or Ethernet interface. And it is often used for initial device configuration or troubleshooting. And the advantages are it provides direct access to network hardware. It's essential for troubleshooting when remote access is unavailable. And it is secure since it does not rely on the network for connectivity. The disadvantages are it requires physical presence or special remote access hardware, and it lacks automation capabilities. All right, so let's move on and talk about a jump box or a jump host. So a jump box, this is an intermediary device used to access and manage network resources securely, and it serves as a gateway between administrators and critical network infrastructure. Its benefits, it acts as a single entry point for accessing sensitive systems, it enhances security by limiting direct access to critical resources, and it enables logging and monitoring of access attempts. And its use cases are you can securely access internal network devices from an external location. It can restrict administrative access to specific users, and it protects sensitive assets from unauthorized access. And then we have what is called in-band versus out-of-band management. So network management, it can be categorized into in-band and out-of-band management based on the method of access. So let's talk about in-band management. So this refers to managing network devices using the primary network infrastructure. And examples of this include using SSH or a web-based GUI to configure routers and switches, managing cloud resources through a centralized dashboard, or running remote scripts via an API. And the advantages are it is convenient and easy to use, it allows centralized management of network devices, and it supports automation and remote troubleshooting. The disadvantages, it is susceptible to network outages, it requires active network connectivity, and it can have potential security risks if it is not properly secured. And then we have what is called out-of-band management, and this provides access to network devices through a separate dedicated management channel. And examples of this could be using a console server for direct hardware access, remote management through a cellular or dial-up connection, or accessing a jump box to configure network infrastructure. And the advantages are it ensures access during network failures, provides higher security by isolating management traffic, and it is essential for disaster recovery and troubleshooting. Now, its disadvantages are it requires additional infrastructure such as a separate network or cellular modem. It can be costly to implement, and it may be more complex to set up. So in conclusion, effective network access and management are crucial for maintaining a secure and efficient IT environment. VPNs, they provide encrypted connectivity for remote users and site-to-site communications, while Secure Shell, GUI, API, and console access, they offer flexible management options. Jump boxes, they enhance security by acting as a gateway to critical systems. And the choice between in-band and out-of-band management, this depends on an organization application security and availability requirements. Now, by understanding these concepts, IT professionals, they can implement the best access and management methods to ensure robust network security and operational efficiency. And mastering these topics, this is essential for those pursuing the CompTIA Network Plus certification and for professionals managing enterprise networks in real-world scenarios. So now that we got that out of the way, let's do some check on learning. So the first question is, which of the following best describes a clientless VPN? Is this a VPN connection that requires a dedicated VPN client software installed on the user's device? Is this a VPN that requires split tunneling to function properly? Is this a VPN that can only be used with SSH connections? Or is this a VPN that allows users to connect through a web browser without installing additional software? And the correct answer is this is a VPN that allows users to connect through a web browser without installing additional software. So a clientless VPN allows users to securely access resources through a web browser without needing to install a dedicated VPN client. And this is often used for remote access to web applications or internal company portals while still providing encryption and authentication mechanisms. Next question. What is the primary difference between in-band and out-of-band management? Is it in-band management requires an admin to be physically present, while out-of-band management allows remote administration? Is it in-band management is used for encrypting network traffic, while out-of-band management is for firewall rules? Is it in-band management occurs over the same production network as user traffic, while out-of-band management uses a dedicated network for administrative access? Or is it in-band management relies on an API, while out-of-band management requires a graphical user interface? And the correct answer is in-band management occurs over the same production network as user traffic, while out-of-band management uses a dedicated network for administrative access. So in-band management uses the same network that users and services operate on, meaning it can be affected by network congestion or failures. Out-of-band, on the other hand, it provides a separate dedicated management channel, such as a serial console or remote access through a jump box to manage devices, even if the primary network is down. And our final question, which of the following is a secure remote access method that provides an encrypted text-based interface for managing network devices? Is this Telnet, SSH, RDP, or API? And the correct answer is SSH or Secure Shell. So this is a protocol that provides encrypted remote command line access to network devices. Now, unlike Telnet, which transmits data in plain text, SSH encrypts the communication to ensure security, and it is commonly used for configuring and managing network devices remotely. In today's interconnected digital world, network security is paramount to ensuring the integrity, confidentiality, and availability of data. And the CompTIA Network Plus exam emphasizes fundamental network security concepts that IT professionals need to protect networks against ever-evolving threats. In this video, we're going to explore the importance of these concepts, including logical and physical security measures, deception technology, security terminology, compliance requirements, and network segmentation enforcement. Let's begin by talking about logical security, and we're going to focus on encryption real quick. So encryption, this is a critical component of network security, ensuring that sensitive data remains confidential and protected from unauthorized access. And within that, we have two components. We have data in transit, and this refers to data actively moving across the network, such as emails, voice over IP communications, and file transfers. And transport layer security and secure shell protocols, they help encrypt data in transit, which reduces the risk of interception. Then we have data at rest, and this is data that is stored on devices such as servers, hard drives, or cloud storage that should be encrypted using techniques like advanced encryption standard to protect against unauthorized access in case of a breach. Next, we have what are called certificates, and certificates, they authenticate users and systems, helping to establish trust in a network environment. And within that, you have what is called public key infrastructure, and this provides a framework for managing digital certificates and encryption keys, ensuring secure communications and authentication. And then you have what are called self-signed certificates. Now, unlike PKI-based certificates that are issued by a trust authority, self-signed certificates are created by organizations for internal use, typically for development or testing environments. All right, next we're going to talk about identity and access management and identity and access management frameworks. This helps manage user identities and enforce access policies. And within that, you have authentication. So this verifies a user's identity before granting access to network resources. You got multi-factor authentication. This enhances security by requiring multiple forms of verification, such as a password and a biometric scan. You have single sign-on. This allows users to access multiple applications with a single set of credentials, which reduces password fatigue and improves security. You have what is called Radius or Remote Authentication Dial-in User Service. And this is a centralized authentication system for remote users accessing a network. You have LDAP or the Lightweight Directory Access Protocol. And this is a protocol that is used to access and manage directory services such as user credentials. You have the Security Assertion Markup Language, and this facilitates SSO for web applications by allowing identity providers to pass authorization credentials to service providers. Then you have what is called TACACS Plus or the Terminal Access Controller Access Control System Plus. And this is a protocol that provides centralized authentication and authorization for remote devices. Then you have time-based authentication, and this is a method that uses time-sensitive one-time passwords for authentication, which is often seen in multi-factor authentication implementations. All right, next we have authorization, and this determines what an authenticated user is allowed to do. And within that, we have what is called least privilege, and this is where users are granted only the minimal access required for their role. And then we have what is called RBAC or role-based access control, and this assigns permissions based on user roles, ensuring consistent security enforcement. And then we have what is called geofencing, and this restricts access to networks based on geographical location, ensuring only that authorized users from a specific area can connect. All right, so let's move on and quickly talk about physical security, and we're going to talk about cameras and locks real quick. So while logical security protects digital assets, physical security prevents unauthorized access to hardware and infrastructure. And within that, we have cameras. So surveillance cameras, they monitor access points and they detect unauthorized activity. And then you have locks. So physical locks, they secure network infrastructure such as server rooms and data centers. Next, we have what are called deception technologies, and these help identify and analyze cyber threats by misleading attackers. And within that, we have what is called a honeypot, and this is a decoy system designed to lure attackers and collect information about their tactics. And then we have what is called a honeynet, and this is a network of honeypots that mimics an organization's infrastructure to detect and analyze cyber threats. All right, so moving on, we have common security terminologies. So understanding security terminology, this is essential for network security professionals. So the first term is that of risk, and this is the potential for loss or damage due to a security threat. You have vulnerability. This is a weakness in a system that can be exploited. You have an exploit. This is the actual method used by attackers to take advantage of a vulnerability. You have a threat. This is any event or action that can cause harm to a network or data. And then you have the CIA triad, which stands for confidentiality, integrity, and availability. And this is a fundamental security principle that ensures that data is protected, accurate, and accessible. All right, so moving on, we have audits and regulatory compliance. So regulatory frameworks, they help organizations comply with security standards. And within that, we have what is called data locality. And this refers to geographic locations where data is stored and the legal implications associated with it. Then you have what is called the PCI DSS or the Payment Card Industry Data Security Standard. And this is a set of security standards to protect credit card transactions. And then you have what is called the GDPR or the General Data Protection Regulation. And this is a European Union regulation that governs data privacy and protection. All right, and next we have network segmentation enforcement. So network segmentation, this improves security by isolating critical assets from less secure environments. And within that, we have the IoT or the Internet of Things and the industrial IoT. And these are devices connected to networks that must be secured with proper segmentation to prevent unauthorized access. Then you have SCADA, and that stands for Supervisory Control and Data Acquisition. You also have ICS, that stands for Industrial Control System. Then you have OT, that stands for Operational Technology. And all of these are critical infrastructure systems that require strict network segmentation to protect against cyber threats. Then you have what are called guest networks, and these provide separate network access for guests to prevent them from accessing sensitive internal systems. Then you have the concept of BYOD, or bring your own device, and these are policies that should enforce segmentation between corporate and personal devices to minimize security risks. All right, so in conclusion, understanding and implementing network security concepts, this is crucial for protecting data, infrastructure, and user privacy. And by securing networks with encryption, identity access management frameworks, physical security measures, deception technologies, and network segmentation, IT professionals, they can mitigate security threats and ensure compliance with regulatory standards. And the CompTIA Network Plus exam tests these essential security principles, helping candidates develop the skills necessary to secure modern networks effectively. Now, with all of that being said, let's do some check on learning. So the first question is, which of the following authentication protocols provide centralized authentication and authorization for remote users and supports multi-factor authentication? Would this be LDAP, Radius, SAML, or TACACS Plus? And the correct answer is Radius. So the remote authentication dial-in user service, this is a centralized authentication protocol used for remote users to access a network. It supports multi-factor authentication and allows for authentication, authorization, and accounting, or AAA. Now, while TACACS Plus is similar, it is used mainly for device administration rather than remote access. In LDAP, this is a directory service protocol. In SAML, this is used for SSO, or single sign-on authentication. Next question, which security principle ensures that users only have the permissions necessary to perform their job functions? Would this be SSO, RBAC, least privilege, or time-based authentication? And the correct answer is least privilege. So the principle of least privilege states that users and applications should only have the minimum access necessary to complete their tasks. This reduces the risk of unauthorized access and security breaches. RBAC, this grants permissions based on job roles, but it does not necessarily enforce the least privilege. And SSO, this allows users to authenticate once to access multiple resources. And time-based authentication, this restricts access based on time constraints, but does not focus on minimal access. And our final question, which of the following best describes a honeypot in network security? Is it a type of firewall that blocks malicious traffic? Is it a security control that isolates sensitive data? Is it a decoy system designed to lure attackers? Or is it a tool used for network segmentation? And the correct answer is it is a decoy system used to lure attackers. So a honeypot, this is a security mechanism that acts as a decoy system to lure cyber attackers. It is designed to detect, deflect, and study hacking attempts. It does not block traffic like a firewall, isolate sensitive data, or segment networks. Honeypots, they help organizations analyze attack techniques and improve their security defenses. In the ever-evolving landscape of cybersecurity, network attacks remain a constant threat to organizations and individuals alike. Now, understanding different types of network attacks and their impacts, all of this is crucial for IT professionals preparing for the CompTIA Network Plus exam. And in this video, we're going to explore various network attack methods, their mechanisms, and how they impact the security of networks. All right, so let's begin by talking about a denial of service attack, or a DOS attack. And this is a malicious attempt to disrupt the availability of a network, service, or application by overwhelming it with excessive requests. And this results in service degradation or a complete shutdown, preventing legitimate users from accessing resources. And some common DOS attacks include the following. So you have what is called a flood attack. And this is when large volumes of traffic overwhelm a network or a system. You have a SYN flood. This exploits the TCP handshake process to consume system resources. And then you have what is called the ping of death, and this sends oversized ICMP packets to crash a system. Next, we have what is called a DDoS attack, or a distributed denial of service attack. And this is a more sophisticated version of a DOS attack where multiple compromised devices known as botnets work together to flood a target system with malicious traffic. And the impacts of a DOS and DDoS attack are as follows. So both of them cause a disruption of business operations. There's financial losses due to downtime. There's resource exhaustion leading to system crashes. And there's reputational damage for the organizations. All right, so now let's move on to the next one, which is called VLAN hopping. And VLAN hopping, this is an attack where a threat actor gains unauthorized access to different VLANs by exploiting switch misconfigurations. And the type of VLAN hopping attacks are as follows. So you have what is called switch spoofing, and this is when an attacker configures a device to act as a trunking switch to access multiple VLANs. And then you have what is called double tagging, and this is when the attacker sends a packet with two VLAN tags, tricking a switch into forwarding the packet to a different VLAN. So here's the impact of VLAN hopping. So it lets people have unauthorized access to sensitive network segments. There's the potential for data interception and exfiltration. And there's the exploitation of network resources for further attacks. Next, we have what is called MAC flooding or media access control flooding. And this is an attack that overwhelms a network switch with a large number of fake MAC addresses, exhausting the switch's MAC address table and forcing it to act as a hub. And the impact of MAC flooding is as follows. So the switches, they fail to function properly, which results in degrading the network performance. Attackers, they can eavesdrop on network traffic, and there's the potential for further network attacks, such as an on-path attack. And then we have what is called an ARP attack or an address resolution protocol attack. And this exploits vulnerabilities in the address resolution protocol, which maps IP addresses to MAC addresses in local networks. And the first type of attack is ARP poisoning. So this is when the attacker sends fake ARP messages associating their MAC address with the IP address of a legitimate device. And this leads to unauthorized access and the interception of network traffic. And then you have what is called ARP spoofing, and this is a form of ARP poisoning where an attacker pretends to be another device on the network, and it is used for on-path attacks or man-in-the-middle attacks to capture and alter data. And the impact of ARP attacks are as follows. So there's unauthorized access to sensitive data, data interception and manipulation, and the potential for a DOS attack. Next, we have what is called a DNS attack. So domain name system attacks, they manipulate DNS queries and responses to redirect users to malicious websites. And within that, we have what is called DNS poisoning. And this is when an attacker corrupts the DNS cache by inserting false mappings between domain names and IP addresses. And then there's DNS spoofing, and this is when attackers intercept and modify DNS responses to misdirect users to fake websites. And here's the potential impact of a DNS attack. So it redirects users to phishing or malware-laden sites. It enables credential theft and financial fraud, and it compromises business integrity and trust. All right, next we have rogue devices and services. So there are unauthorized DHCP and access points. So attackers, they may introduce rogue devices into a network to manipulate traffic and gain unauthorized access. And within that, you have what is called a rogue DHCP server. And this is when an attacker sets up a fake DHCP server that assigns malicious network configurations, and it redirects traffic to attacker-controlled gateways. And then you have what is called a rogue access point. And this is an unauthorized wireless access point that is deployed to intercept or manipulate network traffic. And the impact is it provides unauthorized network access. There's data interception and manipulation, and it facilitates other network attacks such as evil twin setups. And speaking of an evil twin, so there's the evil twin attack, and this is a rogue Wi-Fi access point that mimics a legitimate access point to trick users into connecting to it. And its impact is it provides man-in-the-middle data interception. There's the theft of login credentials and personal data, and there's also the introduction of malware into user devices. Next, we have what is called an on-path attack, also known as a man-in-the-middle attack. And this occurs when an attacker intercepts and manipulates communication between two parties. And the common techniques are ARP poisoning, DNS poisoning, and Wi-Fi eavesdropping. And the impact is data and theft manipulation, unauthorized access to accounts, and the potential for financial fraud and identity theft. Next, we have social engineering attacks. And the first one we're going to talk about is called phishing. And this involves tricking users into providing sensitive information via fraudulent emails, messages, or websites. Then you have what is called dumpster diving. And this is when attackers, they go through discarded documents or hardware to retrieve sensitive information. There's also shoulder surfing, and this is when somebody observes someone's screen or keyboard input to steal their credentials. And then you have what is called tailgating, and this is gaining unauthorized physical access to a secure area by following an authorized person. And here are the impacts of social engineering. So there's once again the theft of sensitive credentials, the compromise of secure environments, and unauthorized access to networks and systems. All right, so let's move on and talk about some malware attacks. And here's some of the most common ones. So the first one is a virus, and this is malicious code that replicates and spreads. Then you have what is called a worm. This is self-replicating programs that exploit vulnerabilities. Then you have what is called a Trojan, and this is disguised as legitimate software, but it executes malicious actions. Then there's ransomware, where this encrypts files and demands payment for decryption. You have spyware, where this secretly collects user information. And then you have what is called a keylogger, where this captures keystrokes to steal credentials. And the impact is there's system corruption and data loss, financial and reputational damage, and network downtime and productivity loss. So in conclusion, understanding these attack methods is crucial for IT professionals preparing for the CompTIA Network Plus exam. And by recognizing how these attacks operate and their potential impact, network admins, they can implement proactive security measures, including regular security patches and updates, network segmentation and access controls, user awareness training, and intrusion detection and prevention systems. And by staying vigilant and informed, network professionals, they can strengthen cybersecurity defenses and protect organizational assets from evolving threats. All right, now with all of that being said, let's do some check on learning. So the first question is, which of the following attacks floods a switch's MAC address table, causing it to act like a hub and forward packets to all connected devices? Would this be VLAN hopping, MAC flooding, ARP poisoning, or an evil twin? And the correct answer is this will be MAC flooding. So MAC flooding, this overwhelms a switch's MAC address table by sending a large number of packets with different source MAC addresses. And once the table is full, the switch enters a fail open state and broadcasts traffic to all connected devices, making it easier for an attacker to intercept sensitive data. Next question. An attacker sets up a fraudulent Wi-Fi access point that mimics a legitimate one to intercept user credentials. What type of attack is this? Is this DNS spoofing, evil twin, on-path attack, or a rogue DHCP server? And the correct answer is this will be an evil twin. So an evil twin attack involves an attacker setting up a fake Wi-Fi access point with the same SSID as a legitimate network, and users, they unknowingly connect to the malicious access point, allowing the attacker to capture login credentials and other sensitive information. And our final question, which type of attack manipulates the resolution of domain names to redirect users to malicious websites? Would this be ARP poisoning, VLAN hopping, DNS poisoning, or tailgating? And the correct answer is this will be DNS poisoning, also known as DNS cache poisoning. And this corrupts the DNS cache by injecting false DNS records, causing users to be redirected to malicious sites instead of legitimate ones. And this attack is often used for phishing, malware distribution, and credential theft. In today's digital world, securing a network is just as crucial as setting it up. And cyber threats, they continue to evolve, making it imperative for IT professionals to apply effective network security measures. And the CompTIA Network Plus exam emphasizes the importance of securing network infrastructure using a combination of device hardening techniques, network access control, key management, security rules, and zones. In this video, we're going to explore these concepts in detail, providing practical guidance on implementing them in real-world scenarios. All right, so let's begin with device hardening. So device hardening, this refers to the process of securing network devices by reducing their attack surfaces. And this involves disabling unnecessary services, securing passwords, and implementing best security practices. So let's talk about disabling unused ports and services. So many network devices, including switches, routers, and firewalls, they come with default settings that enable multiple ports and services, some of which may not be necessary for the organization. And attackers, they can exploit open ports to gain unauthorized access, making it critical to disable any that are not in use. So here are the steps to disable unused ports and services. So first thing you want to do is identify the unused ports. So you want to use network scanning tools like Nmap to detect open ports. Then you want to disable in-device configuration. So for switches and routers, you want to use commands like interface gigabit Ethernet 01 shutdown and exit. And then you want to use firewalls to block ports. So you want to implement firewall rules to restrict access to unnecessary ports. And then you want to monitor for changes. So you want to use security monitoring tools to detect if a previously disabled port becomes active. Next, you want to change your default password. So many network devices, they come with default username and passwords, which are well documented and easily found by attackers. So changing default credentials, this is one of the simplest yet most effective security measures. And here are the best practices for password management. So you want to use strong passwords with a mix of uppercase, lowercase numbers, and special characters. You want to implement multi-factor authentication where possible. You want to avoid reusing passwords across multiple devices, and you want to regularly update passwords and store them securely by using a password manager. All right, next let's talk about network access control, and this enforces security policies to prevent unauthorized devices from accessing the network, and this helps in mitigating threats like rogue devices and unauthorized access. So let's go ahead and talk about port security. So port security, this restricts devices that can connect to switches by limiting MAC addresses, and this is particularly useful in preventing unauthorized devices from connecting to a network. And here are some of the basic steps to go about implementing port security. So the first thing you want to do, you want to enable port security, which you can do so by typing in these types of commands right here. And then you want to only allow specific MAC addresses, which as you can see right here, here's some commands to help you kind of illustrate that. And then after you do all of that, you want to monitor and respond to violations. So you want to use logging mechanisms to track security violations when they occur. All right, next let's talk about 802.1x authentication. So 802.1x, this is a network access control protocol that authenticates devices before allowing them network access. And it is commonly used in enterprise environments to secure wired and wireless networks. And the components of 802.1x are as follows. So you have what is called the supplicant, and this is the device that's requesting access. You have what is called the authenticator. This is the switch or wireless access point that is controlling access. And then you have the authentication server, and this is a radius server that verifies credentials. Next is MAC filtering. So MAC filtering, this restricts network access to specific devices based on their MAC addresses. And to configure MAC addresses for routers, you want to navigate to the security settings and manually enter the allowed MAC addresses. You want to use commands on managed switches to allow only specific MAC addresses. Then you want to combine with VLAN segmentation to further enhance security. All right, so let's move on and talk about key management. So effective key management, this is essential for encrypting communications and securing sensitive data. And the best practices for key management are as follows. So you want to use secure key exchange protocols like Diffie-Hellman and RSA. You want to rotate encryption keys periodically to minimize risk. You want to store keys securely using hardware security modules or key management systems. And then you want to implement access controls to restrict key usage to authorized personnel. All right, next let's talk about security rules. So security rules, they help enforce access control, filter malicious content, and protect network resources. And within that, we have what is called an access control list. And this defines rules that allow or deny traffic based on IP addresses, protocols, or ports. And an example of an ACL configuration would be to deny all traffic except web and SSH access, as you can see on your screen right here in these commands. And then we have what is called URL filtering, and this restricts access to websites based on policies. And the implementation steps are as follows. So you want to use a firewall or proxy servers to block harmful domains. You want to employ DNS filtering services like OpenDNS or Cloudflare. And then you want to set category-based restrictions to prevent access to malicious sites. Next, we have content filtering, and this prevents access to harmful or inappropriate content, which improves network security and productivity. And the methods for content filtering are as follows. So you want to use next generation firewalls with deep packet inspection. You want to deploy secure web gateways to inspect web traffic, and you want to implement email filtering to prevent phishing attacks. All right, so let's move on and talk about zones. So, network segmentation into trusted and untrusted zones. This helps in isolating sensitive assets and reducing attack services. So, a trusted zone, this consists of internal controlled network resources, while an untrusted zone includes external networks like the internet. And the best practices for secure zone management are as follows. You want to use firewalls to enforce security policies between zones. You want to restrict direct access from untrusted to trusted zones. You want to implement intrusion prevention systems to detect and mitigate threats. Then we have what is called a screen subnet or a DMZ, and that stands for demilitarized zone. And this is a network segment that hosts publicly accessible services like web and email filters. And to configure a DMZ, you want to deploy firewalls. So you want to place a firewall between the internal network and DMZ, and another between the DMZ and the internet. Then you want to restrict traffic flow. So you want to use ACLs to limit traffic between the DMZ and the internal network. And then you want to monitor the logs. So you want to regularly inspect firewall logs for any suspicious activity. All right, so in conclusion, implementing robust network security measures, this is essential to protecting digital assets and maintaining a secure IT environment. And by applying device hardening techniques, enforcing network access control policies, managing encryption keys effectively, defining strict security rules, and segmenting networks into zones, IT professionals can significantly enhance network security. And these principles are fundamental to the CompTIA Network Plus exam and serve as a crucial skill for real-world network security implementation. And by mastering these techniques, IT professionals, they can build and maintain secure networks that withstand evolving cyber threats. All right, so let's do some check on learning. So the first question is, a network administrator is securing a switch by limiting access to specific MAC addresses on each port. Which network security feature is being implemented? Would this be 802.1x authentication, port security, network access control, or access control lists? And the correct answer is this will be port security. So port security, this is a feature that restricts a switch port to allow only specific MAC addresses to connect, preventing unauthorized devices from accessing the network. And this is an effective way to mitigate threats such as MAC address spoofing. Next question. An organization wants to ensure that only authenticated users can access its corporate network before obtaining an IP address. Which security mechanism should be implemented? Would this be MAC filtering, an access control list, 802.1x authentication, or URL filtering? And this will be 802.1x authentication. So 802.1x, this is a port-based authentication protocol used for network access control. It requires a client device to authenticate before being granted network access, and it is often integrated with Radius or other types of authentication servers. And our final question, a company wants to prevent employees from accessing non-work related websites while on the corporate network. Which security measures should be used? Would this be content filtering, key management, port security, or a screen subnet? And the correct answer is this will be content filtering. So content filtering, this is used to restrict access to specific websites or types of content based on predefined rules. And this can be implemented through firewalls, proxy servers, or security appliances to block access to unauthorized or harmful websites. Troubleshooting network issues. This is a fundamental skill of IT professionals, and the CompTIA Network Plus exam emphasizes a structured approach to diagnosing and resolving network problems. And in this video, I'm going to break down the CompTIA troubleshooting methodology into its essential steps and provide insights into how IT professionals can effectively troubleshoot network-related issues. All right, so let's begin with step one, which is identifying the problem. So the first step in troubleshooting is to identify the problem accurately. Without a clear understanding of the issue, efforts to resolve it may be misdirected. And this step includes the following sub-steps. So first, you want to gather information. So begin by collecting as much relevant data as possible. And this can include system logs, error messages, and network monitoring tools such as Wireshark or SolarWinds. Then you want to question users. So users experiencing the issue, they can provide valuable information about what happened before the problem occurred. So you want to ask open-ended questions questions like, when did the issue start? What were you doing when the problem occurred? And have you noticed any patterns or triggers? Then you want to identify symptoms. So you want to determine the scope of the problem by identifying symptoms. So for example, is the entire network down, or is it only affecting specific users or applications? Because symptoms, they can guide you towards an initial diagnosis. Do you want to determine if anything has changed? So network issues, they often arise due to recent changes. So you want to ask if any hardware, software configuration changes were made before the issue started. Do you want to duplicate the problem if possible? So try to replicate the issue under controlled conditions, because this can help verify the nature of the problem and confirm user reports. Do you want to approach multiple problems individually? So if there are multiple issues occurring at once, separate them and troubleshoot them one at a time to avoid confusion. All right, so step 2 is you want to establish a theory of probable cause. So once you have identified the problem, the next step is to determine its probable cause. And the first thing you want to do, you want to question the obvious. So sometimes the simplest explanations are the correct ones. So you want to check for basic connectivity issues, unplugged cables, misconfigured settings, or power outages. Do you want to consider multiple approaches? So there are various approaches to troubleshooting network issues. You can do what is called the top to bottom or bottom to top OSI model. This method involves starting at either the application layer and working down, or starting at the physical layer and working up to isolate the issue. Or you can do what is called the divide and conquer. So you can test various network segments to narrow down the location of the issue. So for example, if a network switch is suspected to be faulty, you want to test connectivity before and after the switch to determine its functionality. Step 3, this is test the theory to determine the cause. So now that you have a theory, you need to test it to confirm whether it's the actual cause of the problem. So if the problem is identified, you need to plan how to resolve it. You want to consider factors like downtime, user impact, and whether a temporary fix or permanent solution is necessary. Then if the theory is not confirmed, you want to establish a new theory or escalate it. So if testing disproves your theory, you want to develop a new hypothesis based on your findings. And if the issue is beyond your expertise or access level, you want to escalate it to a senior technician or vendor support. Step 4, you want to establish a plan of action to resolve the problem and identify potential effects. So a resolution plan should be methodical to avoid unintended consequences. So you want to consider these factors. First thing is risk assessment. So will this fix cause downtime for issues? Then there's a rollback plan. If the solution does not work, how will you revert the changes? Then there's testing procedures. So how will you verify that the fix was successful? Next is step 5. So you want to implement the solution or escalate as necessary. After developing a plan, it's time to implement the fix, and the complexity of the solution will vary. So a simple fix like reconnecting a cable, this can be done immediately. A complex fix like reconfiguring a router, this may require scheduled downtime. And if the issue is beyond your authority, you want to escalate it to network engineers, ISPs, or hardware vendors. Then that leads us to step 6. So you want to verify full system functionality and implement preventative measures. So once the solution has been applied, it's time to test the system to ensure the issue is fully resolved. And the way to go about doing a full system functionality check is you want to check if affected users can access the network or services as expected. You want to run diagnostic tests and monitoring tools to confirm stability. Then you want to stress test the system under expected loads. And then you want to implement preventative measures. So if possible, take steps to prevent the issue from reoccurring. So apply patches or updates to prevent known bugs, enhance network monitoring to detect similar issues early, and most importantly, train users on best practices to avoid future problems. And finally, we arrive at step 7. So you want to document findings, actions, outcomes, and lessons learned. So proper documentation, this ensures that similar issues can be resolved more efficiently in the future. And here's what you should document. So obviously we want a description of the problem. So you want to include symptoms and affected systems. You want to document your theories tested. So what theories were considered and which were ruled out. Document your actions taken. So describe the troubleshooting steps and final solution. Document the final solution. So detail how the issue was resolved and any lingering concerns. Then document the preventative measures. So list any changes made to prevent recurrence. All right, so in conclusion, the CompTIA Network Plus troubleshooting methodology, this provides a structured approach to diagnosing and resolving network issues. And by following these steps, such as identifying the problem, establishing a theory, testing the theory, planning and implementing a solution, verifying functionality, and documenting results, you can troubleshoot effectively and minimize downtime. So whether you're an aspiring network technician or a seasoned IT professional, mastering this methodology is crucial for maintaining a reliable network infrastructure. All right, so let's do some check on learning. So our first question is, a user reports that their workstation cannot connect to the company network. As the first step in the troubleshooting methodology, which of the following actions should you take? Should you establish a theory of probable cause? Should you test the theory to determine the cause? Should you identify the problem? Or should you document findings, actions, and outcomes? And the correct answer is you want to identify the problem. So the first step in the troubleshooting methodology is to identify the problem. And this includes gathering information, questioning users, identifying symptoms, determining any recent changes, and attempting to duplicate the issue if possible. Establishing a theory and testing, all of that comes later in the process. Next question. After identifying a network connectivity issue, you suspect that a recent configuration change on a switch may be the cause. What is the next step in the troubleshooting methodology? Is it you want to establish a theory of probable cause? You want to verify full system functionality? You want to implement the solution? Or you want to document your findings? And the correct answer is you want to establish a theory of probable cause. So once the problem is identified, the next step is to establish a theory of probable cause. And this involves questioning the obvious and considering multiple approaches, such as analyzing the OSI model or using a divide and conquer strategy. Testing the theory, this follows after its establishment. And our final question, you have successfully resolved a DNS misconfiguration issue and the user's workstation is now able to connect to the network. Before closing the ticket, what is the final step in the troubleshooting methodology? Is it establishing a plan of action, implementing the solution, documenting findings, actions, and outcomes, or establishing a theory of probable cause? And the correct answer is documenting findings, actions, and outcomes. So the last step in the troubleshooting methodology is documentation. And this includes recording what the issue was, how it was resolved, and any preventative measures implemented. Proper documentation, this ensures that similar issues can be resolved more efficiently in the future. Reliable network connectivity. This is critical for maintaining smooth business operations, and cabling issues, they could be a major cause of network failures. So whether you are dealing with incorrect cables, signal degradation, improper termination, or hardware mismatches, understanding how to troubleshoot these problems is essential for any network professional. And in this video, which is aligned with the CompTIA Network Plus exam objective 5.2, we're going to cover common cabling and physical interface issues, their causes, and solutions. All right, so let's begin with cabling issues, and we're going to talk about incorrect cable types first. So using the wrong cable type, this can cause performance issues, connectivity issues, and slow data transmission. And here are some common mismatches. So let's talk about single mode and multi-mode fiber optics. So we have single mode fiber. So this uses a small core around 9 microns and a single light path. And this is designed for long distance transmissions up to 100 kilometers. Then you have multi-mode fiber. This has a larger core of 50 to 62.5 microns and multiple light paths, making it suitable for shorter distances up to 550 meters for gigabit Ethernet. And when it comes to troubleshooting, you want to verify that both ends of the link use the same fiber type. You want to check the color coding of the fiber cables. You have yellow for single mode fiber and orange or aqua for multi-mode fiber. And you want to ensure the correct transceiver is used for the fiber type. All right, next we have category 5, 6, 7, and 8 cable differences. So Cat5, this supports up to 100 megabits per second, and this is considered outdated. You have Cat5e, this is the enhanced version of Cat5 and supports 1 gigabit per second. Cat6, this supports 1 gigabit per second at 100 meters and 10 gigabits per second at 55 meters. You got Cat6a, this supports 10 gigabits per second at 100 meters. Cat7 and 7a, they use shielding for better performance, and they support 10 gigabits per second. Then you got Cat 8. This supports up to 40 gigabits per second over 30 meters. Now, when it comes to troubleshooting, you want to ensure the cable category matches network speed requirements. You want to replace outdated Cat 5 cables in high-speed networks. Then you want to verify connectors and patch panels are rated for the same category. Next, we have shielded twisted pair and unshielded twisted pair. So shielded twisted pair, this has extra shielding to protect against electromagnetic interference. An unshielded twisted pair, this is more common and cost effective, but it lacks the EMI protection. And when it comes to troubleshooting, you want to use STP in high interference environments, whether near electrical cables, radio towers, or industrial settings. And you also want to ensure proper grounding for STP to avoid signal reflection issues. All right, so let's move on and talk about signal degradation. And the first aspect we're going to talk about is called crosstalk. And this occurs when signal leakage from one cable interferes with another. And within that, we have what is called near-end crosstalk. And this is interference at the cable sending end. And then we have what is called far-end crosstalk. And this is interference at the receiving end. And when it comes to troubleshooting, you want to use higher capacity cables like Cat 6 or higher to reduce crosstalk. You want to ensure proper cable separation and avoid running cables parallel to power lines. Next, we have what is called interference. So external sources like fluorescent lights, microwaves, or other devices, they can disrupt signals. When it comes to troubleshooting, you want to use shielded cables for STP or fiber to minimize interference. You want to keep network cables away from power lines and electrical equipment. Then we have what is called attenuation, and this is signal loss over distance due to resistance and cable quality. And when it comes to troubleshooting, you want to use signal repeaters for long distances. You want to upgrade the fiber optics for long-range connectivity. And you want to avoid exceeding cable distances like 100 meters for Ethernet UTP and STP. All right, so let's move on and talk about improper termination. So improper crimping, incorrect pinouts, and loose connections, all of this can cause connectivity failure. So when it comes to troubleshooting, you want to use a cable tester to verify correct wiring. You want to follow the TIA 568B and 568A standards for Ethernet cabling, and you want to ensure your RJ45 connectors are properly crimped. All right, next let's talk about transmitter receiver transpose. So this occurs when transmit and receive cables are swapped. And when it comes to troubleshooting, you want to check cable polarity with a network tester, and you want to use the correct straight through or crossover cable as required. All right, moving on, let's talk about some interface issues. And let's first talk about increasing interface counters. So errors in packet transmission, they indicate underlying issues. And within that, we have what is called cyclic redundancy checks or CRC errors. And this occurs due to corrupt packets caused by faulty cables, interference, or incorrect duplex settings. And to troubleshoot this, you want to replace or inspect cables for damage. And then you want to check your duplex settings because they should be matching on both ends. Then we have what are called runts, and these are packets that are smaller than the minimum Ethernet frame size of 64 bytes. And these things can cause collisions and duplex matches. And how to troubleshoot them, you want to enable auto negotiation or manually set correct speeds in duplex. And you also want to replace failing network cards or cables. Then we have what are called giants, and these are oversized packets that exceed the MTU limits. And to troubleshoot them, you want to adjust the MTU settings to match network requirements, and then you want to investigate the NIC settings for jumbo frame support. And then you have what are called drops, and these are packets that are discarded due to congestion. And to troubleshoot them, you want to monitor QoS policies and bandwidth usage, and you also want to reduce network congestion by optimizing traffic flow. All right, next we have what are called port status issues. And the first one is error displayed. So a switch port automatically shuts down due to security violations, such as the BPDU guard, port security, or STP loops. And to troubleshoot this, you want to identify the root cause showing interface commands. And you want to reactivate the port using shutdown or no shutdown commands. Then you have what is called administratively down. And this is when the port is manually disabled. And to troubleshoot this, you want to enable the port using no shutdown command, and then verify the port configurations and policies. And then you have what is called suspended. And this is when the port is in a suspended state due to mismatched channel configurations. And to fix this, you want to ensure the correct Ethernet channel settings, and then check your switch logs for error messages. All right, so let's move on and talk about hardware issues. And we're going to start with power over Ethernet issues. And within that, we have what is called the power budget that has been exceeded. So if the PoE switch exceeds its power budget, then new devices may not power on. And to fix this, you want to check the switch power capacity. Do you want to reduce the number of PoE devices or upgrade the switch? And then we have the incorrect standard. So using incompatible PoE standards, this can cause device failures. And to fix this, you want to verify PoE standards on both switch and powered devices, and then you want to use mid-span injectors for additional power needs. All right, next we have what are called transceiver issues, and within that you can have a mismatch, and this is using the wrong transceiver module for the fiber or copper interface. And to fix this, you want to ensure the correct SFP, SFP plus, and QSFP module is used. If you want to match the transceiver wavelength with the fiber type, then you have signal strength issues. So weak signals, they can lead to packet loss and slow speeds. And to fix this, you want to use an optical power meter to measure signal levels and replace or clean fiber connectors. All right, so in conclusion, troubleshooting cable and interface issues, this requires a methodical approach using the right tools and understanding physical layer fundamentals. So whether dealing with incorrect cables, signal degradation, port issues, or power over Ethernet problems, following structured diagnostics, this will help ensure reliable network performance. And by mastering these skills, IT professionals, they can effectively prevent and resolve network connectivity problems. All right, so let's do some check on learning. So our first question is, a technician is troubleshooting a fiber optic network issue where devices are unable to communicate. Upon inspection, they discover that a single mode fiber cable has been used instead of a multi-mode fiber cable. What is the likely result of this incorrect cable usage? Would this be excessive crosstalk causing signal distortion, a short transmission distance due to high attenuation, the link will not function due to incompatible optical transceivers, or interference from electromagnetic sources? And the correct answer is the link will not function due to incompatible optical transceivers. So single mode and multi-mode fiber cables require different transceivers due to differences in core size, wavelength, and transmission properties. Using a single mode fiber with a multi-mode transceiver or vice versa, this typically results in a non-functional link, and the signal may not properly propagate, which will prevent communication between devices. Next question. A network admin is diagnosing intermittent connectivity issues on a twisted pair Ethernet cable. Upon testing, they notice significant attenuation over a long cable run. What is the best solution to mitigate this issue? Would it be replace the cable with a shorter one or install a repeater? Would it be use shielded twisted pair instead of unshielded twisted pair? Would it be increase the transmit power of the network devices? Or would it be disable auto negotiation on both ends of the link? And the correct answer is to replace the cable with a shorter one or install a repeater. So attenuation occurs when a signal weakens over long distances. The maximum recommended length for Ethernet cables is 100 meters or 328 feet. If a cable exceeds this limit, signal strength degrades, leading to intermittent or failed connections. So the best solution is to reduce cable length or install a repeater, such as a switch, to regenerate the signal. And our final question, a network technician is troubleshooting a switch port that is administratively down and is unable to pass traffic. What is the most likely cause of this issue? Is it a high number of cyclic redundancy check errors? Is it a manually disabled port configuration in the switch? Is it a cable mismatch between STP and UTP? Or is it excessive signal attenuation due to a long cable run? And the correct answer is a manually disabled port configuration in the switch. So if a port is labeled as administratively down, this means that an admin has manually disabled the port through the switch's configuration settings, such as using the shutdown command on Cisco devices. To restore functionality, the admin must enable the port using the appropriate command, such as typing in no shutdown. Network administrators and IT professionals, they often encounter various issues with network services that can disrupt connectivity, slow down performance, or compromise security. And the CompTIA Network Plus exam emphasizes the ability to troubleshoot common network service problems effectively. And in this video, We're going to examine key network troubleshooting scenarios, including switching issues, route selection, address pool exhaustion, incorrect gateway configurations, and IP addressing errors. And understanding these topics is critical for ensuring smooth network operations and maintaining optimal performance. All right, so let's begin by talking about switching issues. So switching issues, they can cause disruptions in network traffic, leading to poor connectivity and performance. And the following are some common switching issues and their respective troubleshooting methods. So let's go ahead and talk about spanning tree protocol. And within that, we have network loops. And network loops, they can occur when redundant links between switches cause continuous loops in data traffic. And this can lead to excessive broadcast storms and network failures. And to fix all of that, you want to verify that SPT is enabled on all switches. You want to identify redundant links and manually disable one if STP is not functioning properly. You want to use the show spanning tree command on Cisco devices to check the STP status. And then you want to ensure the STP is properly configured and not disabled by mistake. And then next we have what is called the root bridge selection. So the root bridge, this is the central switch in an STP configured network that determines the shortest path for data transmission. And incorrect root bridge selection, this can cause inefficient traffic flow. So to fix that, you want to use the show spanning tree root command to determine the current root bridge. You want to ensure the lowest bridge priority is assigned to the preferred switch to make it the root bridge. And then you want to adjust the priority values if an undesired switch has been elected as the root. Then we have port roles. So each port in an STP topology is assigned a role such as a root port, designated port, or blocking port. And misconfigured port roles, this can lead to suboptimal traffic flow. And to fix that, you want to check the STP port roles using the show spanning tree interface. And then you want to reassign roles if necessary to ensure traffic follows the most efficient path. And then we have what are called port states. So ports in an STP enable network transition through different states, such as blocking, listening, learning, and forwarding. And if a port remains in a state other than forwarding for an extended period, connectivity issues may arise. And to fix that, you want to verify port states using the show spanning tree command. Then you want to check for misconfigured timers that delay port state transitions. And then you want to use rapid spanning tree protocol to speed up convergence. All right, next let's talk about an incorrect VLAN assignment. So VLAN misconfiguration, this can prevent devices from communicating with each other as expected. And to fix that, you want to use the show VLAN brief command to verify VLAN assignments. You want to ensure that devices within the same VLAN have the correct VLAN ID. Do you want to check trunk port configurations using the show interfaces trunk command to confirm proper VLAN tagging? And then you want to use the switch port mode trunk or switch port mode access commands to correctly configure VLAN membership. And then we have access control lists. So ACL misconfigurations, they can block legitimate traffic and cause connectivity issues as well. And to fix that, you want to check ACL configurations by using the show access list command. You want to ensure rules allow necessary traffic while blocking unauthorized access. You want to verify the rule order as ACLs are processed from top to bottom. And then you want to use the show IP interface command to see which ACLs are applied to interfaces. All right, next let's talk about route selection issues. And within that, we're going to talk about a routing table. So a missing or incorrect route in the routing table, this can lead to packet loss and communication failures. So to fix that, you want to use the show IP route command to verify routing table entries. You want to ensure routes are correctly learned through dynamic protocols like OSPF or EIGRP, or they are statically configured. And then you want to check for misconfigured administrative distances that may cause incorrect route selection. Next, we have default routes. So default routes, they direct traffic to destinations not explicitly listed in the routing table. And if they're misconfigured, packets may not reach their intended destinations. So to fix this, you want to use the show IP route 0.0.0.0/0 command to verify the default route. Then you want to ensure the next hop address or exit interface is correctly configured. And then you want to confirm that dynamic routing protocols propagate the default route correctly. All right, next let's talk about address pool exhaustion. And this occurs when all available IP addresses in a DHCP pool are allocated, preventing new devices from attaining an IP address. And to fix this, you want to use the show IP DHCP binding command to check assigned addresses. Then you want to increase the DHCP scope if more addresses are needed. After that, you want to reduce release time to free up unused addresses faster. Do you want to identify and remove unauthorized devices that are consuming addresses? Next, we have an incorrect default gateway. So if a device's default gateway is misconfigured, it will be unable to communicate with devices outside its local network. So to fix this, you want to check gateway configurations using the ipconfig command for Windows or ifconfig for Linux and Mac. Do you want to ensure the default gateway matches the router's IP address on the same subnet? And then you want to verify that the router interface serving as the gateway is operational using the ping command. Next, we have incorrect IP address assignments, and within that, we have duplicate IP addresses. So duplicate IP addresses, they can cause IP conflicts, leading to connectivity problems for affected devices. And to fix that, you want to use the ARP-A command to identify duplicate IP addresses. Then you want to check the DHCP server for static assignments that overlap with dynamic ranges. After that, you want to modify static IP configurations to avoid conflicts. Then you want to implement IP address management to prevent duplication. And then we have an incorrect subnet mask. So an incorrect subnet mask, this can prevent devices from communicating with other hosts in the intended network. And to fix that, you want to verify subnet mask using the ipconfig/all command. You want to ensure all devices in the same network have a consistent subnet mask. Then you want to use subnet calculators to validate correct subnet configurations. All right, so in conclusion, troubleshooting network services, this requires deep understanding of common networking concepts, configurations, and diagnostic tools. And by mastering the troubleshooting steps outlined in this video, IT professionals, they can efficiently resolve network service issues that are related to switching, routing, address allocation, and IP configuration errors. And these skills, they are essential for success in the CompTIA Network Plus exam and real-world networking environments. All right, so let's go ahead and do some check on learning. So our first question is, a network admin notices intermittent connectivity issues and high traffic spikes on the network. Upon investigation, they discover multiple redundant links between switches. Which protocol should be checked to resolve this issue? Would this be OSPF, STP, DHCP, or NAT? And the correct answer is STP. So spanning tree protocol. This is used to prevent network loops in a switching environment by determining a root bridge and assigning port roles. If STP is misconfigured or disabled, redundant links between switches can create broadcast storms and network loops, leading to instability and intermittent connectivity. Next question. A user reports that they cannot access resources on a different VLAN. The network admin checks the switch configuration and sees that the port is assigned to VLAN 10, but the resource is on VLAN 20. What is the most likely issue? Is it the switch has a failing power supply? Is it the router is not configured with a default route? Is it the port is assigned to the incorrect VLAN? Or is it the user has an incorrect IP address? And the correct answer is the port is assigned to the incorrect VLAN. So if a user is assigned to VLAN 10, but needs to access resources on VLAN 20, they will not be able to communicate without proper VLAN assignment or inter-VLAN routing. So checking and correcting the VLAN assignment on the switch, this can resolve the issue. And our final question, a technician is troubleshooting an issue where multiple devices on the network are experiencing connectivity problems. Upon checking the DHCP server, they notice that no new devices are obtaining IP addresses. What is the most likely cause? Is it the default gateway is misconfigured, the DHCP address pool is exhausted, a network ACL is blocking access, or the DNS server is unreachable? And the correct answer is the DHCP address pool is exhausted. So if the DHCP server's address pool is exhausted, it means that there are no more available IP addresses to assign to new devices. This can prevent devices from connecting to the network unless more addresses are allocated, release time is adjusted, or unnecessary reservations are removed. Network performance issues can be frustrating, leading to slow speeds, connectivity drops, and application failures. And as an IT professional preparing for the CompTIA Network Plus certification, you must understand how to diagnose and resolve common network performance problems. And this video is going to explore various performance issues, including congestion, bottlenecks, bandwidth limitations, latency, packet loss, jitter, and wireless connectivity challenges. And by mastering these troubleshooting techniques, you can enhance network efficiency and ensure seamless communication across wired and wireless infrastructure. All right, so let's begin by talking about some common performance issues, and we're going to start with congestion and contention. So, network congestion, this occurs when too many devices compete for limited network resources, leading to slower performance. And the common causes are excessive network traffic from high bandwidth applications like video streaming and large file transfers, insufficient network infrastructure to support peak loads, and multiple devices sharing a limited bandwidth connection. And to fix all of this, you can use network monitoring tools like Wireshark, SolarWinds, and PRTG to analyze traffic patterns. You can identify and prioritize mission critical applications using quality of service. You can upgrade network hardware such as switches, routers, and network interface cards. And you can implement traffic shaping and bandwidth allocation policies to prevent bottlenecks. And speaking of bottlenecks, so a bottleneck, this occurs when a network component like a router, switch, or a server limits overall network performance. And the common causes are outdated or underpowered hardware, high CPU memory utilization on network devices, and insufficient bandwidth for connected devices. And to go about fixing all of this, you can check device utilization, such as the CPU, memory, and disk input output using SNMP monitoring tools. And you can upgrade network equipment like replacing fast Ethernet with gigabit Ethernet. You can distribute workloads across multiple network paths like implementing load balancing, or you can implement VLANs to optimize traffic flow. All right, next we have bandwidth and throughput capacity. So bandwidth, this is the maximum data transfer rate of a network connection, and throughput, this is the actual data transmission rate over a network link. And the common causes of low throughput are as follows. So you have network congestion or bottlenecks, poor quality cabling or hardware faults, or high network load during peak hours. And to fix all of this, you can run speed tests using tools like iPerf or speedtest.net. You can identify high bandwidth applications or restrict or optimize them. You can upgrade to a higher speed internet plan or network link, or you can replace outdated cables like upgrading from Cat5e to Cat6 or Cat6a. All right, next we have latency, and this refers to the delay in data transmission from source to destination. And the common causes are the distance between endpoints. So you could be dealing with an international connection that has a higher latency, network congestion or inefficient routing, or inefficient processing power on network devices. And to fix this, you can use ping or trace route to measure delay and identify routing inefficiencies. You can optimize routing paths by configuring BGP, OSPF, or EIGRP. You can reduce the number of network hops by implementing content delivery networks. And you can upgrade to low latency switches and routers. All right, next we have packet loss, and this occurs when data packets fail to reach their destination. And the common causes are network congestion or hardware failure, wireless interference or poor signal strength, or misconfigured firewalls and security settings. And to fix this, you can run packet capture analysis with Wireshark to detect drops. You can check network cables and connectors for physical damage. You can adjust firewall settings to prevent unnecessary filtering. And you can reduce congestion by implementing traffic shaping or quality of service policies. Next, we have jitter, and this refers to the variation in packet arrival times leading to inconsistent network performance. And the common causes are high network congestion, poor routing or network misconfigurations, or insufficient bandwidth for real-time applications like voice over IP and video calls. And to deal with this issue, you can use ping or jitter testing tools like Ping Plotter or VoIP Monitor. You can implement QoS policies to prioritize time-sensitive traffic, or you can minimize congestion by increasing network capacity or implementing load balancing. All right, so let's move on and talk about wireless network performance issues. And first, we're going to talk about interference. And within that, we have channel overlap. So overlapping Wi-Fi channels, this can cause interference, which reduces network performance. And some of the common causes are nearby Wi-Fi networks that use the same channel and incorrect Wi-Fi channel settings. And to fix this, you can use Wi-Fi analysis tools like NetSpot or Wi-Fi Analyzer to scan for congestion, or you can switch to a less crowded Wi-Fi channel like channel 1, 6, or 11 for the 2.4 gigahertz frequency, or channels 36, 40, 44, or 48 for the 5 gigahertz frequency. Next, we have signal degradation or signal loss. So weak or unstable Wi-Fi signals, this can slow speeds and frequent disconnections. And the common causes are as follows. So it could be the distance from the Wi-Fi router or access point. It could be physical obstructions like walls, furniture, or metal objects. Or it could be interference from electronic devices like microwaves and Bluetooth devices. And to deal with this issue, you can move closer to the router or install additional Wi-Fi access points. You can remove obstructions or reposition the router, or you can switch to a higher frequency band like 5 gigahertz or 6 gigahertz for improved performance. The next issue is insufficient wireless coverage. So dead zones or weak signal areas in large buildings or outdoor environments, they can cause insufficient wireless coverage. And some of the common causes are a limited range of access points, incorrect placement of Wi-Fi routers, or a lack of mesh networking support. And to fix this, you can install Wi-Fi extenders or mesh network systems. You can increase transmission power settings on the access point, or you can conduct a Wi-Fi site survey to optimize coverage areas. Next, we have what are called client disassociation issues, and this is when clients are randomly disconnected from Wi-Fi, causing interrupted connectivity. And some of the common causes are poor signal strength, authentication failures, and MAC address filtering or security misconfiguration. And to deal with this, you can verify your authentication settings, making sure you're on WPA2, WPA3, Radius, or 802.1x. You can check your access control lists and remove unnecessary restrictions, or you can update your wireless drivers and firmware for improved compatibility. And then we have what is called roaming misconfiguration. And this is when Wi-Fi clients fail to switch seamlessly between access points, causing network drops. And the common causes are poorly configured handover thresholds, mismatched SSID settings across access points, and a lack of support for fast roaming protocols like 802.11r, 802.11k, and 802.11v. And to fix all of this, you can enable 802.11r or fast roaming for seamless transitions. You can ensure consistent SSID settings across access points, and you can adjust signal strength thresholds to optimize handoffs. So in conclusion, network performance issues, they can severely impact business operations, user experience, and overall productivity. Now, by understanding common wired and wireless network performance issues such as congestion, bottlenecks, latency, packet loss, jitter, and Wi-Fi related problems, you can effectively diagnose and resolve network inefficiencies. And so mastering these troubleshooting techniques is essential for IT professionals that are pursuing the CompTIA Network Plus certification and those working in network administration, cybersecurity, and IT support roles. Now, with all of that being said, let's do some check on learning. So our first question is, a network admin is investigating slow performance on a company's wired network. The admin runs a throughput test and finds that data transfer rates are significantly lower than the advertised bandwidth. What is the most likely cause of this issue? Is it high latency, packet loss, network congestion, or wireless interference? And the correct answer is network congestion. So network congestion, this occurs when too many devices are transmitting data over the same network path, leading to slower throughput and higher contention for resources. Even if the network has high bandwidth, congestion can reduce actual data transfer rates, and latency and packet loss, this can contribute to slow performance, but congestion is the most likely culprit in this scenario. And wireless interference, this would not affect a wired network. Next question. A company's voice over IP phone system is experiencing frequent call drops, delays, and poor audio quality. After analyzing network traffic, the admin observes high levels of jitter. What is the best way to mitigate this issue? Would it be to increase available bandwidth, enable quality of service settings, upgrade network switches to newer models, or disable encryption on voice over IP packets? And the correct answer is to enable QoS settings. So jitter, this occurs when packet arrival times vary due to network congestion or inconsistent routing. Implementing QoS, this prioritizes voice over IP traffic, ensuring consistent packet delivery and reducing delays. Now, while increasing bandwidth may help, it does not specifically address jitter. Upgrading switches, this could be beneficial in some cases, but it is not the most direct solution. And disabling encryption, this is not a valid solution as it does not impact jitter. And our final question, a network admin is troubleshooting a wireless network issue where users frequently disconnect when moving between different areas of a building. The admin suspects a misconfiguration. What is the most likely cause of this issue? Is it roaming misconfiguration, client disassociation, channel overlap, or signal degradation? And the correct answer is this will be roaming misconfiguration. So roaming misconfiguration occurs when wireless access points do not properly hand off client connections as users move between coverage areas. And this can result in frequent disconnections and reconnections, leading to a poor user experience. Channel overlap, this can cause interference, but does not directly lead to frequent disconnections. Client disassociation, this can happen due to other factors such as security settings. And signal degradation, this affects coverage, but does not specifically explain issues related to roaming between access points. In the world of networking, issues are inevitable. However, the ability to efficiently troubleshoot and resolve these issues is a critical skill for network administrators, IT support professionals, and cybersecurity specialists. And the CompTIA Network Plus exam objective 5.5 is going to focus on selecting the appropriate tools and protocols to solve networking problems effectively. And in this video, we're going to explore essential software and hardware tools, as well as basic network device commands to enhance your troubleshooting capabilities. All right, so let's begin by talking about software tools for network troubleshooting, and let's go ahead and start with a protocol analyzer. So a protocol analyzer such as Wireshark, this is a critical tool for network troubleshooting. It captures and analyzes network traffic in real time, helping admins detect anomalies, security threats, and performance bottlenecks. And by inspecting packet details, network professionals can identify excessive retransmissions, unauthorized access, or misconfigured devices. All right, next we're going to talk about some command line tools. So command line tools, they provide quick insights into network connectivity, routing, and device configurations. And here are some of the most useful commands. So the first one is the ping command, and this tests network connectivity between devices. And if the ping is successful, it indicates that the target device is reachable. If not, it may suggest connectivity issues. And next we have the trace route command, and this maps the route that packets take to their destination, and this helps in identifying delays or drop connections at specific hops. And then you have the NS lookup command, and this queries the domain name system to resolve host names to IP addresses. And if a domain name fails to resolve, this could indicate DNS misconfigurations. Then you have the TCP dump command, and this captures and analyzes network packets, and is useful for diagnosing network performance issues and security threats. There's the dig command, and this queries DNS records with more advanced options than NS lookup. And this tool helps verify DNS settings and troubleshoot domain resolution issues. Then there's the net stat command, and this displays active network connections and listening ports, and is useful for detecting unauthorized connections and open ports. You have the IP, the ifconfig, and the ipconfig commands, and they show and configure network interfaces, and they help in verifying IP configurations, detecting conflicts, and resetting network adapters. You got the ARP command, and this displays and modifies the ARP table, and it helps in identifying MAC address conflicts and rogue devices. All right, next we have what is called Nmap, and this is a powerful network scanner used for discovering devices, open ports, and security vulnerabilities. And this helps in identifying active devices in a network. And then you have the LLDP or the CDP protocols, and they identify directly connected network devices, and they are useful for mapping network topology. And then you have what is called a speed tester, and this measures network bandwidth and latency, and tools like speedtest.net. They can help diagnose slow internet speeds and ISP issues. All right, so let's move on to talk about some hardware tools for network troubleshooting. And the first one is the toner and probe kit. So a toner and probe kit is used to trace cables in a network environment, identify mislabeled or disconnected cables. Then you have what's called a cable tester. This helps in verifying the continuity and integrity of network cables. So if a cable is faulty, it could lead to intermittent connectivity issues. Then you have what's called a network tap. And this is a hardware device that monitors network traffic passively without interfering. And these are used for deep packet inspection and performance monitoring. Next, we have what is called a Wi-Fi analyzer, and this is used to scan Wi-Fi networks, detect interference, and optimize signal strength. And examples of this include NetSpot and Wireshark. And then you have what is called a visual fault locator, which is the image on your screen right here. And this is used for fiber optic cables emitting a visible laser to detect breaks or misalignments in fiber connections. All right, so now we're going to talk about some basic networking device commands. So networking devices such as switches, routers, and firewalls, they have built-in commands that allow admins to diagnose connectivity issues. So the first command is the show MAC address table, and this displays the MAC addresses of devices connected to the switch, and this can help in tracking devices and troubleshooting VLAN segmentation issues. Then you have the show route command. This displays the routing table showing how data packets are forwarded, and this can help in verifying correct path selection. Then you have the show interface command. This displays status and statistics of network interfaces, and this is useful for diagnosing interface errors and bandwidth utilization. You got the show config command, and this displays the current configuration of a networking device. And this is used for verifying settings and identifying misconfigurations. You got the show ARP command. This displays the ARP table showing IP to map address mappings. And this helps in resolving connectivity issues and detecting MAC spoofing. You got the show VLAN command, and this displays VLAN configurations on a switch. And this is helpful in troubleshooting VLAN assignment and network segmentation. And then you got the show power command, and this displays the power consumption and availability of power over Ethernet devices. And this is useful for diagnosing PoE issues on IP phones and access points. All right, so in conclusion, effective network troubleshooting requires the right mix of software tools, hardware tools, and device commands. And by mastering these tools and techniques, IT professionals can quickly identify and resolve network issues, ensuring optimal performance and security. So whether it's diagnosing connectivity problems with ping, scanning for security vulnerabilities with Nmap, or inspecting network traffic with Wireshark, having a solid understanding of these troubleshooting methods is essential for anyone in the field of networking. Let's go ahead and do some check on learning. And our first question is, a network admin is troubleshooting a slow network connection on a router and wants to verify the routing table to check for any misconfigurations. Which command should they use? Would this be the show MAC address table, show route, show VLAN, or show power? And the correct answer is show route. So the show route command, this is used to display the routing table of a network device, helping admins verify and troubleshoot routing issues. And this command allows the admin to check for incorrect or missing routes that could be causing slow or failed connections. Next question. A technician needs to determine whether a remote web server is reachable and analyze the number of hops it takes to reach the destination. Which command line tool should they use? Would this be ping, netstat, TCP dump, or traceroute? And the correct answer is traceroute. So the traceroute command, this helps track the path that packets take to reach a destination, displaying each hop along the route. And this is useful for diagnosing network latency and routing issues by identifying points of delay or failure in the network path. And then our final question. A network engineer is troubleshooting an issue where a specific workstation cannot communicate with other devices on the network. The engineer suspects an ARP issue. Which command should they use to verify the workstation's ARP cache? Would this be ipconfig/all, show MAC address table, Nmap, or ARP-A? And of course, the correct answer is ARP-A. So the ARP-A command displays the ARP table showing the mapping of IP addresses to MAC addresses. So if a workstation is experiencing communication issues, checking the ARP cache, this can help determine whether the MAC address is associated with an IP, indicating potential issues like incorrect ARP entries or ARP poisoning.